So, good morning to everyone. We're here, the radio team. We're ready to start the online international workshop, the celebration of science, astronomy for peace. We join our cultures, our knowledge, our enthusiasm for astronomy. And today we're going to have presentations by the radio team who is here, and I will ask them to introduce themselves, and by schools in China, Pakistan, and Greece, who prepared very nice assignment presentations to show you that broadcast the whole universe, topics from the whole universe. So let's start. Let's start with Hira. Hira, can you hear us? Maybe, can you hear us now?
Eleni, are you talking to me?
Yes. Would you
Hello
like
everyone. I am Hira Fatma. I am affiliated with University of Karachi and I work with International Astronomical Union, Office of Astronomy for Education as National Astronomy Education Coordinator for Pakistan. I'm one of the radio representatives for Pakistan and I'm looking forward to meeting you today with your projects. Thank you.
Thank you very much. Faisal?
Hello everyone, and I am Syed Faisal Rahman, and I am based in Pakistan. And I'll be discussing some Python with you. And I'm also part of Pakistan team for radio astronomy. I'm affiliated with Lahore University of Management Sciences and NCBC at NAD University. Thank you.
Thank you very much. Hongming?
Hi. Hello, I'm Hongming. I'm based in China. I'm now a assistant professor at the Xi'an Jiaotong Liverpool University, weird, but the China UK co-founder university. I'm also co-leading the Radio Galaxy Zoo email with Eleni. And today I may share some of the backbone knowledge about citizen science with you. Thank you.
That's fantastic. I will also introduce myself. I'm Eleni Vardilaki. I'm an astrophysicist at the National Observatory of Athens, the Institute for Astronomy, and I'm the chair for the National Astronomy Education Coordinators in Greece. And just to announce that in a while, we're going to have a node for Greece for the Office of Astronomy of Education, which we're very excited about, so we can continue these beautiful things that we're doing here. Very nice. So we have a full day. I will start with a very short introduction on our project, RADIIO, to inspire you a bit. And so let me share my screen. So sit back and enjoy. Very nice. So, radio astronomy for development, intercultural innovation, and outreach. This is our project. It's called RADIIO in short. Very nice. What is it? It's a pilot international educational program in astrophysics and radio astronomy for students in middle school aged from 12 to 17, 18, and teachers. It was founded by the Office of Astronomy for Development of the International Astronomical Union. The main issue we wanted to mitigate was that astronomy is not on the school curriculum, which is a shame because a lot of students, actually most of the students love astronomy and their teachers too. And radio astronomy, it's a bit unknown to school students, but we changed that. Right. Our goals were to get them in contact with modern radio astronomy and research, to get them familiarized with scientific knowledge and methodology, to get the culture in contact, get the students in contact with other cultures and the teachers under the common roof of science, so we can mitigate stereotypes. This is Astronomy for Peace, and in the difficult times that we are going through, I think we should all go for this message, astronomy for peace. And of course, we wanted to provide high quality education through a jointly designed educational program. Right. RADIO is an international collaboration of astrophysicists and educators. We all started with a citizen science project, Radio Galaxy Zoo EMU. Please wait for the talk by Hongming Tang in a little bit. He will describe our beautiful citizen science project. So because we were involved in research through this project, we decided to bring radio astronomy to schools. We formed this collaboration and applied for funding. The coordinator is the Institute of Astronomy, Astrophysics, Space Applications and Remote Sensing at the National Observatory of Athens, along with the Pakistani Science Society and the Xiantong Liverpool University in China. Okay, very nice. The management team, we already introduced ourselves. You can see here our credentials. Very nice. We have very strong teams behind us that supported us all this time, and we're very grateful to them. In Greece, the instructors who performed the online seminars along with me were Alexandros Chiotelis, also an astrophysicist at the National Observatory of Athens, and Yannis Dakanalis, also an astrophysicist at the National Observatory of Athens. Of course, we had consultants on education. The Greek team was composed of professors in neurology, educational psychology, and educational psychology, yes, and radio astronomy experts. Very nice. The Pakistani team was very strong. They performed a lot of seminars and visits in schools. We will describe them shortly. And a very good, strong Chinese team that performed this program, and we are very grateful for their efforts. Very nice. So, the project deliverables. Of course, we wanted to bring astronomy to schools, and the first deliverable was online astronomy seminars. From the local radio teams, we did introduction to astronomy, to radio astronomy, and to citizen science. We urged them to participate in the citizen science projects, and in particular in Radio Galaxy Zoo EMU, and we gave them examples of data analysis. For us, it was very important for the students and the teachers to learn through hands-on experience. So we suggested research topics with Aladdin, Stellarium, how to build a simple radio antenna from cheap material. We gave them Jupyter notebooks to explore data analysis, and we were also interested in their connection to nature. Very important, the intercultural exchange. A lot of schools asked us to interact with each other between the three countries. And of course, what we're doing today is the intercultural exchange. We bring everyone together so they can discuss about science. And we did visits to schools in cities and in villages. And also we had schools visiting us in our local facilities. In Greece, we had 2 rounds of online seminars. We had more than 2,000 students and teachers from all over Greece and from Cyprus, and we are very grateful for their attendance. Very nice. We performed the online seminars. We visited 25 schools where we gave talks, and we did solar observations with a solar telescope, but also a detection with a radio antenna at 10 gigahertz, which we constructed because of this program. We participated in conferences and outreach events like Astro Edu and the Astro for Development Full Moon Mashup series. We did numerous outreach events like the Researchers' Night in 2025, And of course, radio astronomy workshops and antenna operations and summer schools. Here you can see some of the visits, and the kids, the students that took part also made their own radio antennas and detected signals from all around us. And just a few statistics, we're very happy about that, because during the program, we see understanding improvement in astronomy, and the comprehension also has increased. So we conclude that the results indicate strong conceptual consolidation of radio astronomy. So students received well our project and understood what we were discussing about, and they were inspired to do assignments. So for us, this is a win. Let's go to Pakistan. In Pakistan, there was participation from 13 schools from Karachi and Lahore at the end of 2025 with online seminars discussing astronomy, radio astronomy, and astrophysics in general. And they also performed surveys, which are very encouraging. We see successfully that students were strengthened during these programs. They understand the concepts, and we are very grateful for that. This gives us, this helps us continue for the future programs that we are planning. Very nice. And Pakistan didn't stop there. They had a bilingual approach for accessibility, which is very important, in Urdu and English. They performed online workshops in January and March on radio astronomy and Python for astronomy. So how do we analyze the data? Okay, we get the data from the telescopes, but how do we play with the data and how we interpret them? And they also gave assignments which students performed successfully. But it hasn't finished here. On the 28th and 29th of March, there are 2 more workshops, and this will close the radio project. They also visited the theory schooling system in Karachi and did a demonstration of the radio antenna operation. You can see here. The kids are very excited about this. We're very grateful for this participation. Let's go to China. A very strong team, including a lot of students and giving them assignments, inspiring them. So on the left, we have a painted poster by students in the Shanghai Northern America International School. In the middle, we have the radio antenna designed by Dr. Hun Yanggu and Dr. Quan Guo, and the students that took part. And on the right, the teacher training program, because as I mentioned earlier, our goal was not only to educate students, but also teachers so they can bring radio astronomy to the schools in their own pace and in their own curriculum. Very nice. And school visits, of course. The Chinese team visited schools, and one of the amazing activities was to reconstruct a model of the fast radio telescope, which you can see here on the bottom left. I would love to do that myself, to be honest. I'm a bit jealous. And of course, they talked about astronomy and astrophysics. And they had also visits from schools in the Shanghai Astronomy Museum, as you can see here. Very nice. A big collection of pictures. There are many more. There are many schools that took part. We are very grateful for all their effort, and this gives us the will to continue forward. Very nice. Let's summarize. So RADIIO, a pilot international educational program, provides quality education through a jointly designed international program. Theoretical, but also practical. This was very important for us. Actually, on the right, you can see the radio antenna that visited all the Greek schools. Very nice. And detected solar radiation at 10 gigahertz with a simple satellite finder, actually. Very nice. So what did we wanted to mitigate? That astronomy is not on the school curriculum in either of our countries. We believe that by bringing these outreach programs, educational programs to the schools, we can create the right conditions so we change this situation and astronomy becomes part of the school curriculum. Because students and teachers really love astronomy and science. So we can say that 50% from our studies, from the quizzes we gave to the students and the teachers, we can say that 50% have a basic idea of what radio astronomy is after taking part in our seminars. And they welcomed our pilot program and took part online and in person. We had 30 schools in Greece, 25 in Pakistan, and 6 in China that did additional projects. And most of them selected the radio antenna, citizen science, programming, making the fast wooden models, assignments with Stellarium and Aladdin, which we will see in the presentation of Hira Fatima. But they also created their own board games. So we will see a couple of Greek teams that will present astronomy board games. And today we have 27 schools from Greece, 1 from Pakistan and 1 from China presenting their assignments. There were a lot of challenges. We had different school years, we had wars, we had different national holidays, but we mitigated these problems with our methodology, a commonly designed curriculum. We adopted it to local needs, and we got advice from educators within our local teams, so we can design the best possible program. Very nice. Our target is for radio to become a standard in astronomy education worldwide. So we are seeking and applying for long-term funding to bring you radio astronomy and get you involved with this beautiful science. So thank you very much. I will stop here and we will move on to Hongming Tan for his presentation.
Hello.
Hello.
And before I give the presentation, please allow me to add a comment on the China side that on the later, I think from next week, from 11 March next week, just at the location of FAST, we will have multiple on-site workshops near the FAST telescope to teach our county school students how to build a radio antenna.
Wow. Yes, that's amazing. That's amazing.
Yep.
Thank you very much.
So can I share the?
Yes, please go ahead and share.
Okay. So let's start with the slides. Can you see it?
Yes.
Okay, so I may make it full screen.
Mhm.
Yep. Okay.
Very
So
good.
perfect. Thank you, Eleni, again. And hello, everyone. So in today's, I would like to share you our citizen science project, Radio Galaxy Zoo Emu, that Eleni kindly mentioned beforehand. And because this is I think it's a workshop, I hope that you are not only have a rough idea of our project, but also learn how to build one by yourself. So in the future, when you have an idea that you may think, oh, I could have some others help, or let's do something interesting together. This becomes a tool by your hand. So in the second half of this talk, we may mention how to build your own project, a simple one. Okay, so let's start. So basically, this talk I will cover 4 little segments. One is our motivation, why we hunt supermassive black holes, and which is why we set up this project. And secondly, we may mention what Radio Galaxy Zoo Emu is like. So we may provide you the actual interfaces that as a volunteer to access with on the web base. Thirdly, after knowing the RGZ-EMU project, we may move on to the general strategy, or let's say the philosophy behind building up a project on your own. And I will introduce you the Zooniverse platform that really is almost zero coding. And even if coding, it will be super easy ones, and you have examples. And I would introduce how can you build one little toy project by yourself, but actually it has scientifically meaningful purposes, which I call pulsar profile analysis, okay, as an example. And we will run through that step by step. So let's start from our project. Our project starts in the radio wave band. When we talk about radio wave band, we usually hear it. What I'm saying hearing is about you may hear FM, you may use Wi-Fi in your home, or you may watch televisions, and all of these are in a radio wave band. But what if we use the radio telescope, say, to observe our Milky Way? So from here, you can see our sun now behaves like this, and close away from the center of our Milky Way, you may see this little portion that includes a protoplanetary disk. This is actually observed by ALMA telescope array in Chile. If you move on to the center, you can see that in the center, the innermost center of our Milky Way, there exists a really, really tiny object in volume, but really massive object, which we call black hole, or more specifically, we call it supermassive black hole, because it lives in our Milky Way. Actually, our one of our astronomers named it as Sag A, okay, Sagittarius A star, which gives it a very particular name for our supermassive black hole in the Milky Way. Oh, sorry. If you move to the right a little bit, still in the Milky Way, there's another species, actually a species of stars called pulsars. They are actually neutron stars, which is a stars made of all by neutrons. But why we call them pulsars is because you can see the animation that it's just like a cosmic lighthouse that when it rotates, it has an axis that with the strongest emissions point towards flowing and backwards. So basically you see the emission become stronger and lighter, and then it becomes quiet. And after some time, it becomes bright again and diminish again. So from periods to periods that you see it. So this is called pulsar because we believe it's pulsating. If you move even to the right, there is one kind of objects called supernova remnants. Also, you can observe it on the radio wave band. And of course, those planets, we also able to do it. Due to the time limit, I will just skip them. But please be aware, in the radio wave band, we can not only listen, but we can actually see, of course, with some techniques. And we can use the radio waveband to study our sun, protoplanetary disks, supermassive black holes, pulsars, or even more. So that's the importance and the interest part about radio. So let's go back to our interest part, the supermassive black holes. With some other telescopes that aim to survey the much larger field of view, much larger sky, we're actually not looking at black hole itself, but we are looking at its effect. In fact, if you look at it very, very far away, you cannot see the black hole easily, but it is located in a galaxy, which I'm pointing here. The galaxies, due to the activity of the supermassive black hole, will beam relativistic jets. You can see it as very energetic charged particles to a very far away distance. which we call intergalactic medium. It will beam the jets to intergalactic medium, and due to its emission mechanisms, we can actually observe it in the radio waveband. And that's where we can backtrack the location of the supermassive black hole by looking at the radio emission. Of course, to locate the host galaxies, we need also the optical waveband and the infrared waveband that we can together locate the potential location of the supermassive black hole. And that's our target. To be honest, if with only little sample, we could do sometimes, let's say, in ourselves. But the problem is, in real practice, we found out that for our evolutionary map of the universe project, we probably will actually discover 20 million of them. And experts is never enough. Also, if we apply those conventional methods, we still have 2 million left, which means that we need your help. We need to have your knowledge to work with us. So that's the reason why we call citizen science, because we, as general citizens, can join science research activities and we can work together. Of course, as I said, when doing the citizen science, 2 million is still too much, so we may combine the use of AI. But please live with that. Basically, AI plus citizen science will be a friend of hunting supermassive black hole. Now, what the citizen science project is about. In actual practice, actually, we have a web page. We will show you later. And on this web page, we ask you to look at images to mark the host galaxy of the supermassive black hole, and also to identify the radio emission region of the source. We call it source, which represents the radio emission regions. Also, moreover, because the radio emissions have different morphology, which may represent either its source nature or its interaction with the outskirts environment. Hence, we also provide about 10 tags, we call them tags, to identify the radio morphology of a radio galaxy. And finally, if you are interested, please feel free to discuss with us on the talk board, which I will show you. And this is a place where we can chat on particular subjects, or you can raise your questions to us and we may answer your timely. So now please allow me to switch and share with you the actual project. Okay. Okay, let me check. So, okay, can you see it? Okay, so sorry about that. Okay, so for here you can see this is the main web page of the Radio Galaxy Zoo EMU. If you would not like to use English, please feel free. We have multiple language versions, so please find your own language. If you cannot find your native language, please contact us, and we might find translators to do another version for you. Okay, so whenever you log in to this page, you can actually click this EMU Zoo all-in-one button, which will guide you to the main workflow that we ask you to, or any volunteer to work on it. So on this main page, you can see an image which divided into 3x3 panel. On the upper panel, we show you the radial data, and in the middle, optical data, and on the bottom, the infrared data. So from left to right, we show you different field of view. Left is zoom in, and then in the middle is the default view, larger, and then to the right, even larger. We call them zoom out view. Okay. So this main workflow has two steps. The step one, actually, we have three functionalities here. Step one is called draw total source box, which asks you perhaps to identify the radio emission regions. Let's do it this way. So you have a box, and to include all the necessary radio emission of a radio galaxies that you believe. Secondly, we ask you to mark host galaxies. Let's say let's randomly pick this one. Let's say this infrared source is the host galaxies we believed, because you need a host galaxies to beam jet bilateral. So we see a bilateral structure here, and this is a infrared galaxies in the middle. So we believe that's the potential source. Sorry. Afterwards, if you find any other radio emission that you don't believe as the part of the source, you can actually try to kick it out by drawing a purple box. Okay, so this is the main step of identifying a radio galaxy, and also to locate the potential supermassive black hole location, which in here means the location of the host galaxy. Okay, but wait, we still have a second step. The second step asks you to identify the radial morphology of it. Okay, so here I see it's roughly it has a bridge which connects the two lobes. You can see the jets, and of course, it's more or less an hourglass shape, though not perfect. But for consciousness, I'm not doing this time. Okay, so basically, you can tag multiple tags here to identify the radial morphology of a radio galaxies. If you think this is a special source, actually you can click the done and talk button. If you find, nah, I'm good with that, then you can do done, okay? And that will move you to the next source. Now, if we click the done and talk button, it will guide you to another page, which will allows you to comment on this particular radio galaxies. You can see the image now is much bigger, which allows you to look at it closer and perhaps discuss with other people. And you can see actually there was one of our volunteers commenting interesting. So of course you can leave your own comments here. Say, I agree. Let's say it this way. Okay. So, and you can add your comment, and afterwards, yeah, you see your comments. Okay. So you can see your comments, and that's the start of a chat. Okay. So basically, this is the general workflow. For our scientists, after we collect enough number of classifications, we would export the data for our later analysis, which I hope some of our speakers will cover that later today. And I think Faisal will teach you maybe not this data, but some others data analysis using Python, which you can anticipate today. So that's Radio Galaxy Zoo Emu. Please feel free to have a play to get familiar with, and we will push up new data very soon. Okay. So for this is the RGZ Emu part. Okay. But what is the second half? The second half will tell you actually how to. Sorry, can I? Okay. So the second half will tell you how to build one. Okay, so the platform I just showed you is called Zooniverse. Zooniverse is the world's largest and most popular platform for people powers research. And please feel free to Google it, and it's really straightforward. You can even access it on your phone. Basically, Zooniverse research can only becomes possible by volunteers, which means over 2 million people on the internet around the world, and they all come together to assist professional researchers. So these yields not only astronomy, but also biology, social science, history, subjects you can imagine. So basically, because of the vast needs of doing popularity research, you can actually see, even only consider astronomy related projects, we have this many, and we have more upcoming. And because the vast needs of both researchers and volunteers, Zooniverse actually provide a low coding platform for builders to build their own projects, which could be you. So here I'm showing you one examples I recently developed myself, private research only, and only I think 5-6 of us are using these toy projects, but doing real science. So this project, I called it pulsar pattern analysis, which you will see it later, is what we are actually working on right now. I actually just received the data early this morning. So before I actually show you the data, please allow me to describe how a project is built in the first place. Any citizen science projects needs a goal. So actually, if you ask Eleni and me, and Hila and Faisal, we spent months to set up our clear scientific goals in the first place. And the reason for that is goals always matters. After you have a goal, data becomes a constraint. So we need to get the data we need and process it so all volunteers can work on it. Thirdly, when we have goals, we have images, we know what we do. So Zooniverse becomes your friend, and you can design your own workflow on Zooniverse. You can input data to it, write your text, and export data when you have enough classifications. And fourth, when you have the data by hand, I mean the labeled ones or the classified ones, science will just comes out. And that's the moment we have our research outcome. Okay, so let's start. For short, as you might have seen the animation, this is a normal pulsar pulse profile if you look at the lower half of the animation. In usual cases, you can see the blue arrows there. Most normal pulsar pulses actually arrives to the Earth at the same time. And hence, in most of the normal pulsars, you see that the x-axis of the right figure, that the brightest pulse, if you look at them on the y-axis, if it is a normal pulsar, it will always be the same. So it will be roughly here. But as you see, in regions such as the green boxes, the brightest pulse actually shifted to the right. And the mechanism of such kind of shifts is yet to be well understood. Which means if we can have enough samples of this shifted pulse, we may be able to find the underlying pattern, and we may uncover the mystery of how these, what we call shift modes, take place. Perhaps the pulsar changed its rotation axis. Perhaps it was it actually has multiple stable motion mode. These are all possible. But to know which one is correct, we need to know shift and non-shifted at the first place. So this is the scientific target. Now, the reason why we could do this project is we got the data. So luckily enough, we have a good team here in China who actually acquired more than 10 times of FAST proposals, observed over 100 hours, and got the data like this. So here you see that we have actually cut the data into chunks and convert them to images like this, so we can actually upload them to the Zooniverse and make a project. Now, let's go back to Zooniverse and make a project like this. Okay, Ellen, are you with me on this?
I am with you. We can see your screen. Go ahead. Thanks.
Okay, thank you. So now let's go to the segments that a user will not see, but a builder will see. So if you click, let's do it this way. If you build a project, you need to log in first, and then there's a button on the top that called Build a Project. If you log in, these will be the projects you can see only by yourself. Okay, and now we use this example. Sorry, I also have a project called Coffee Counter, which counts the coffee beans. Okay, so basically here's a pulsar profile analysis. When you click it, you enter the builder panel. Okay, so to start with, always start with this main page, and you can upload your own avatar, which is a GPT generated image. And then you can name it. You can name, let's say, pulsar profile analysis. Okay. Afterwards, try to type some description so your helper will know what you're doing. Okay. Of course, you can add content by yourself. This is all optional. If you want to spread your projects, you can actually type your linked projects web page, or even, I think, mobile app page to here. Okay, so people would know you whenever there's an update. Okay. The first thing is we need to import data. So please go down to the subject set regions. In here, you can actually create a new subject set. Let's do in this way. Let's try to name it as radio test set. Okay. And afterwards, we need to upload images. So for here, I use only one. Let me do it this way. Okay, let me find an object randomly. I could, sorry, that may take some minutes to 1 minute to find. And okay, I got my data. Okay, so 2019. Okay, so I have, let's say, one single image. You just need to drag it. You can see the PNG name now, and you can drag it to here. So it tells you that one subject image is ready to load, and then click the upload button. Spend some time because we need to do data transport. We now have the data in the subject set. So when you look at it, I'm not sure if the figure is too big, but basically you can see it here. Okay. Or we can see it sometime later on a workflow. Okay. Oops, sorry about that. Yep, and by the way, you can see the metadata here. Okay. Let me refresh it so you can keep going. Okay. So basically the subject set is here, and I'm gonna just close it and we will see it later. Okay. And that's the data. You will see it on the main workflow, by the way. With the data, we're now able to design a workflow. Okay. So let's say we want to design a new workflow. Okay. Radio test workflow. Yeah. And afterwards, you enter this page called the workflow designation page. Okay. To do that, we actually have multiple tools, which we call task here. Say question, drawing, text, and survey. You can see all these functionalities. For these projects, we choose drawing because we need boxes. So now let's barely say draw a box. Okay, draw a box. That's a main step, and blah blah blah. Okay, for help text, well, you don't need this essentially, but you can actually do it. Of course, we just type this untitled subject set, which is the subject set we just created. And then the actual thing we are doing is we now add the tools for volunteers to draw boxes. Okay, so let's say shift. And you can choose the type. It can be points, it can be rectangles, it can be, let's say, circles, etc. And let's define it as a green one. Okay. And of course, only shift is boring. We also want to do some others, let's say non-shift. Okay. But non-shift includes many, many things, right? So in this case, let's say we also do rectangle, but let's say in magenta color this time, because we want to know more information after you draw this box, you can click subtasks. And in subtasks, we also have several sub-functionalities. One is called text, which enables you to enter instructions. So let's say try to tag the mode you believes the region belongs to. Okay, and then we say add, and we close it. Okay, and we set it as a required task if you do this, and then we close it. Now we have finished a very quick version of the workflow designation. Okay, but how do we know if that's correct or not? You can simply test the workflow. And this is where we test if we have done things right or wrong. Now let's try. This is basically a trial version of the project that helps you to check it. Now you see the picture. This is the picture we just uploaded, okay? And you can actually zoom in or zoom out. You can use this move subject tool to move it in the panel. You can rotate it, and you can set back to the original. So now, what if we want to do shifts? You can zoom in and using the green box to draw it. Oh, sorry, back. Okay, and then you can draw it. Okay, you can draw a green box. And what about a non-shift ones? Let's say in this way. If we have a non-shift ones, let's draw a magneto box, and it automatically asks you to type something. For me, I'm no expert at all, so I just type I don't know. I don't know, and you can save and close it. Afterwards, if we click done, then this is done. Okay, due to only one subject set, so you will see you have finished everything. Okay, so congratulations. Now you have done your very first demo project. Please feel free to explore more, and Zooniverse actually have provided you many examples and tutorials how to build one. If you build a more or less comprehensive one, like the RGZ EMU, you may find that we provided what's called a field guided to help our volunteers, saying that what situations volunteers will meet, any interesting objects they're in. We also have put those contents in. When users get lost, you can make use of the tutorial functionalities, which will guide you through the necessary steps of the workflow. Of course, you can try out to see the about page, okay, to learn the background information, which everything you can type in. You can do, say, research. You can know our team members like Eleni here. And of course, our scientific results, frequently asked questions, and our education effort. So these are all up to you to develop. So I would say Zooniverse is a platform that you can use your creativity and your knowledge to build many interesting stuff. In fact, if you look at the Zooniverse, you can see there are a whole bunch of different categories that researchers are working on, and you don't have to make it public. You can do private. And I cannot wait how you come up with this and and show me your research outcomes. So thank you so much and wish you enjoy.
Thank you very much, Hongming. I hope we inspired people to also use our project, but also to build their own project, and then they should contact us and we will join.
Yes, yes.
I mean, you inspired me to make a coffee maker.
Yes, please try.
That is amazing. That's fantastic. We have a few people from Greece that joined our Zoom call. Good morning to them and good morning to everyone who is on YouTube. If you have questions, please type them on the YouTube chat and we will ask them. At the moment, there are no questions. I don't know if there are questions from Zoom. Please type them and we will ask Hongming, but let's take a breath. Okay, 2 minutes. Let me see the schedule. I think we are very good when it comes to time. Let's see here. Right. Yes. So the next item on the agenda, it's the Shanghai Northern America International School. So this is the time for their presentation. So Hongming, please update us a bit about that.
Okay, so for sure that we inform the very talented and young lady to join us at 4 local time. So we may still have several minutes left, but please allow me to briefly introduce this school. This school is actually led by, so the astro activity of this school is led by Miss Yuan Sui, who I really appreciated that she led the village national rural school astro course teaching in last year. Actually, she was the one that gave the lecture. And also she led the translation of the Astro game that Eleni, you contact me. So students from this school particularly have been worked really hard to do the translation. Besides, they are actually a really active group locally to organize astro activities and doing outreach, etc. and etc. And I have seen some of their students, really, really lovely kids. So for the upcoming talk, they may cover some representatives' activities they perform because they only have one speaker. And so basically you would anticipate it's a summary of their recent radio-related activities. I have seen some photos you have mentioned, which comes from these schools.
Yes, yes.
And unfortunately, in China, our English level is really various or diverse, if you name it. But for this school kids, I would say they're brave. Okay, they're brave enough to present. So please encourage them, encourage her, I would say, when she's get online. Um,
Absolutely,
and
of course.
yeah.
And thank you for reminding me that they collaborated with a Greek school for the translation of the board game. That's fantastic. I'm very glad it worked out because I understand it's very hard also to do these connections. We are very grateful for all the effort they put in. Let me check if we have any questions online. Come on, people, ask questions. No, we don't have questions. They understood everything you said about how to make their own citizen science project. And just to say that it is very important to actually reiterate what you said, that it's very important to have citizen science projects because in the era of big data, it's not possible to write algorithms to analyze this data without having the input from humans. We are not there yet, let's say. Maybe the algorithms of the future will be trained well enough to understand like a human does, but at the moment they're not. So it's very important that we analyze data using our eyes, right? And we train the algorithms to do this in millions of subjects. Absolutely. Let me see now. Where are we at?
Okay.
Yes.
I think she's joining. She just messaged me that
great.
she's joining. Yeah.
That is fantastic. And just to say that when we organized this workshop, we took into account the different time zones. We wanted to bring everyone together, and we want people to understand that so China now is in the afternoon. The day is almost over, and we're very grateful for them joining at this late time. Pakistan is a little bit in the middle, and then for Greece, it's early morning. And this was the only way we could all be together at a similar time to interact in this platform that we made for you. Since we're waiting a bit for the student to join, maybe the ones that are on Zoom, they would like to say good morning. We have some schools, some Greek schools online. Please unmute and to say hello, if you would like to.
Good morning from Miraculum. Hello.
Good morning. Very nice to have you from Miraculum. We're glad that everyone from Greece is here, and from Pakistan and from China. So, let's see. Please check Hongming if the student had joined. And whoever else wants to say hello, please do, and tell us which school you're joining from. Very nice. Good morning from the third gymnasium of Polychny. Good morning to everyone. We are looking forward to your presentation later in the afternoon. So, Sophia has joined, right?
I think Sophia is the speaker.
Yes.
Okay. Good afternoon, Sophia.
Can you hear Sophia?
Good afternoon.
Good afternoon. Hello.
I think I'm going to. Yeah, I can.
Okay, you can hear us, right?
Yeah, I can. I'm
Okay.
sharing the PPT.
Okay, please share your screen.
Nice to see you.
Okay. Wait. So, um, wait, so now you can see my screen, right?
We can see your screen, yes.
Yes.
Okay, so I like to open it.
Yes. Take your
Sorry, it's
time.
the first time I use this app, Zoom, so I'm not quite familiar with it.
It's no problem. Take your time.
For wasting your time.
Yes, it's okay. While we wait, Hongming, there is a question for you.
Yes.
So, about the data you upload in a new project in Zooniverse, are the data only images, or can you upload other types of data?
So as far as I know, what I saw most cases are images. Of course, you can upload videos. So videos and images are both okay. But let's say if you're uploading documents, then I'm not quite sure about that. But I'm sure videos is also good. Audio, you may want to explore yourself, but I never see a project work on that on Zooniverse. Yeah, please feel free to have a play with it. And if you find that you want to upload audio or you want to upload documents that is yet to be available, my suggestion is please contact Zooniverse. They're really responsive and they also are happy to have new functionalities that may under development. And you may be the first one to try.
Yeah, no, that's fantastic. Great. Yes, we also asked for a few functionalities in our time because we wanted to make our project more efficient. So yeah, go ahead. We have the presentation on. I am very excited for this. So Sophia, we will stop talking and the floor is yours. Thank you.
Okay, thank you. Hello, everyone. My name is Sophia Wang, and I'm a member of the Astronomy Club at Shanghai North American International School. Today, I'm very happy to share our project called Chasing Dreams with Radio. Our astronomy club has always believed that astronomy should not only be something we read about in textbooks. So it should also be something we explore, build, and share with others. So today, I will briefly introduce what our club usually does and then talk about how the radio project helped us take our exploration a step further. Well, in our astronomy club, we try to combine learning and hands-on exploration. Of course, we start with learning some basic astronomical theories and concepts, but more importantly, we also organize observational and practical activities so students can actually experience astronomy. Sometimes we also have fun activities like astronomy games or watching science movies together, and these activities help make astronomy more interesting and accessible for everyone in the club. Besides, learning within the club, we also like to share astronomy with the rest of the school. For example, during our school's club fair, we set up a booth to present what we have learned. We show research results, explain astronomical topics, and display the boards made by our members. We also introduce some astronomy equipment, such as optical telescopes and simple radio astronomy devices. Through these activities, we hope more students can discover how fascinating astronomy is. Another thing we often do is create astronomy posters. Posters are a simple and low-cost way to present scientific ideas. So through diagrams, pictures, and short explanations, we can explain complex concepts in a clearer way. Designing posters also help us practice an important skill, which is how to communicate science clearly to others. So these are some of the general activities in our astronomy club. Now I would like to talk about something more special, our work with the radio project. The radio project gave us a chance to experience astronomy in a completely new way. First, we tried to build a low-cost radio telescope using simple materials. Like during the process, we learned how radio telescopes work and how radio signals from space can be detected. This was exciting for us because it showed that even students can build meaningful scientific experiments with limited resources. And secondly, we organized our work into poster presentations so we could clearly explain our process and what we learned. Another important part was sharing the radio project with students in rural areas. We visited rural schools and introduced experiment and the ideas behind radio astronomy. Our goal was simple, to let more students know that science exploration is something anyone can participate in. Finally, we also helped localize some radio astronomy games into Chinese so that more students could easily understand and enjoy them. So through all these activities, the radio project connected learning, experimentation, and science outreach. For us, it was not only about studying astronomy, it was also about sharing curiosity and inspiring others. And this is what we meant by chasing dreams with radio. Wait. So I think this is the end of the presentation. To conclude, the NI's Astronomy Club hopes to create opportunities for students to explore science activity and share it with others. And the radio project helped us turn our curiosity about the universe into hands-on experiments and real outreach activities. We believe astronomy is not only about distant stars, but also about curiosity, creativity, and collaboration. And thank you very much.
That is fantastic. Thank you very much. We're really glad to see the great effort you put into the project and also that you got inspired from it. That was our purpose in the beginning. Hongming, would you like to say some words?
Yeah, I'm totally fascinated. To be honest, I'm totally fascinated. And I was not expected that you have mentioned that you go to the rural schools and actually give them lectures. Well, I heard from Sui, but I never realized that's been happened, but not a plan. So I'm really excited about this, and great job, by the way, great job. And yeah.
That's fantastic. Can you tell us a few of your like best moments of this experience? Would you like to share with us what made you an impression when visiting schools, for example?
Well, visiting the schools, you mean? So you want me to share some experience to go through the experience about visiting the rural schools? Well, actually, our team did do that before, but it was not me. It was a few other members, and I was at school, like taking the exam that time, so I didn't have time to go there. So if you want to hear stories about the rural schools, I think maybe next time our other members would come to here and introduce it to you. Sorry.
No, that's not a problem. That's not a problem. Thank you. Right. Let's see if there are any questions online. Guys, if you have questions online, please share them with us. We are happy to get involved and interact. We have very nice comments here on Zoom. Great work. Congratulations to you and your school. And we're very proud of you. Thank you for spreading the radio project around. That was the whole idea about the project, to be able to inspire people. And what you mentioned about building a low-cost antenna that is also easy to build by students, that was our initial goal. We're very, very, very happy this was materialized. Very nice. Let's see the project. So thank you, Sophia. We won't hold you anymore unless you would like to share something more with us. You're more than welcome to. We have quite a lot of time for questions until the next talk. So we have around 20 minutes until Hira's talk. We can open up the question section. So please feel free to share questions about radio astronomy, our project, radio antennas, citizen science, how to get involved with radio astronomers. Maybe we can discuss this, Hongming, since we are already doing that. Maybe you would like to share how someone can contact a professional scientist and become a citizen scientist, for example, or join a science team.
Yes, actually, on the Zooniverse webpage for any of the project, if you go to the About page, or if you scroll down to the main page, you can actually see. Let me share. So let me check if I have the. Okay. So this is the general one, but let's say if I do let's type our projects, okay? Radio Galaxy, Radio Galaxy Zoo, and let's try paused one because we are still having supplementary data. So yeah, please feel free when you have this explore project. Let's click the about page or for info. Okay, so the info, if you scroll down and didn't find necessary information, please go to the team page if you would like to. So in the team page, you can see that I'm not sure if I have. Yes. So for me, I have put, and I think for Eleni too, we have our personal web page. So you can contact us via our personal page. Of course, if you, like us, have the main page written in additional information. Sorry, I should update my email address here. But basically, you can see we have email address here. So for any projects page that with an email address, please feel free to contact. Moreover, for some projects also like us, we have Twitter or X if you like to. And occasionally, or well, in low rate, but we will check from time to time. You can access it through social media. And if the social media is active, they should respond to you. So that's one thing. However, if you're thinking of the most frequent or most active board, we have this talk board. So on the talk board, let's wait for 1 sec. So you can see that there is a board called Questions for the Research Team. So here you can leave your own message to us, especially if you have some idea, if you have some particular source you wanted to check with us. And to be honest, this is usually where our discussions start. And as long as the discussions moves on, we may recognize your capability, we may recognize your passion, and then we may start something. In fact, our previous super zooters, we call them super zooters, some of them did show us their interest in involving the projects in more depth. So we had one papers published along with roughly 10, 15 volunteers as co-authors. And that's the result of co-working. But other than that, if you want to reach out to professionals without citizen science, I would encourage you to check the nearby astronomers. For instance, in Greece, please reach out to Eleni. And in Pakistan, please, Hila and Faisal. So they may be the one who knows who you should contact with for your interested subjects.
Yes.
For me, for instance, some of my students, they're not interested in galaxy, but they're really a fan of what's called intermediate mass black hole. So the young lady, she was studying financial math, actually. One day she knocked at my office and was asking, can you guide me to find someone who actually know this thing? So in the later half of this year, she will go to Beijing for her intern and actually study the intermediate mass supermassive black hole with a faculty there. So we are happy to help out if you don't know who to ask.
That's great. Yes, thank you very much. I think we could, let's see. Great. No, no questions. Right. Shall we move on? The next presentation is by Hira Fatima. Would you like to go ahead and share your presentation and we can start, and maybe we can dedicate some more time for questions later?
Okay, can you see my screen?
Yes, thank you very much.
Hello everyone, I'm Hira Fatma and I am associated with University of Karachi, Pakistan, and I have been working with International Astronomical Union, Office of Astronomy for Education, as the chair of National Astronomy Education Coordinators team for Pakistan. I'm also national coordinator for Astronomers Without Borders, and this project is a real example of Astronomy Without Borders, our project RADIIO. So I welcome you all to this international workshop. Today I will talk to you about seeing the invisible universe using multi-wavelength astronomy. And I will briefly demonstrate two astronomical tools, Stellarium and Aladdin. So this is the outline of my presentation. Today we have very limited time for this talk, so I will be touching upon these topics, these subtopics very briefly. But if you want to have some in-depth knowledge of these subtopics, you can watch our recorded lectures of our previous webinars, where you can find very in-depth knowledge of these topics, these astronomical tools. So before I start, I want to ask you a question. When you look at the sky, what do you see? Do you look at the sky or you don't have time for that? I hope you look at the sky. Okay, I do. And I guess you say stars, planets, the moon. Okay. So I would like to ask, do we see everything that exists in the universe? Do you really think we see everything that exists in the universe when we look at the sky? Well, we don't see everything that exists in the universe. But why? We want to see everything that exists, but we can't. Why? Because our eyes only see a very small part of electromagnetic spectrum. Yes, human eyes detect only visible light. So you can see that all these electromagnetic spectrum that is available, we can see only a very small part of it, which is known as visible light. And because we can see it, we call it visible. But the universe emits many kinds of light, and we really want to see all of them because we want to explore the universe as much as possible. So here you see the electromagnetic spectrum, and you can see that we have a whole range of radiations, and you say the complete set of these radiation as electromagnetic spectrum. If you see on one end, you find gamma rays. On the other hand, you see radio waves. And what is the difference between these waves? The difference of wavelength. You see here you find the short wavelength in gamma rays and very long wavelength in radio waves. And this difference in wavelength makes everything different. For example, these gamma rays, which have short wavelength, have high frequency and high energy. On the other hand, these radio wavelength, which have long wavelength, have low frequency and low energy. And why this thing matters? This thing matters because different wavelengths reveal different secrets of our universe. But the problem is that our viewing capability, our viewing ability is only confined to this narrow region known as visible light. It means if we somehow manage to see the other parts of the spectrum, we can reveal the secrets of this universe. So let's try to see the other parts of this spectrum. So now we do astronomy at different wavelengths. And if we observe different celestial objects at different wavelengths, we call it multi-wavelength astronomy. Because now astronomy is not only confined to optical region or the visible part of the spectrum, but we also do astronomy at different wavelengths. If we observe one celestial object in different wavelength, we call it multi-wavelength astronomy. For example, you can see I'm showing you Crab Nebula at different wavelengths. So I can say that I am doing multi-wavelength astronomy. But if I am observing a celestial object at a specific wavelength, for example, at radio wavelength, so I can say that I'm doing radio astronomy. If I'm observing at optical wavelength, I can say I am doing optical astronomy. But why it is important to do astronomy at different wavelengths? As I mentioned earlier, that if you do astronomy at different wavelengths, you can reveal the secrets of this universe. If you do a radio astronomy, you can study cold gas, you can study pulsars, radio galaxies, and cosmic microwave background, which is Big Bang remnant radiation. On the other hand, if we observe, if we do optical astronomy, you can see totally different things. For example, you can see stars, planets, galaxies, invisible light, and this is what you are very used to see in your books, in your science books, especially at a school level. And if you move forward to infrared astronomy, you can see that cool objects like dust clouds, the nebula, the nurseries where stars are born. So you can see the star forming regions, you can see exoplanets. And if you do ultraviolet astronomy, you can see young stars. The young stars, very hot stars, you can study interstellar medium, which is the medium between the stars. And you can study the galaxy evolution. We know that the galaxies are formed, they evolve. So you can study the evolution of galaxy in ultraviolet. And if you want to study very extreme events, very energetic events of the universe, for example, supernova, so you can study that in X-rays and gamma rays. So you can see that we have whole range of wavelengths, we have whole range of astronomical objects, and we have whole range of astronomical phenomena. To cover all these aspects, we can do multi-wavelength astronomy, or we can do astronomy at different wavelengths. Let's look at these very wonderful, stunning astronomical images. So the first image that you see is antenna galaxies. So you can see that a pair of colliding spiral galaxies. I really love this this image, and you can see that I have shown you this image in from three different telescopes, right? And as we move forward, you see M82 galaxy, you see galaxy cluster, Abell galaxy cluster, you see supernova remnant, you see Eta Carina, which is a binary star system, which is expected to go supernova very soon. And then you see this card galaxy, in which you see a small object is stuck in this larger object, and this very beautiful helix nebula. And then we see Crab Nebula, yes, in different wavelengths. It's a very special nebula. You can see the nebula as well as a pulsar inside it. So we will talk about these objects a little bit later, and in some of these objects in Alini's talk. So let's move forward. So I have shown you very beautiful, stunning astronomical images, but how do we get these images? This is a question we all think about. So if we have telescope, we can do observation, but to get the data, to capture some data, so that you can analyze the data later, you need some other instruments. For example, let's start with filters. So we use filters with telescopes so that we can work on certain wavelengths of light. These filters allow a certain wavelength of light to pass and block all the other wavelengths. This helps astronomers to study specific wavelengths, or you can say specific features, for example, stars, galaxies, or nebula, whatever you want to study. Filters, to make it more easy, filters are like sunglasses, or you can say colored glasses. If you wear blue glasses, you mostly see blue light like this. And after filters, we need detectors, because these detectors measure the radiation and convert it into digital data, or you can say numbers like this. You can see a grid of numbers, and then astronomers use computers to assign colors to those data, or you can say numbers, and this is how we create these images. So here you see a grayscale, a single band image. But in astronomy, you see very colorful images, and we really love to see colorful images, not grayscale images like this. So how do we get these colorful images? So here we see a natural color image. One is of hot air balloon, and the other one is astronaut. So how do we get these images? You can see that I have captured, or someone has captured this image thrice. We took 3 observations, one in red band, or you can say I used the red filter to capture an image, and then I displayed it as a grayscale image, and other in blue filter, and other in green filter. And then what I did in my computer, that I assigned I gave red color to the red band, blue color to the blue band, green color to the green band, and then I composite these images to get this natural color image. If I can do this on the objects on ground, then I can do this same technique on the objects in a space. So we applied the same techniques on Saturn to get this natural color image. But in astronomy, most of the time we see astronomical images like this. Here you see Cas A, or you can say Cassiopeia A, which is the remnant of a massive star that exploded about 300 years ago. And this is the X-ray image of expanding shell of gas produced by this explosion. So the point here is this is an X-ray image, and we cannot see X-rays. Then how is possible that I have this X-ray image and I'm showing you this X-ray image? So in astronomy, we know that we observe celestial object at multiple wavelengths, with the wavelengths that we can see and the wavelengths that we cannot see. For example, our eyes cannot see radio wave, infrared, X-rays. But the telescopes have special detectors that can detect those invisible wavelengths. And these detectors measure the radiation, convert it into digital numbers, or you can say digital data. And then astronomers use computer to assign colors to those numbers or data, creating images that we can see. And this is the example of false color image, because I have assigned colors to different numbers. There were no colors at all. There were only numbers, and I have assigned different colors to different numbers. So this is a false color image of Cas A supernova. To make it supernova remnant, or to make it more easy for you, you can think about a thermometer. We cannot see temperature itself, but the thermometer measures it and show us the numbers. Or you can think about subtitle, because this example is very relevant. Today you will be watching some presentations in Greek, and if you cannot understand Greek, it's fine, because there will be English subtitle and you will be able to understand. So this is how astronomical images translate invisible light into visible colors. So here are some more examples for you. Here you see Saturn, and you can see that this is a false color image, and I'm not using red, green, blue filter this time, but I am taking all these observations in infrared wavelength. All these observations were taken in infrared, and then I have these three grayscale images. I have given this grayscale image the red color, the blue color, the green color, and then I combine to get these false color image of Saturn. And this is another example, and you see a galaxy Messier 101, and in this image I have combined images from three different, not only wavelengths, three different telescopes. So this is how we get the colorful images that you see in your science books. Now let's talk about multi-wavelength astronomy. I have mentioned that when we study the universe, or when we study the celestial object at different wavelength, we can reveal their secrets. We can get the deeper understanding of the celestial object. So here is my favorite example. You can see Orion Nebula and 4 different wavelengths. For example, X-ray, visible, infrared, and radio. And all these images are different because they are giving you different sort of information. For example, if you see this X-ray photograph, it reveals sun-like stars, white dwarf stars, neutron stars. This one, supernova remnants in our galaxy. So, or you can say some distant quasars. But if you see this at this visible image, it shows you all type of stars at all ages, at all temperatures. So this image and this image is different. If you look at the infrared image, our view of Orion is dominated by emission from the clouds of gas and dust. I mentioned the clouds, the star nurseries where stars are born. So you are seeing the material from which new stars will born. And in the last image, in the radio image, you see the distribution of hydrogen molecules. So this is how you can see that doing multi-wavelength astronomy give you a lot more information about any astronomical object. The next example is supernova remnant, Cas A or Cassiopeia A, and let's start with X-ray. In X-ray, we see the gaseous clump of silicon, sulfur, and iron that is ejected from this exploded star. And as we all know that these heavier elements are formed during the supernova explosion. So in the X-ray image, you see this gas shell which has temperature about 50 million degrees. In visible light, the image is different. You see wispy filaments of gas at the edge of a spherical shell. In infrared image, you see thermal emission produced by dust mixed with gas in this expanding shell. And in the last one, in the radio image, you see the radio emission, which is the radiation generated by fast-moving electrons immersed in magnetic field. This is something that will be discussed in Eleni's talk as well. And the last example, now we are looking at a galaxy, and you see the multi-wavelength Whirlpool galaxy images. And as we have discussed earlier, that different wavelengths are giving you different sort of information. It's very interesting if you look at the radio image, and you can see these region of cool gas here. So these images are giving you totally different information, and you can understand much better about this galaxy using multi-wavelength astronomy. Now, we have different wavelengths and we have different telescopes, because to observe all these different wavelengths, we need different telescopes. The interesting thing is that these different telescopes are on ground as well as in space. But my question for you is, why do we send telescopes in space? Because it's much more easier to have your telescope on ground instead of putting your telescope in space. So why do we send our telescopes in space? To understand this thing, I have two examples for you. First of all, we know that our beautiful planet has an atmosphere. And this atmosphere has layers. And these layers have different temperature and densities, right? So we know about the layers of our atmosphere. Okay, so different atmospheric layers, different temperature, different densities, different composition. Okay, the next thing is that we have this graph. The electromagnetic spectrum has different wavelengths, and these different wavelengths interact with Earth's atmosphere in different ways. For example, if we look at this graph, what do you see? Here we have mentioned transparency, and here you can see the wavelengths. Let's talk about individual wavelengths. For example, if we talk about X-rays, what happens? If X-rays comes from the space, the Earth atmosphere is opaque for that. What does that mean? The X-rays will not be able to pass from Earth's atmosphere and reach to the Earth's surface, because the atmosphere is opaque for X-rays, and that is really good for us. Because of this opacity of X-rays, we survive on Earth, right? So if X-rays comes from the space, the Earth atmosphere block it, and the X-rays will not reach on the ground. Okay. If we talk about ultraviolet, we see the same pattern, that ultraviolet radiation will not reach on the ground and the Earth atmosphere will block it. Okay. If we move further, we see visible region, and we know if any wavelength come from this part, visible part of electromagnetic spectrum, it will reach on the ground. Okay. And infrared, you see opacity and you see transparency, both. Opacity and transparency both. Okay. In microwaves, what do you see? That some part of the microwave here is opaque, but some part is transparent, and some part is opaque here. So if a wavelength cannot travel through the Earth atmosphere and reach on ground, so there is no point in putting that telescope on ground. For example, if I put the X-ray telescope on ground, what happens? The X-rays traveling from space will not reach to my telescope. So if I want to take observation in X-rays, I have to put my telescope in space. To make it more clear, let's look at this figure. So you can see now we have these different wavelengths, and we have these different wavelengths, and we have Earth's atmosphere. If we talk about radio wavelength, the radio wavelength that can transmit through Earth atmosphere, we can put that radio telescope on ground because it's very easy that we can collect these radio waves with our radio telescope. But the wavelengths that cannot travel through Earth atmosphere, for that I have to put my telescope in space. And same for infrared, you can see that this telescope is on a plane because infrared radiation can come to the lower parts of the atmosphere. So I don't have to put it specifically in space, but I can put it on aeroplane, the telescope on aeroplane. And now we can see the same examples for optical. Interestingly, you see an optical telescope on ground. That makes sense because we know that visible part of the spectrum can travel through the atmosphere and we can have our telescope on ground. But you see that there is a telescope in space which is also taking some observation in optical part of the spectrum. But why? Because we can take optical observation from ground. But why do we need to put a telescope in space that is taking observation in optical? So I will tell you this thing in a moment. And now we have this example for ultraviolet, X-rays. We cannot put our X-ray telescope on ground because it will make no use for that telescope. So you can see the X-ray and gamma rays telescopes are on ground. So for optical telescopes, we know that if we have optical telescope on ground, it's fine that we can take observations. But we know that if our electromagnetic radiation is coming through the Earth atmosphere, for example, it's coming from a star. We see stars at pinpoint sources in the sky. So the light traveling from the star should come like a straight line. But as this starlight enters in the Earth atmosphere, because the Earth atmosphere is turbulent, the path of the starlight changes. It changes, and that's why we see stars as they twinkle. They are not twinkling, they seem to appear twinkling because of the path changes as it enters Earth atmosphere. So if I put my telescope here and if I capture the data, I will easily take data in optical wavelength, but my data is little bit blur. You will see stars not as pinpoint sources in images, but as a small disk. If you want high resolution data, very, very high resolution data, so you can put your optical telescopes in space. So these are few things that let you decide that what telescope do you need, because you can say that I want to study, for example, star clusters, and to study star cluster, I want to do observation in optical wavelength. And to do optical wavelength astronomy, I can put telescope on ground. But if I put my telescope in space, I will have much better data. So these are your observation targets, your goals that help you decide which type of wavelength or which type of telescope do you need for your observation. So here are some examples for you of ground-based and space telescopes. So first you see a difference between ground and space-based telescope. You know that ground-based telescopes are cheaper. You can make big telescopes for your ground. And the problem is the atmosphere distort your view, and not all the wavelengths are available on ground for observation. In space telescopes, your view is very clear and you can see all the wavelengths, but it's not very economical. It's costly, right? So here is an example. You can see a WISE space telescope, and you can have the idea of its size by this comparison. And this is infrared space telescope. Now you look at James Webb Space Telescope, and you see this wonderful image of Jupiter, which is captured in near infrared, and you see the polar lights in near infrared. We have the similar lights, auroral lights on Earth, and we see them in optical wavelength, invisible part of the spectrum. But here we see these auroral lights in near infrared. And there is another image, and it is from Hubble Space Telescope, and we are looking at Jupiter again. It's very interesting and very beautiful. Another space telescope is Spitzer Space Telescope, and we can make observation in near infrared and far infrared region with this telescope. And we have this Chandra X-ray Observatory, and it is used for extra observation of highly energetic astronomical objects and events in space. And after seeing all these space telescopes, I want to tell you that there are very huge telescopes on ground as well. These are some ongoing projects under construction. Here you see TMT, 30-meter telescope, and you see another extremely large telescope. And as our project is mainly focused on radio astronomy, here comes the radio telescopes. You see this very huge 110-meter radio telescope and this 100-meter telescope. When we work on radio telescope, we don't use mirrors or lenses. We use these metallic parabolic dishes, and you will see more radio telescopes in Alini's talk. So here is another one, 76-meter radio telescope. So after seeing all these ground and space-based telescopes, it's a very small activity for you. You can do it later. But what you have to do, you can think about a ground-based telescope and a space-based telescope. And you have to write 2 advantages for both and 1 limitation of both, so that you can understand that we cannot do all the astronomy by putting all the telescopes on ground, and we cannot do all the astronomy by doing all the telescopes in space. So this is a very small and easy activity for you. And other one, I am giving you a chance to build your own observatory. No limitations. Forget about every limitation that is in your head, that you don't have money, you don't have resources. Forget about it. Just decide what type of observatory do you want. It should be a ground-based or a space-based observatory. What wavelength you will be observing with that telescope, and what is your science goal. So basically you can start with your science goal, because your science goal will tell you the wavelength, and your wavelength will help you decide if your telescope should be on ground or if it should be on Earth or in a space. So these are very 2 interesting activities for you related to ground and space-based telescopes. Now, before we move to Stellarium and Aladdin, I have a question for you. Do you know what it is this? Do you know which constellation is this? I think you know, because the name is mentioned already. So we are looking at Orion constellation. Okay. So if you look at any sky map, you will see this constellation like this. But when we look in your sky, you will look that this constellation appears like this. Do you have any idea what is the most fascinating facts or interesting facts about this constellation? Why this is my favorite? Why I'm showing you only this constellation for working in a Stellarium or Aladdin? So I am showing you this constellation for several reasons. First of all, if you do naked eye astronomy, you go outside and try to observe the night sky. It is very easy to find this constellation, especially in December, January, February. You can easily recognize these 3 stars, which is known as Orion belt. So you can easily recognize. And this constellation has very interesting astronomical objects, very diverse. You see Betelgeuse, which is a huge red giant. Okay, it means it's nearing the end of its life. You see Regal, a very hot, luminous blue star, right? So you see red star, you see blue stars, and it means that these stars are at different stages of their stellar evolution. And we see Orion Nebula, which is the most studied star forming region in the universe. It is the nursery where the stars form. And this constellation is mostly seen in northern as well as southern hemisphere in winters. And you can do multiple multi-wavelength astronomy on this constellation, or you can say in this Orion Nebula. So this is the perfect example for multi-wavelength astronomy. So before I move to the next part, Eleni, how much time do I have?
So I will give you 10 minutes.
Okay, thank you.
And then theory schooling system is here to give us the beautiful presentation they have presented. So yes, please wrap up in 10 minutes so we can.
Yeah, I'm very excited for the presentation.
Yes.
Let's wrap up this in
Where
10
to?
minutes. Yeah. So we have talked about Orion Nebula, and here we are seeing this interesting animation, and you can see what we see with our naked eye and what we see if we can see the radio waves, right? So you can see two different views of Orion constellation. So this is a perfect laboratory for multi-wavelength astronomy because it has young stars, it has dust cloud, it has molecular gas, and we can do multi-wavelength astronomy on that. So let's quickly move to the two astronomical tools that I want to show you. The first one is Stellarium. I will very briefly introduce you with the Stellarium, but if you really want to do some in-depth if you really want to have some in-depth knowledge of Stellarium, if you want to make some interesting projects with the Stellarium, you can visit this link where we have the recording of 2-hour Stellarium demonstration where you can find interesting project ideas and you can make projects with the Stellarium. So for now, Stellarium is a free virtual planetarium. You just go to the link and download it. You can use it online on your web browser, but it will have limited functionalities. So it's better if you download it and install it, and then you can use it. You can also use it on your cell phone, of course, with limited functionalities. We can use planetarium to make a sky map from any place on Earth, not only from any place on Earth, on any time in future or in past or current time. And we use Stellarium because even if it's cloudy, if you want to see what is visible in your sky, you can do that in Stellarium. And you can make astronomy topics fun and interactive. It's very useful tool for students as well as teachers. And all the topics that you study in your science curriculum books, for example, eclipses, phases, transit, all these things you can do that in Stellarium. If you want to see any future eclipse, if you want to see any past eclipse, if you want to see how Mars retrograde motion, you can visualize that in Stellarium. You can do that everything in Stellarium. And the next tool that I want to introduce to you is Aladdin. And why Aladdin is important, because we know that astronomers also not only make sky maps, they also study real sky surveys. So astronomers collect huge amounts of sky data in multi-wavelengths. And to explore this data, we use tool known as Aladdin Sky Atlas. So you can access all the astronomical surveys data in this. You can view any specific astronomical object in different wavelengths, and you can overlay catalogs on your images and you can analyze images. So let's quickly explore these tools. Let's do a small exercise. Okay. So I hope you can see my screen.
Yes, we can see.
Okay.
We're looking forward to it.
Yeah. So if you go to if you search for Stellarium, you will find different results, and I suggest you don't go to Stellarium web because it will give you limited functionality. Go to this link. Okay, now you can download for your Windows or your Linux machine, and when you install it, it's free. It's absolutely free, and it's very easy to install it. When you install it, you will see a screen like this. Okay, when you open it, it will take your information about your location and your time from your internet, your IP address, and then you can do further analysis. How we can do that? Okay. Okay, so there are several menus available here and there. For example, let's do the most simple thing. I want to see what is visible in the sky tonight, but it's day here. It's 2 p.m. in Karachi right now, and I want to see what is visible in the sky at 10 p.m. So I can change the speed of time. I can increase the rate, speed of time, so that I can see the sky changing. Okay, you see the sun set, and okay, so you can change the speed, or you can do something else. You can change the time and date here. It's much convenient. Okay, so you can change it from here. Okay, so for example, I want to see, I have the date and I want to see sky at this time. Okay, you don't see much in my sky because the constellations are turned off. If you want to on the constellation, you can do like this. And if I click on any object, I will have the information about this. Okay, so you can see that I can not only see astronomical objects in Stellarium, I can see even satellites. So you can click on any object and you can have information about that. Right, very good. And if you want to see any certain object that is not visible in your sky right now, you can search for that object. For example, I go to search option and I write Orion. Okay, I have this option of Orion Nebula. I have option of Orion Belt. Let's go with Orion. So what does it shows me? It shows me this constellation, Orion constellation, and it's very interesting, as I mentioned earlier. Okay, what I do, I want to, I know that this is Orion Belt, and Orion has an interesting object known as Orion Nebula. If I want to go to Orion Nebula, I can zoom in to that, or I can just simply this. Okay, so this is Orion Nebula. Now if I want to see it at different wavelengths, I cannot do this in Stellarium. What I can do, I can go to another tool that is known as Aladdin. So if you want to explore different objects in multiple wavelength, you can go through my slides. You can have the names of these astronomical objects. But if you want to see any object that is not available in my slide, and you want to say, okay, I want to see what is visible in my sky tonight, you go to the Stellarium, you can see the names of these objects, and then you can search them in Aladdin Sky Atlas. So when you search for Aladdin Sky Atlas, you will see something like this. I highly recommend you to download this. It will give you more options, but you can also go for the web version of this. So you can use Aladdin Sky Atlas in your browser. So when you open it, you will see any image, and it's random image. They are showing you a very beautiful image of 7 sisters right now. But if I want to see any specific image, for example, I want to see Orion Nebula, I can search for it. The important point that I want to show you is that in my lecture, I have shown you images in different wavelength. And if you think, how can I access images of different wavelength of any certain objects? Then here you see there are data from different wavelengths are visible. For example, I can mention few of them very quickly. For example, Chandra, we know that the Chandra X-ray telescope, which in space. So you can see that the Orion Nebula in X-rays looks totally different. If you see Orion Nebula in optical part, it is totally different like this. And if you see it in Stellarium, you will see something like this. But if you look at it in X-rays, it's totally different. And you can explore some other wavelengths from this. Like you can go for ultraviolet, you can go for optical, you can explore different wavelengths from this. And you can also do one more last thing. You can overlay data from different catalogs on this. It will take some time to load, but when once it's loaded, it's showing you the point sources that are available in these catalogs. You can open the Gaia catalog, you can open the TUMAS catalog, and TUMAS is infrared catalog. So these are some tools that I wanted to introduce to you very briefly. But if you want to explore them in detail, as I mentioned earlier, that you can go through our past recorded lectures, and you will have more information on that. And that's all from my side. In summary, I can say that the universe is full of hidden wonders, and it's time for you to explore, because now you are part of this project radio and you have connections with these experts in astronomy, and you are more than welcome to reach out anytime. Thank you very much.
Thank you very much, Hira. That was an amazing demonstration and explanation of the multi-wavelength universe. Thank you very much for all the effort. I'm not sure if there are questions. If you have questions, please place them on the chat and we will try to answer them. What inspired you to talk to us about the multi-wavelength universe? This is what I want to ask. Why we should care about using all these telescopes and putting them into space and on tall mountains. You explained this very well, but I want to hear your personal view on this. I can't hear you, sorry.
So when I was a school student, the most fascinating fact for me about astronomy is that when we look into space, as we look further in space, we look the past. We look more into the past. Like we see sun at 8 minutes. It was 8 minutes ago. We see Alpha Centauri at it was 4 years ago. So the most interesting fact for me is that when we look in space, we look in the past. The next most fascinating fact for me is that when we look at any object in one single wavelength, you have very limited sense of that object. And when we look at different wavelengths, the same objects appears totally different. You have different not only view of that object, but we have information about different physical processes that are going on in that object. So for me, it's like, okay, doing astronomy in one wavelength is giving you very limited observation. To have the holistic view of that object, let's go and do multi-wavelength astronomy. So right now I started my astronomy journey from optical astronomy, but right now I'm doing astronomy, radio astronomy, and X-ray astronomy.
That is fantastic. Thank you very much. We're very grateful for this beautiful presentation. We will move on to our next presenter, which is a school from Karachi. It is the theory schooling system. They will talk to us about construction and operation of low-cost radio antenna. And welcome. Would you like to introduce yourselves and give your presentation?
Assalamu alaikum, everyone. Can you hear us?
We can hear you. Welcome.
Okay. My name is Mohammad Qasim from Theory Schooling System, and I am from Pakistan, Karachi. Today, I am excited to share my project, a low-cost radio telescope. We built this to detect radio waves coming from the sun using simple, affordable equipment. What is radio astronomy? Usually, when we think of telescopes, we think of looking through glass to see light. But space objects also send out radio waves. Radio astronomy lets us see the universe using these invisible signals. And the best part is we can do this even on a cloudy day or during the daytime. Why observe the sun? The sun is a very busy star. It doesn't just give us the heat and light. It also sends out radio waves caused by hot plasma and solar flares. By studying these signals, we can understand space weather, which is important because solar storms can actually interfere with our satellites and phone signals. Objective of our project. The goal of our project was simple. We built a working radio telescope without spending a lot of money. We wanted to detect signal changes from the sun and record how strong they are to prove the sun is radio source. The next part will be explained by Muhammad Ibrahim.
We used everyday items for this, a small satellite dish like the ones for TV, a KU band LNB, a 12-volt power supply, and an analog satellite finder instead of watching TV. Used these tools to listen to the stars. What is a KU band LNB? The LNB is the eye of our telescope. It sits in front of the dish. Its job to its job is to collect very weak microwave signals from space, make them stronger, amplify them, and convert them into a frequency that our meter can read. Working principle. Here is how it works. The big dish acts like a funnel, gathering radio waves and reflecting them into the LNB. The LNB boosts the signal, and then the satellite finder shows us a reading. A higher number on the meter means a stronger signal is being detected. Procedure. To do the experiment, we first pointed the dish at a cold part of the sky, away from the sun to get a baseline. Then we slowly moved the dish toward the sun. We watched the needle on our meter carefully to see if it moved as we got closer to the sun. Next part explained by Muhammad Marsabi.
As you can see from our data at 12:15 p.m. when pointing away from the sun, our reading was only 3, but just 10 minutes later when we pointed directly at the sun, the reading jumped up to 9. This was our eureka moment. Result. Our results were clear. Every time the dish pointed at the sun, the signal went up when we moved it away, the signal dropped. This confirms that our telescope was successfully hearing the radio emissions from the sun. Scientific explanation. Why did this happen? The sun's atmosphere is full of super hot gas called plasma. This plasma vibrates and creates microwaves. Our dish focused those waves onto the LNB, allowing us to measure the sun's energy. Challenges faced. It wasn't always easy. Aligning the dish perfectly with the sun was tricky because the sun is so far away. We also had to deal with noise or interference from other electronic devices nearby, and keeping the mount steady was a challenge. The next part will be explained by Asadullah.
What we learned: electromagnetic wave concept, microwave frequency detection, signal amplification, practical application of physics, importance of data recording, teamwork, and scientific method. Conclusion. In conclusion, we proved that you don't need $1 million lab to do real science. With a little curiosity and some basic equipment, we built a tool that can detect energy from stars 93 million miles away. Thank you.
Thank you very much. That was a great presentation. Congratulations on the building the antenna and operating it. And congratulations on detecting the sun. We can see here your whole school with your teacher. And you, we are very proud of you. Yes, we are very proud of you. And I would like to ask you, how were you excited about this project? And have you done something like that before? Sorry, I cannot hear you. It's okay. It's okay. Don't stress.
The first time on this.
I asked if you are excited about this project with the radio antenna.
Yes, we are really excited for this. And sorry for the mic quality.
No, it's great. Thank you very much.
Thank you.
Maybe the Pakistan team, Hira or Faisal, would like to add something?
Yeah, so it was actually a very great experience for me to interact with the kids. Of course, it was their first time learning about radio astronomy in any way. In fact, astronomy is not taught in school in Pakistan, so I was expecting a bit tough time to explain some concepts, especially. So I was preparing to, as you can see, as you have, I think, checked the pre-survey. There were some very basic questions given just to check what should I prepare. Luckily, when I went to the school, kids had a good understanding. At least for the school level, some of the concepts, physics concepts related to related to light, electromagnetic waves, and stuff like that. They were able. It made a bit easier for me. So then I introduced some of the concepts, and I really liked the enthusiasm from the theory school team and their management, Ubaid. They helped in finding the equipment in local markets, as there are certain challenges in importing things like, finding things like satellite finder in a local market. But so the school team really helped, and I hope that the school children have learned a lot. They were very excited on the day of the workshop, and hopefully they will continue learning and exploring the material which is given to them, and hopefully they have enjoyed it. And I'm glad, actually. I'm really proud that they completed the project, the tasks, and getting the readings, and completing the setup, and then presenting it like this. Although I know it's a bit challenging, again, English, presenting it in front of an international audience for the first time, and again, in a different language. But they did a very. I'm really glad that they come through and presented their work, and proudly presented their work. And really glad that they did, and hopefully they will continue learning this.
I would like to add a few points. Thank you, Faisal. So first of all, I would like to congratulate all the students, the teacher, and the school. Um, uh, as I talk about my astronomy education journey in Pakistan, in the past few years, we have introduced optical telescopes. Okay, let's build a small optical telescope and do optical astronomy. And that was at that time, it was very new thing for students. They were very excited to build some small DIY telescopes. And then in later years, we introduced robotic telescopes in classroom. Students were very excited to use robotic telescopes in Chile and in other countries. They were very excited. But this is the very first time that we had this opportunity to introduce radio astronomy or radio telescopes at a school level, because astronomy is not fully established in my country yet. So astronomy is not part of, like, if not part of science curricula in much detail, it's touched upon it very briefly. So to introduce students with radio astronomy, to show them invisible universe, it's totally exciting experience for us as well as students. And I would like to congratulate the teacher especially, because there are some opportunities, but to seize the opportunity for your students to do, so to put some extra effort with your students so that they can seize the opportunity, do something, and become part of something that is international and very, very international project. Work with the students from different countries, for example, China and Greece, was a very wonderful opportunity, and they seized it and they made most out of it. So I'm really proud of them, and I would like to congratulate them once again. Thank you.
Thank you very much, both, and thank you very much, Theory Schooling System. You were amazing, and I wish you keep taking up the opportunity when it comes, and do more projects and explore the multi-wavelength universe and maybe design your own antenna one day to study astronomical objects. Again, congratulations to all the students and the teacher. We are very excited, very proud of you.
Thank you so much.
Thank you very much. Very nice. You have very nice comments. Congratulations also from the people watching live on YouTube. We are very happy to have everyone here together in this celebration of science. We love astronomy, we love astrophysics and radio astronomy, and we believe it's a vessel to connect our countries, and it's a vessel for peace, right, in these quite difficult times and uncertain times for humanity. Through collaboration and common understanding, we can go even further. And we do have the tools through science to explore the beautiful universe. Very nice. There are no more questions, as I can say. We have quite a lot of time until my talk, which is the next on the schedule. So my talk will introduce the Greek assignments. I would like to ask our Pakistan team, Hira and Faisal, maybe to describe a bit their efforts with teacher training in the country, in your country, which I find very inspiring and very useful, if you would like to share that.
Yeah, so I've been teaching astronomy in Pakistan since 2013. I started teaching a basic astronomy course at the university when I came back from Australia. So a good thing is some of these students, they have become teachers themselves and teaching at various undergrad level and leading some of the outreach program. In fact, Hira is one of the students and she was one of my best students when I taught that basic astronomy course, and glad to see that she has become has been involved in really training a lot of other teachers, and she and leading the efforts in Pakistan related to outreach astronomy. So the desire is there in the students. Hopefully the desire is there, the desire teachers want to teach. The only thing is that the lack of resources and the some of the directions. So one thing hopefully we will try to do is to make this material available as much easily available for all the schools, and not just schools but at the same time universities as well, because it's some of the materials can be used as part of the labs in starting under first semester or second semester undergrad courses as well. So that's the main as Hira will tell you more about the outreach efforts in remote areas. She has done more work. I mostly interacted with universities and schools in the cities. I don't unfortunately I don't travel much in the rural areas, but Hira will tell you much how much because of my corporate lifestyle these days. But Hira can tell a lot about how her experience with interacting with the rural areas. And but I can just say one thing, like even in remote areas there's a lot of interest in understanding astronomy, especially when there's a lot of clear sky there as compared to the cities. The only thing is like these were hopefully the workshops we have done, hopefully the introduction we have done, that will be really helpful for them in going further. Although we started focus mainly on Lahore and Karachi, but in an online workshop we had students from remote areas in Pakistan as well, and not just in Pakistan. Actually, we had people from remote areas in India, like you were saying, astronomy for fees, even in the tough time between Pakistan and India. I was really happy to see a lot of kids from remote areas in India who had joined us and took part in the workshops. So Hira, can you add further?
Thank you very much, Dr. Faisal, for this kind introduction to our work. I talk about, if I talk about my astronomy education journey in Pakistan, I started with students. I used to travel to schools and voluntarily give lectures, tell them about space science and astronomy. But at that point, I realized that there is a limit how many students I can reach with these volunteer lectures. So I started working with teachers, and I started working with the International Astronomical Union, Office of Astronomy for Education, as their National Astronomy Education Coordinator for Pakistan. And I started organizing teacher training workshops. In the beginning, I organized trainings to show teachers how they can teach astronomy in better, most effective ways. And then I started working on showing them how they can use astronomy and space science as a gateway to STEAM education. So that was the turning point, and at that point I developed the interest to introduce more and more tools, like making small DIY telescopes, like introducing robotic telescopes, so that every student can have access to real data, and every student can have access to telescope and radio telescopes. But at that point, that I realized that my all the astronomy education and outreach activities are confined to a very limited region, that is Karachi. I know it's very large city, but I wanted to go beyond it. So with the help of International Astronomical Union, Office of Astronomy for Development, I initiated a project in Thar Parker, which is a deserted region in Pakistan, which is very underprivileged, underserved region in Pakistan. So we traveled to Thar Parker Desert, and we organized teacher training and student trainings there. And at that point, I realized, okay, that's great. I am doing astronomy education uh, initiatives in different parts of my country. I want to do astronomy education project with different countries. So the radio project made that thing possible, and I feel myself that, oh, I am part of something huge, this international astronomy education project that is going to be bigger and bigger with the passage of time. So this is my vision for radio. So my experience of interacting with students and teachers in Karachi and remote regions is out of this world. Totally, is out of this world, because we are very busy professionals and we dedicate our time and energy to voluntarily to these astronomy education projects. And when we get the feedback, and when we see the impact that we created with these students and teacher, we feel like that, okay, our energy and our time, our part of life is invested in something really good. And the thing that I feel, that when students from remote regions or from in my city see that we are trying to create opportunities for them, and we are trying to create opportunities for them, and they are part of something huge, they see they themselves as global citizens, that they, okay, they are part of this international project, their voices matter. They realize that, okay, they are capable to contribute to science. So this is something that they feel, and this is something that's why they work really hard, and this is something that create impact of our projects. So yeah, this is
That is amazing and very, very inspiring words from both of you. Thank you very much for all the effort you put. And I'm really glad that radio has given you the space to explore the international community and offer to the international community. That was our goal from the beginning. And through science, we collaborate all the time for our scientific projects. Hira has demonstrated very well that we use, for example, to observe one galaxy, we use different telescopes. Different countries operate different telescopes. So different countries and scientists in different countries to obtain data and study galaxies, for example, in all these beautiful wavelengths with these beautiful images. So having this in mind, we wanted to bring it to schools and inspire the next generation to follow the road of collaboration and the road of science, and build on that and become the scientists of the universe. For us, it's very important to have a continuation, right? We love doing science, but we also love educating the next generation, so they take over and take it even further. Discover discover all the mysteries of the universe that we haven't solved yet. Like, can we observe dark energy? Can we observe dark matter? Are there things in the universe that we haven't observed yet, right? There are so many unsolved problems. Very nice. We are a bit ahead of time, but I think that's okay, right? Unless there are some questions, let's check. There is a question. So it's about Zooniverse. Let me reiterate the question. The question was if it's a low-code or no-code platform, Zooniverse. So the answer by Hongming was that, let me find it, you can call it no-code, though to make the most of it, to do the analysis, some easy code still needs to be done. But the coding happens afterwards when you have collected your data and exported it so you can analyze it locally. Developing the web page itself is no code. And there is a follow-up question. Is there a demo video to see the possibilities of the platform? Can anyone make a simulation? Does it have limits as far as the number of particles or complexity? I am not sure you can do simulations there. The concept of Zooniverse is you have something ready, okay? And you ask for citizen scientists to classify something like Hongming very well demonstrated. Maybe I can show again if I share our project. So it's used mainly for classification and identification of objects, various things. It can be anything. So this is a project and we classify, as we said, galaxies. So what you upload, that's one example. What you upload are images, PNG images, or you can even upload a small video, but keep in mind that there is limitation in the storage, right? Because you are sharing storage capabilities with many other projects. But if you go, let's see, to the Zooniverse, right? There are, you can see how many registered volunteers and classifications so far. There are numerous projects covering everything, every kind of science, from nature to the universe, lightnings, birds, I don't know, waves, everything, anything that you can do. This is the frog find. I just randomly clicked it. So let's see how we can. It's now available. Excellent. Join in. Yes, I would like to join in. Sorry. Classify. I could not. Right. Classify. They have a very nice description. Okay. So they also provide images, right? So this is a spectrogram to aid you in identifying various calling frog species. So you hear their sound and you convert it to an image. The citizen scientists go and look at the image and follow the tasks. But you cannot build a simulation here. It doesn't have the platform for that. So, okay, good. I hope I answered this question. Very nice. Let's close this. Stop share. And I lost. Wait. Right. There is one more question. Do you work at the observatory in Athens in Pendeli? I think this is for me. So I work at the Observatory of Athens, the National Observatory of Athens. My office is in Thyseo, but I also go to Pendeli. So I visit both places during the week. And I'm in science communication and education. If there are more questions, please type them now. And the next part, it's quite long. It starts with my talk about exploring the radio sky, radio astronomy in the era of big data. Following my presentation, we have Greek schools that will be presenting either via pre-recorded video, because unfortunately today they could not attend. There are some other competitions related to astrophysics in the country, so a lot of the students are taking part in that, but they have kindly kindly prepared videos, and they have subtitles in case the videos are in Greek. And some of the students will also present live. And there is going to be a small break between the Greek presentations, and Faisal will give a demonstration about Python and astronomy. So he will do a very nice introduction to Python for radio astronomy with Jupyter Notebook. So you should all be here and watch it. It's going to be very exciting. We will continue with the rest of the presentations, and then at the end, we will do the closing remarks. So let me check. Very nice. I will start then with my presentation. Very nice. Sorry about that. I was reading some messages. Good. Excellent. I hope you can see my presentation. Could you please verify?
Yes.
Thank you very much. So we will discuss about radio astronomy in the era of big data. We all hear about AI all the time, and now AI is in our lives every day. We will explore the radio sky, and at the background, it's one of the latest pictures from the LOFAR radio telescope and the LOTS survey. I will explain what LOFAR radio telescope is in a bit. And you can see on the left Andromeda galaxy at radio wavelengths. Okay, it's a beautiful galaxy with a nucleus and spiral arms. So we see cold dust from the galaxy. And on the right, you have another small galaxy here. This is an active galaxy, which I will explain also later. And you have a lot of very small, very elliptical compact galaxies, let's say, featureless. So let's start. Here I very nicely described the whole electromagnetic spectrum and why we need different telescopes. So I will follow the beautiful presentation, very well explained concepts, and I urge you to go back and watch it again. The electromagnetic spectrum is radiation from astrophysical objects and everything around us, and we can observe it in many, as we say, frequencies or wavelengths. For us, wavelength is a bit more conceptual. We can understand it a bit better. In a sense, we have the expression also when we talk to someone and we are in the same wavelength. Okay, and we can relate it to waves of the sea. So big waves, radar, radio, microwave. Then we go to the visible, smaller waves, ultraviolet, X-rays, gamma rays. The smaller waves, higher energy, bigger waves, lower energy. So the left part of the electromagnetic spectrum is a bit dangerous for humans because it has the same size as our DNA, so it can alter our DNA, and we don't want that. But as Hira very nice demonstrated, our atmosphere is a filter, so it protects us from daily X-rays. The right part of the spectrum is what we are interested as scientists, what I am interested, but without using the whole information from the whole electromagnetic spectrum, we cannot understand the physics of the astronomical objects. The green band is what we can see with our eyes, and for that we are grateful to our atmosphere that it has made our eyes look like that. Our eyes, let's say, adapted to our atmosphere. Okay, and why do we need all these beautiful wavelengths? Let's start with the nearest star, our sun. Our sun also emits across the electromagnetic spectrum, and that's why we need different telescopes to observe it and understand its nature, right? So different telescopes in space and on the ground. And just to make this note, please never look the sun with naked eye, okay? It's very dangerous, not even with glasses, like common glasses. You need specific glasses that are used for eclipses, because the radiation from the sun can burn your eye. Okay, very nice. And why we need all these different wavelengths? Imagine a human, right? To see the appearance on the outside, you can use your eyes. Okay, but if you want to examine, to see the inside of the person, to see the bones, for example, you have to do an X-ray. So you use a different part of the spectrum. If you want to study the organs, you do ultrasounds, different technology. So in order to understand a body, you need different parts of the electromagnetic spectrum and different radiations. Very nice. I will show you also a few of my favorites, multi-wavelength objects. The Crab Nebula in the X-rays is a neutron star, and actually a pulsar. So you see some pulses emitted, jets. We call them jets. These are X-ray jets, very high energies. In the optical, we see cocoons expanding after a star has exploded because it has exhausted all its material. And so it has a lot of gravity, a lot of mass, a lot of gravity. Everything collapses, and as it collapses, it bounces back violently in space, and it leaves all the outer layers of the stars in space. And the colors, as you remember from Hira's presentation, are different chemicals, okay, that we color with our beautiful techniques, the astronomy techniques. In the infrared, we observe cool dust and regions where stars are born. And in radio, we also observe cold dust, but some other processes that I will describe in a bit. Of course, we are part of a bigger construction that is called the Milky Way. So our sun is one of the 200 billion stars in the Milky Way, right? And this is how we see the Milky Way from the side, okay? And at different wavelengths, starting from radio continuum at 400 megahertz, atomic hydrogen. I will show you later on another image of another galaxy. So these give us different information about the galaxy and where the cold dust is, where the stars are, where the warm dust is, or if you have a supermassive black hole in the center, for example, and it produces radio jets. We will see this in a bit. So you start from radio and you move down to infrared, optical, X-rays, and gamma rays. So I think this is a very beautiful picture of the multi-wavelength Milky Way. We also explained this just to summarize. The Whirlpool galaxy is one of the objects that also amateur astronomers see through their telescopes, and it's one of the very well-known targets. But when you see it through an amateur telescope, you see something small and fuzzy. So to get these beautiful images, you really need very good telescopes, professional telescopes. Radio telescopes, here you see also the temperature. Okay, so colder for radio, hotter for X-rays, and different information. We have a spiral galaxy in the center. You have the nucleus, a lot of stars, older stars forming around it. Here you have a lot of dust and gas, and you see it darker because the light cannot go through the dust. Okay. And a lot of stars are being born in cold dust. To be able to see through the dust, you need infrared. So here you see the cold dust and the regions where stars are being born. Okay, and in the radio, you see the star formation regions much more clearly because this radiation that I will explain a bit later is non-thermal in nature, and it tells us that here you have local magnetic fields and you have free electrons that interact with these magnetic fields from the regions where the stars are being born, and they highlight these regions. Okay, and on the other side, you have hot stars in the ultraviolet, especially blue stars, they are less frequent in galaxies. Okay, and In X-rays, very energetic phenomena, high energies. They are emitted from the hottest regions. So the hottest region here is the nucleus, and here is the companion galaxy. Okay, close to the center of the galaxy. Circinus galaxy, it's a composite image on the left, so we put all the three images together to create a composite. In radio, you see highlighting the spiral arms. It's cool hydrogen gas, the specific one, so it's one wavelength, is not continuum. It means that this is only the hydrogen and not the full band of the radio emission that can come from this object. And usually hydrogen gas extends even further than where the spiral arms are. In the X-ray, you see the warm dust, and beautifully here, it highlights also the spiral arms. Probably this galaxy has formed from interaction with another galaxy because we see a lot of gas outside of the main body of the galaxy. And on the right, you see stars in the infrared and cold dust. Now we go to further away to Centaurus A and an active galaxy. Okay, this is an active galaxy because it has a supermassive black hole, and the supermassive black hole, the area around the supermassive black hole emits a lot of energy, and it has a lot of a strong magnetic field and a lot of electrons that speed. They go very fast to speeds close to the speed of light, and these are getting trapped by magnetic fields of the black hole and emit in radio. So the radio continuum now, right? So it's a broadband, not just an emission, it's a broadband. The radio continuum tells us this information, exactly this physical process, that you have you have very fast electrons, relativistic electrons, they're getting trapped by the magnetic field of the source. Okay, and they produce this radiation we observe in the radio. We call it synchrotron radiation. In the radio, 21 centimeters, so this is the hydrogen, you see a very different picture. Okay, so this hydrogen is excited and it emits, but at different regions than the jets. So you have different processes. This is related, if you see the optical image that we see with our eyes, or here with the DSS survey. This is the spiral rings, spiral arms of the disk, let's say, of the galaxy. So it is related to the dust here, the dust and gas in this galaxy, and processes in there. In the optical, we see stars, we see the dust, but as absorption, okay? And then in X-rays, a lot of things are happening. This is very complicated. We still see a jet like in the radio because we have high energies, but we also see a lot of hot gas. And this tells us that this galaxy was formed through interaction with another galaxy. And as they were merging and passing through each other, they left behind this hot gas. They left it in the intergalactic medium, as we say, and we can observe it with X-ray telescopes. Very nice, but why do we observe all these objects with big telescopes? Okay, they are beautiful for sure, but we don't only observe them because they are beautiful. We want to understand the bigger picture. We want to put the pieces of the puzzle together. So I showed you a star, I showed you a supernova, I showed you the Milky Way and other galaxies. There are many more astronomical objects, planets, for example, in our universe, and we need to understand how they were formed. So the most established theory of the universe creation is the Big Bang. This is a theory that has been proven through observations, is not a hypothesis, okay? So it still stands to today, despite new discoveries that challenge it daily. So the universe was created by a situation with a very dense and very hot we call it singularity. And space and time started being created. So the universe, our universe, creates its own space and its own time, okay? And then time starts moving. The first stars are being born. Stars and dust together create galaxies, so bigger constructions. Galaxies, because of mass, they attract each other and they combine, they merge, right? So they go through each other and they become one. And then a lot of processes start happening inside the galaxies. A lot of stars are being formed because you have a lot of cold dust in galaxies. We call these dusty starburst galaxies. And these phenomena are very violent around the similar amount of time. So if you check, I'm talking about billions of years, right? Processes in space take a very, very, very long time. So billions of years. At the same time, this dust is being attracted by the center of the galaxies, where you have black holes. These black holes grow and they become supermassive black holes, and they attract all the matter around them. They attract stars, they attract dust, they devour it, let's say. And that's why they devour even light. We call them black holes because not even light can escape them. So we have the appearance of very bright objects. We call them quasars. These are active galaxies. We call them active because they're black holes at the center. The supermassive black holes are very massive and they attract everything around them. The space around the black holes are very energetic, and they produce a lot of energy across the electromagnetic spectrum. Okay, we can observe them with infrared telescopes, the hot plasma around it, with radio telescopes, the accretion disk, so the matter that falls into the black hole. We can observe the jets, as I showed you before, and we can observe hot X-rays, warm dust from them. So galaxies keep evolving and merging and growing. We have the appearance of more compact galaxies. They keep merging and they grow bigger and bigger. Okay, so this process that takes 13.7 billion years brings us to the very big galaxies we see today, like our Milky Way or Andromeda, or big elliptical galaxies that don't have a disk or spiral arms. But they're not so big as we thought. They're actually a bit smaller. So, I mean, less massive. So there are some processes that happen during these 13 billion years that stops galaxies from forming stars. And this is this guy here, quasars. So black holes, supermassive black holes emit, the areas around the supermassive black holes emit winds, emit radio jets, and these do the following. They warm up the environment around them. Okay, so when the galaxies have cold dust and they are preparing to make stars, and you have a supermassive black hole warming up the environment, then the cold dust becomes warm and you cannot form stars. We say that they stop star formation. In astronomy, we call it feedback. And this way, the galaxies cannot grow more mass and become overly massive. Okay, so these processes are very important. And in radio astronomy, this is one of the things that we study. Okay, how galaxies grow and evolve, and why we see them like that today. But of course, we try to understand everything that composes a galaxy, from the stars, planets, pulsar, supernova, dust, gas, dark matter, dark energy. Very nice. I realize I should have put some simulations in there. I apologize for that, but I hope I excited your imagination to think about this astrophysical phenomenon. Let's move on a bit on the physics. What kind of emission do we observe in radio? So we can have thermal emission. Anything that has a body emits black body radiation because of temperature, right? Like for our sun, for example, or other astronomical objects, or ourselves. So we emit heat, and this is called thermal radiation. Also, we have the thermal free radiation, example from hot nebulae. So planetary nebulae. For example, our sun is a star that after 5 billion years, when it burns all its materials, it will expand, okay, into red giant, and it will leave all the outer layers of the atmosphere in the solar system, and it will become a planetary nebula. Okay, so this is thermal energy of electrons, and it is converted into radiation as they are accelerated when they pass an ion. We have non-thermal radiation. I already mentioned it a couple of times. This is very important for radio astronomy because we observe this the most. It's dominating the megahertz and gigahertz frequencies. So these are electrons, very, very fast electrons. They go close to the speed of light. These are relativistic electrons that are accelerated in magnetic fields. Around us, there are magnetic fields. In space, there are magnetic fields. Okay, Earth has a magnetic field to protect us from the solar winds. In the center of galaxies, you have magnetic fields. In the regions where stars are being born and in the disk of galaxies, you have magnetic fields, a bit less strong. And in between galaxies, you also have magnetic fields. What exactly is a magnetic field is a very difficult question. And if you hear the interview by Carl Sagan, you will understand why. So we take it as granted and we describe it with math. So they get accelerated in these magnetic field lines, and we find them in star-forming galaxy regions and active galaxies. And we also have line radiation. I also already mentioned H1, the hydrogen line. It's a line emission. It's a bright or dark feature in a spectrum, okay? And it's caused when a photon of specific energy changes the state of an ion, atom, or molecule. This is the definition. I will show you some pictures, so to make it a bit more comprehensive. Here we have the comparison of optical and a thermal camera, okay, on the left. So this scientist, astrophysicist from NASA IPAC, is demonstrating that we cannot see his arm because it's covered by this bag. Okay, our eyes cannot see the thermal emission, the temperature of his arm, because it's covered behind the bag. But if you have a thermal camera, well, the bag is transparent. So you can see how hot his arm is, okay? And this is the concept behind observing also in infrared wavelengths, okay? You can see through objects that you will not be able to see with your eyes. Then let's go to the non-thermal type of radiation. Here, as I said, we have relativistic electrons. I'm demonstrating with a sketch. You have the magnetic field line, and the electrons get trapped by the magnetic field, and they spiral around them, okay? And they emit radiation. We call this synchrotron radiation, and we observe it with our radio telescopes. Okay. In reality, we observe a composite of radiations, thermal and synchrotron, but the thermal is a small percent and synchrotron is dominating, at least at the ranges that we observe, and I will show you now. Let's see some examples. Okay, I already said that in the radio sky, the dominant features are non-thermal sources. Okay. We have on the left a star-forming galaxy. We can see the beautiful, we can see the beautiful spiral arms. In the center, you have the nucleus, and this is a composite image. You have the optical underneath and the radio on top. Okay, and the radio highlights regions where stars are being formed. And in these regions, because you have magnetic fields, so free electrons, these are usually cosmic rays, they get trapped by these magnetic fields and they emit non-thermal radiation. But as you see, this is more local phenomenon. They don't go very far. Okay, these are smaller magnetic fields and the phenomenon is more locally. So it highlights star-forming regions that can even be outside the galaxy, because if the galaxy has interacted with another galaxy, sometimes they leave gas and dust in the intergalactic medium, and if that dust is cold, then you can form stars. Okay, very nice. On the right, we have an active galaxy. This is a fantastic active galaxy, Hercules A. It's a composite image. On the background, you have the white ones is the optical image from the Hubble Space Telescope. This is an elliptical galaxy. It doesn't have spiral arms. It has been formed because of merging with other galaxies, and after a long time, 13 billion years, everything is more symmetrical. Okay, and these galaxies usually don't form stars, maybe less than a star a year. I will give you an example. Our galaxy forms one star a year. Okay, so this type of galaxies, not even one sometimes. Okay, but in the center, they have supermassive black holes where their mass is 1 million or even 1 billion times the mass of our sun as a comparison. And because these black holes have very strong magnetic fields in the center and they have free electrons, these electrons get accelerated in the magnetic fields and they produce these jets of radio emission. So these travel to distances beyond the galaxy. You can see here the radio emission from, which telescope is that? I suppose it's the Very Large Telescope, because this is an RADIO. So here you have bubbles, we call them lobes, and here you have jets. And this is all non-thermal emission. This process takes millions of years, okay? It doesn't happen instantly. And the black hole remains active for millions of years, and then it doesn't have anything else to eat around it, so it stops, okay? Very nice. I'll show you a few more nice images. Here we have examples from the LOTS survey. It's a survey with a low-far radio telescope, the low-frequency array. I have a very nice picture to show you later from the low-far telescope. And they observed the whole northern hemisphere with this telescope. And they released their data last week. Yes. On the left, you have Andromeda Galaxy. Andromeda Galaxy is our neighbor. It has 1 trillion stars, a supermassive black hole, and it's a spiral galaxy. And here we can see cold gas and star-forming regions. Okay, so you have synchrotron emission, non-thermal emission from the galaxy disk, but also from regions in the center. We don't have a visible jet like in the previous galaxy, but some scientists are studying the regions very close to the black hole, and they have revealed some jets. So we are very interested in that to see what happens. As you see, the space is not empty. There are hundreds and thousands and millions of galaxies that emit in radio. Some are smaller, some are bigger. Okay. On the right, you have supernovae in the Milky Way. So these are stars that have exploded, and because electrons get accelerated in the magnetic fields, you still have this type of process happening. On the bottom, my favorite topic, active galaxies. I'm a bit biased, I'm sorry. Look at them. They have beautiful, beautiful, beautiful shapes. They have jets that are wiggly and they're bent, and they tell you how they interact with the environment, or if they are falling down in a cluster. So this particular guy here, so you have a big cluster of galaxies that is composed of hundreds or thousands of galaxies, and this one is attracted by the massive galaxy in the center of the cluster, and it's falling in. So the jets that it produces in the radio are falling behind like a tail, like a comet tail, but it's not quite the same. Okay, so by studying this, we can understand how active the black hole is in the center of the galaxies, how much energy it emits. Okay, the bigger picture. Does it stop star formation in a galaxy and why? So it helps us understand the galaxy itself, and it helps us understand interactions within galaxies and environments. Are these galaxies alone, or are they part of a group or a cluster? And on the right, two more beautiful galaxies that are wiggly. They show interaction with the local medium. And many, many, many radio galaxies at the back. Right, this is beautiful. I hope you agree. This is a nearby galaxy, NGC 6964. On the left, you see the optical, and you see stars and dust. Okay, so it's a spiral galaxy, and we see it, as we say, face on from atop. In space, we don't have the opportunity to rotate the galaxy. We don't have this technology yet. It would be great if we would be able to take an image and flip it and see the side of the galaxy. But it's not possible because everything is projected in 2D. Okay, space is 3D, but as we see it through our telescopes, we see that like everything is projected on the same plane. So it's impossible to see this galaxy with the technology that we have now from the side. We see it from the top, and we study millions of galaxies, hundreds of millions of galaxies at different shapes, different orientations, as we say, in order to understand how galaxies form and grow and evolve. Okay, and this takes a very long time. Right, on the left, optical light, what you see with your eyes. On the right, radio from a single line at 1.4 gigahertz, at 21 centimeters, hydrogen gas. And this is spectacular because for the first observations that happened in hydrogen gas revealed that these galaxies are much bigger, right? Our eyes can only see so much, but with radio telescopes, and particularly with the hydrogen gas, we see that you have gas here, okay, active gas, extending beyond the optical regions of the galaxies. So it tells you interactions have happened. This we can understand more about the nature of galaxies. Let's say it simply. Okay. Right. So now I will discuss with you about how we observe the invisible radio universe. Of course, with radio telescopes, and I will show you some examples. Here we have a composite of the Very Large Array and my favorite field in the sky, the cosmos field, and active galaxies and very small galaxies far away. So, pretty pictures. We have single-dish radio telescopes. This is the 100-meter Effelsberg radio telescope in Germany, a bit outside of Bonn. You can see me here 11 years ago, or maybe more, 13 years ago, when I visited for a conference, and they took us on a tour, and I also went up the stairs. I didn't step on that dish, but I went up the stairs and observed the beautiful view. It's a fantastic telescope and very important for space exploration. And if you don't notice, I will tell it to you. This is another radio telescope. I will show you the bigger picture later. This is called LOFAR, and these are dipoles. These are antennas on the ground observing at low frequency. So this is observing at gigahertz. These are observing at low megahertz. The fast radio telescope, 500 meters. So this is built in a natural valley. This is another way to build a telescope, so you don't have to support the whole weight, because after a point, you need to be able to support the weight of the telescope. And if you want to build a bigger telescope, you go to a natural valley. Another big telescope was Arecibo, but Arecibo sadly was destroyed. because the reflector fell on the dish and destroyed it. And it's very expensive to fix it, sadly. This is the telescope. So in China, the schools made the fast models. This is the telescope they made a model of. Okay, they constructed a fast model radio telescope. The Very Large Array, I have worked with this data all my professional life. So the VLA is in New Mexico in the USA. It's composed of 28 antennas, and each antenna has 25 meters in diameter. I have stepped on top of this antenna. It's amazing. So that was back in 2004 when I went there for a summer school. So this is a flat area, and this technique is called interferometry. Okay, so instead of building a huge dish, which is very difficult to construct and very expensive, okay, you build many antennas and connect them. You point at the same region of the sky, and then astronomers combine the data, and they can zoom into the centers of galaxies and get very beautiful pictures. We have more of these. So all these are called pathfinders, square kilometer array pathfinders. This is in Australia, ASCAP. It's 36 antennas, 12 meters in diameter. We also use data, and our Radio Galaxy Zoo project is using data from this radio telescope and analyzes them. This is Meerkat. It is in South Africa. It has 64 antennas, and its antenna is 13.5 meters in diameter. And we also have data with my collaborators from this, and we analyze them to explore the universe. Dipole arrays, I already showed you the low band antenna, the picture next to Effelsberg telescope. Okay, so this is called the International LOFAR telescope. These are stations all over Europe. Okay, each station has minimum one low band antenna array, okay, that observes at 60 megahertz, and a high band antenna array that observes at 150 megahertz. It's a broadband, so this is the central frequency. It looks a bit like that when they are together, okay? And in Netherlands, they have more of them because it started from there, here, the Dutch stations. They have a very nice cluster of stations, and then it expanded to the rest of Europe. The most recent ones is Bulgaria and in Italy. They will build one in Malta very soon and another one in Italy. And we are doing a lot of efforts since the last 3 years to bring this project to Greece also and expand. By expanding, what do? You build like a model telescope, like a virtual, let's say, dish that is the size of Europe. So you can really zoom in and see beautiful details of galaxies, like the images I showed you before of the Andromeda galaxy and the LOTS images. Because to make these beautiful images, they had to use all these antennas together. This is the millimeter array, so radio, millimeter, submillimeter, they are being used together in many surveys because we get a lot of information out of them. This is the Atacama Large Millimeter Array, ALMA. It has 66 antennas. There are 54 antennas of 12 meters and 12 antennas of 7 meters. Okay, so they can detect emission that is more extended or emission that is more compact, far away or closer. And this is in Chile, in the Atacama Desert, and I would really love to visit that one day. So, what do you do with all these telescopes? You combine them into one big telescope to create a huge telescope the size of the Earth. This is the Event Horizon Telescope. This concept is called VLBI. The specific collaboration combined 8 radio telescopes across the Earth, and the purpose was to get the first image of a black hole, because they could zoom in so much into the center of nearby galaxies and of our own galaxy that they could see hot plasma matter spiraling around the central black hole, which we cannot see, of course, because it does not emit light, but the region around the black hole, matter, as it gets attracted, it gets broken. Okay, so electrons go there, protons go there, and things start spiraling around the black hole. We call this an accretion disk. This is like a ring emission. It's very hot plasma, and we observe it at very high gigahertz, 200, 300 gigahertz. Okay, and it's the only way to observe the center of galaxies in that resolution. All these telescopes are called square kilometer array precursors because the era of radio astronomy is now. Okay, this is the best time for radio astronomy, and we are very excited about it. We're getting a lot of data, and this gives us the opportunity to understand the physical mechanisms of objects. So the square kilometer array will be in 2 places. I will tell you a story. When I started my PhD in 2003 in Oxford, my supervisor, Steve Rawlings, co-wrote the science case for the square kilometer array with Chris Carilli. And so this was a vision to make arrays in a square kilometer, but this expanded in 2 continents. So today, there is going to be SKA mid 197 antennas with 13.5 meter dishes in South Africa. This is going to expand Meerkat. Meerkat is going to be part of this. And the other one is in Australia, SKA low, 131,000 antennas, 512 stations across Australia, and together they will observe low frequencies and high frequencies. And then on the US side, I forgot to add this, I'm sorry, we have the next generation VLA, so the expanded VLA that will observe at higher gigahertz. We have entered the era of big data, and I think you will agree with me that we take a lot of photos in our phone and there is no space left. So this also happens when we take a lot of photos of astronomical objects. There is a big problem in the astronomical society right now, and I would say in every field, about how to store the data, how to process the data. We need computers, we need storage. These are expensive and they are not fast enough yet. We are getting petabytes of data. So these LOFAR observations I showed you, its 8-hour observation is like 3 terabytes of data. And when you analyze them, they triple in size. Okay, so you really need servers, you need supercomputers to analyze the data. You cannot do it on your laptop. It's impossible. We have a lot of surveys of the sky, and a lot of surveys are doing monitoring in the sense that they observe again and again and again the same object, or they observe continuously to find things that happen once. We call this like a burst, or transient things that happen repeatedly. And we have a lot of collaborations. As I said, we need computing and storage. So we wrote about this. During the pandemic, we held a conference and we wrote a book about it of 500 pages. This is called Data Intensive Radio Astronomy, how you acquire the data, you store it temporarily, you analyze it, you process it, you analyze it, you write your algorithms, you write your AI algorithms, you do your citizen science projects, and then you put them on archives so other scientists can access them. Okay, so all this process, the life cycle of the data is described here, and it also raises the issue of preserving our environment. This is the last chapter, because it's very important not to forget that with all these AI data centers that are popping up, okay, which is mostly for business, is not for science, we are destroying our environment. We are stealing water from the cities, water that is very, I mean, it's not enough for everyone. So a lot of cities are already suffering from that. So we really need to be very cautious about how we proceed and how to preserve our environment and protect our lives. Parenthesis closed. Okay. So I will give you some examples. The SKA will produce more data than the global internet traffic today. Wow. And this is a projection. The required ASCAP SKA computing capacity. This is from a few years back. So it's an extrapolation of the data. And it's a, yes, it's a, why am I stuttering? Because it's very difficult to have these storage capabilities and computing capabilities. We are not there yet. This is a projection, but we are not there yet. This is a projection from a few years ago. So let's say what will happen every year that we obtain data from the SKA, the radio telescope, the volume of data stored would fill over 1,500,000 gigabyte laptops, okay? So like the laptop you have at home, or maybe a bit better, 1 million times that. We don't have that. So they need 2 supercomputers to store the data, to archive 600 petabytes per year, and to store on average 500 gigabyte laptop. So you will need that, more than 1 million of them a year, as I said before. This is the data flow. It goes from the SKA mid and the SKA low. So this is in South Africa, this is in Australia, through, I guess there are, sorry, I forgot the word. Anyway, I will continue. So you store them temporarily, but you need to store them on supercomputers and to have a good rate so users can use this data, okay? Because you cannot store them, the Astronomical Society has decided not to store them. So the raw data are being purged. So scientists today are writing algorithms that will, as the telescope observes, the data come on your computer, right? You see them and you run an algorithm that tries to find important objects like, I don't know, pulsars, or to identify them in the data, okay? Identify them on the fly, and then it stores them, it takes them to the next part of the pipeline, and then this can be processed, pre-processed, processed, and analyzed. Everything else cannot be stored because there's not enough space for them. So these antennas produce too much data to handle, okay? So the idea of I take some images of the sky and I store them on my laptop has died. It doesn't exist anymore. But let's put it a bit on a context that we can understand in society. What is a petabyte? It's 1,000 terabytes or 1 million gigabytes. 1 petabyte of data can store approximately 200 million to 333 million songs. Okay, so also it can store 1 billion books, or 1 petabyte per day. You can create over 200,000 high-definition movies or 256 million photos daily. I know I take a lot of photos, but I don't take 256 million photos. That's okay. But you see the problem, okay? And with LOFAR, next generation, LOFAR 2, and with SKA, we will obtain petabytes per day. So we are here. We don't have this yet. And what about the discoveries? If you throw away the raw data, you know, a lot of discoveries happen serendipitously. It means that scientists, when they designed the telescopes, they didn't know these things are going to happen, you know, sorry. They didn't know that these objects were there in the universe. They just observed them in their data. There was like an anomaly. And they said, oh, what is that? Oh, wait a minute, that is something. For example, the discovery of pulsars. So this was discovered completely randomly by a PhD student back in Cambridge, whose supervisor got the Nobel Prize for them, unfortunately. So she saw a repeating pulse in the data. Hongming before showed you example of these pulses, okay? And she said to her supervisor, this is something. He said, no, it's nothing. She said, no, it is something. It was something. It was something big. It was the discovery of pulsars, okay? The last, so the end of the life of massive stars, major discovery. But if you throw away the raw data and you only look in the data for things that you know they exist, are you stealing discoveries from the next generation? So this is a question for you to think, and we can discuss it. Because you can see the projection in the 60s and 80s, there was a huge discovery because astronomers were free to discover. And then, not so free anymore. Eh? So how do we analyze the big data? Supercomputers. The data are a lot, so we need to make algorithms to analyze them and train these algorithms to handle millions of data sets. And for that, we have citizen science projects. So I'm referring you to the talk by Faisal later on, and earlier to the talk by Hongming. The key message is we need all three. We need the humans, we need the AI, humans in the sense of professional scientists, and we need also the citizen scientists. So this is the best recipe. Okay. We are going to discover many new things, we hope. We want to probe the early universe in the new SKA era. So what happens right in the beginning after the Big Bang, to understand dark energy and dark matter, how galaxies evolve. We are studying this, but there are so many unanswered questions. To study magnetism, magnetic fields, this is a very big question mark. We can study them, but still we need to understand it better. We will test better the general relativity and the origin of gravitational waves, also from the collision of galaxies and collision of supermassive black holes. We want to study transient and bursting phenomena, so bursts in the universe, radio bursts, and why they happen, where they come from. This is a very big field right now. To study the sun, the nearest object, study planets, okay, exoplanets, and of course, the origins of life. This is a very big question mark. We want to solve it. I will go very fast if I have time. Hira, can you tell me what time it is?
Oh, it's 3:20 p.m.
3:20
in Pakistan.
3:20 p.m. Pakistan. So let me check the program because I think I talk too much.
I can check that for you.
Yeah. So if I have 10 more minutes, I'll show you some very cool things if you give me the time. And then the Greek schools can start. Would that be okay?
Yeah, I think because I guess some student presentations will be shorter than expected. So
Okay.
I think you can
Okay, good,
show
good.
us cool pictures, please.
I will show you. So I will show you how we analyze the data through some sketches. I wasn't able to put the videos up here, but so I refer you to the NRAO website for the videos that will follow. And I will show you a cool demonstration of how and where you can put the antennas to get a better signal. So we said that we use big antennas, and in order to make a very big radio telescope, we need to use a lot of them. Okay, so this is called interferometry. And how does it work? Its antenna receives the incoming signal and it collects the data, which are correlated and pre-processed. Okay, so here is an example from ALMA. You get the analog signal and you convert it into digital. from all the antennas, but these observe the same object, but they have a different phase, as we say, and you really need to synchronize them, okay? You really need to make sure that the observations are synchronized so you can process them. This happens in a machine called a correlator that collects all the signals from the different arrays and synchronizes them, okay? These are big machines with a lot of computing and storage capacity. So how does the interferometry work? You have two antennas, and depending where you put them, how close or how far away, you can see more compact emission or more extended emission. Okay, so we use it to create a virtual telescope. Okay, and as I said, in some cases, the telescope has the size of the Earth. And what do we get? We get an interference pattern in the same way that we would get an interference pattern from light if you have two gaps, okay? And you shed a torch through it, you will get interference patterns. So in the same way, the gaps are the antennas, okay? So when we collect the data, they are waves, and the wave patterns are similar to the wave patterns in the light when the light passes through a pair of slits, as seen here. Okay, so it creates regions with more light and regions with no light, or let's say less light. Okay, so in radio astronomy, the antenna pair takes the place of the two slits. Here you would place the dishes. Okay, then you take this pattern, which it doesn't tell you much at the moment. That's why we have a mathematical model. It's called the Fourier transform, and we transform it into a signal. Okay, so it's a wave, and then it gets translated in the set of stripes. And depending on your telescope, you will get different waves or your configuration, okay, where you put your antennas. The more antennas you have, the clearer your picture would be, and you have to play a game where to place your antennas. We will play the game in a bit. So the more time also we observe, the better the image gets, but sometimes you need to observe not continuously, but again and again, and to add the pictures together to enhance the signal, because you reach a limit after a point if you observe continuously, and then you don't get much better observations. So this is how so if you consider this the sky, these paths are what the antennas observe after 4 hours, okay? So then you combine them and you do your Fourier transform and you create an image. And these are astronomical objects. The image is not very clean, so you have to clean it. And we have other algorithms that do that. So now we will do an example, and then I will stop talking. And so we have a cat, right? And the cat, we will observe it with the VLA telescope, radio telescope. So here we have it in compact configuration. The antennas are very close together. So this is the advantage of the VLA. You can move the antennas further and closer. It has different configurations, as we say. So let's see how, after we take an image with a radio telescope, how the cat is. Here we have the cat, but it's not very good image in the radio. Okay, we observe with 20 antennas for 10 minutes. We see the highlighted region and something that looks like the glasses, maybe the nose and mouth, but it's not very good. Maybe we need more time, observing time, or maybe we need to change the configuration because now it's not very good. So I'm changing the configuration and I'm spreading out the antennas, the same amount of antennas, the same observing time, and there you go. We have a better picture, but I have a lot of noise. I'm not satisfied with that. So I put the antennas even further out. Oh, here I can see also as we say, moustakia in Greek, of the cat and highlighting the glasses. but I have a lot of noise. I want to clean the noise. So 20 antennas, 10 minutes. I'm gonna go 30 antennas because I have a lot of money in my budget. It is a little bit better, but I have still a lot of noise. I add observing time. It is a little bit better. I'm going back and forth. Okay, but not extremely good. So now, because I had unlimited funds, I put all the antennas, 74 antennas. In 10 minutes, they gave me a fantastic picture. Unfortunately, in real life, we don't have all the money. So astronomers, we play this game. We try to find the sweet spot. We can observe with different configurations, compact, middle, more extended, and we put antennas in different areas so we can cover more of the space, okay, and reveal the best photo without spending so much money that we don't have. So that's it. Thank you very much. Thank you for your patience. Right, are there any questions? So I will show, okay, there are two questions. You mentioned that there is a limit for the growth of stars and galaxies. How is this accomplished? Is there, if there is matter around, how it can be kept out of their attractive gravitational force? So I mentioned that galaxies form because of stars and gas. Okay, they are these big cities composed of stars, gas, and dust. And the biggest galaxies have supermassive black holes in the center. Okay, so these supermassive black holes, they hit the environment around them, but not just immediately around them. They hit the whole galaxy and they hit the area around the galaxy. So galaxies live inside halos of dark matter. Dark matter is 27% of the composition of the universe, of the ingredients of the universe, and it attracts galaxies and keeps them where they are. Okay, so black holes and the phenomena around the black holes hit the environment and they stop star formation. You need cold dust to form stars. And when you hit the cold dust, you can't form stars. So that is the concept, that it's galaxy, in the galaxy involution concept. Okay, you grow galaxies, you form stars. They are star bursting in the beginning because they have a lot of dust. Then approximately at the same amount of time, you have the development of supermassive black holes in the center of the galaxies. They hit the environment, they stop the violent star formation, so you don't grow overly massive galaxies. Okay, so nothing, and to answer about the gravitational force, well, I think black holes are a great example of that. Not even light escapes a massive object. So there are no more questions. Only mentioned that the issue of environment is very crucial, and thank you for that. Indeed, it is. So I don't want to waste more time on me. I'm happy to discuss
Thank
more
you
on
very much, Eleni. It was a wonderful talk, and I believe everybody enjoyed your talk, and we are pretty much well on time. Don't worry.
Okay.
I checked the schedule. Yeah. Well
Okay,
done.
thank you so much. That's great. Thank you so much. I wanted to show you the last part because I think it's quite cool to see how you can place the antennas. Right, so we will start with the Greek presentations now, and I will see my schedule. The first school is Boulafedio General Upper High School of Leros, and their presentation is about exploring the sky of Leros with Stellarium. So that's great, coming after your very nice presentation, Hira. So we have Konstantinos Kondouris and Dimitra Brousali. They have sent a video, okay, and which I will play. The video is in Greek, but it has subtitles. So bear with me, excuse me. Very nice. So let me share. And let's enjoy them.
Ονομάζομαι Παπαδόρης και είμαι μαθητής της Τρίτης Λυκείου του Πολυτεχνείου Γενικού Λυκείου της ΛΕΕ. Καλησπέρα, είμαι η Νικαβλούσα, είμαι 17 χρονών και μαθήτρια του Πολυτεχνείου Γενικού Λυκείου ΛΕΕ. Αποφασίσαμε μέσω της εφαρμογής Stellarium να ανακαλύψουμε τον ουρανό της ΛΕΕ. Ας ξεκινήσουμε από τα βασικά. Ο Πτολεμαίος ήταν ένας Έλληνας και Ρωμαίος αστρονόμος, ο οποίος δημιούργησε το γεωμετρικό μοντέλο του σύμπαντος, δηλαδή κατανόησε πως η Γη είναι στο κέντρο του σύμπαντος και κατέγραψε περίπου 48 γνωστούς αστερισμούς στο βιβλίο του The Almanac. Οι αστερισμοί έχουν πάρει τα ονόματά τους από ήρωες της ελληνικής μυθολογίας και χρησιμοποιούνται ακόμα και σήμερα. Εδώ βλέπουμε την ανατολή του ήλιου από την Αγία Μαρίνη. Εδώ πέρα, στον ουρανό, βλέπουμε τον αστερισμό της Ανδρομέδας και τον αστερισμό του Περσέα. Ο γαλαξία της Ανδρομέδας είναι ο κοντινότερος γαλαξία σε σχήμα σπήρας στο Μύκηνα. Εδώ βλέπουμε μια φωτογραφία από ένα συνεφιασμένο καλοκαιρινό απόλυτο στη Λέρα. Από πάνω βρίσκονται οι αστερισμοί του Ταύρου και οι Πλειάδες. Το έντονο μπλε του χρώμου οφείλεται στις ιδιότητες των αστεριών και κυρίως στις υψηλές θερμοκρασίες τους. Εδώ βλέπουμε το ηλιοβασίλεμα το λιμάνι της Αγίας Μαρίνας. Εδώ είναι ο ήλιος που βρει και εδώ κρύβεται ο αστερισμός της Ορίγκα με το πιο κοντινό αστέρι να είναι η Καπέλα. Ανάμεσα στο πιο κοντινό αστέρι τον νυχτερινό ουρανό. Εδώ βλέπουμε το φωτισμένο φάρο της Λέρου. Είναι λίγο πριν τη δύση του ήλιου. Και εδώ κρύβεται ο αστερισμός του Ηρακλή. Σύμφωνα με τον αρχαίο ελληνικό μύθο, ο Ηρακλής ήταν ένας ήλιος που ήταν γνωστός για τη δύναμή του και το ηρωικό του πνεύμα. Πλατεία στην Αγία Μαρίνα, εκεί βλέπουμε πολύ αρνά το φεγγάρι ανάμεσα στον αστερισμό του Τζέμινα. Εδώ πέρα βλέπουμε τους μήλους της Λέρου, κάτω από τον αστερισμό του Δράκοντα. Μύθοι χρησιμοποιούνταν παλαιότερα για την άλυση του σιταριού. Ο αστερισμός του Δράκοντα μπορεί να γίνει ορατός όλο τον χρόνο. Εδώ βλέπουμε το ψαραπόλι του Παντελιού και πίσω ο ήλιος να δει. Εδώ πέρα κρύβεται ο αστερισμός του Ορίωνα με το πιο γνωστό αστερισμό των Μπερδελκές. Σύμφωνα με την ελληνική μυθολογία, ο Ορίωνας ήταν ένας σπουδαίος κυνηγός. Αλλά επειδή σκότωνε πάρα πολλά ζώα, το οποίο ήταν ενάντια στην πίστη των κυνηγών, οι δύο το τιμώρησαν. Η θέα Άρτεμις στριμούσε για τον θάνατό του και γι' αυτό έφτιαξε έναν αστερισμό αφιερωμένο σε αυτό που ονομάστηκε ζώνη του Ορίων. Εδώ, από τα παρελθόνια μας, προσπαθήσαμε να αναπτύσσουμε διάφορες φάσεις της σελήνης. Επομένως, είναι αντιληπτό ότι όλοι συνδεόμαστε με έναν πιο ουράνιο τρόπο, που αυτοί οι αστερισμοί είναι αναπτύσσονται σε όλες τις χώρες του κόσμου. Σας ευχαριστούμε πάρα πολύ για τον χρόνο σας. Γεια σας!
Amazing, very nice. So here I think that was a tribute to you. That was amazing. Stellarium and Orion. Okay, 2 for 2.
Wonderful.
And a bit of the mythology in here, combining culture and the night sky. This is what we love also in Greece. And we will continue with the next school. Let me see my notes. So, the next school is the second junior high school of Metamorphosis in Athens, Attica. And their title is Construction of Radio Antenna, Detection of Radio Signals. So I have a video to show by the students Antonis Zoitakis, Marina Yannou, Eleni Yannou, Celia Yanaki, Elena Kurkuletsi, Athanasia Hidjiou, Χριστίνα Μαυρίκη, Κωνσταντίνος Μιχαλάκης, Κλειό Δρίτσου και Ευρυδίκη Παρασκευά. Sorry, and I started speaking Greek all of a sudden. Okay. Very nice. Let me find the video. Very nice. Okay. Let's share it. So,
Σιγά σιγά θα εξελίξουμε την ευκαιρία, δεν μπορούσαμε να συνδέσουμε και ένα υπολογιστή. Ναι. Χρειάζεται πιο πολλά εξαρτήματα.
Αυτό θα είναι το τέλειο, παιδιά, θα καταφέρουμε. Θα γράψετε μια ωραία έκθεση για του χρόνου, για να πάρουμε και το εξάρτημα αυτό και να περάσουμε τα μηνύματα του ήλιου στον υπολογιστή μας.
Αν θέλουμε να δώσει. Ναι, χρειάζεται μερικά ακόμα.
Και τι είπατε προλίγου για τον ήλιο, ότι είναι καλύτερα που είναι ψηλά.
Είναι καλύτερα που είναι ψηλά, γιατί είχαμε πάρα πολλά σήματα από κεραίες, από τα κινητά, από τα ραδιόφωνα.
Κατάλαβα.
Οπότε, επειδή είναι ψηλά, είναι ξεκάθαρο ότι βλέπουμε ήλιο. Αν ήταν πολύ χαμηλά στον ορίζοντα, δεν μπορούσαμε να το ξεχωρίσουμε.
Ακριβώς.
Και θα δείτε τώρα τη διαφορά, ελπίζω να βγει, να τον δούμε. Γιατί είναι αυτό μάλλον. Λοιπόν, αυτό το LMB ανιχνεύει ακτινοβολία στα 10 με 12 γίγαντες, που είναι θερμική ακτινοβολία των. Οπότε πρέπει να τον δει να παίρνει και τη θερμότητά του. Άμα είχαμε ένα άλλο είδους πιάτο, μια άλλη κεραία, που ανίχνευε στα χαμηλά gigahertz, όπως λέγαμε είναι μη θερμική, θα μπορούσαμε να τον ανιχνεύσουμε και μέσα στα σύννεφα. Αλλά μας δείχνει συγκεκριμένη πρέπει να φαίνεται λίγο. Να μην είναι τελείως κρυμμένος πίσω από. Πρέπει πηγαίνεις έτσι προς τα πάνω και όταν θα τον ανιχνεύσεις θα ακούσεις τη διαφορά στο satellite finder. Αλλά πρέπει να πηγαίνεις συνεχόμενα για να καταλάβεις τη διαφορά. Όχι προς τα πάνω. Έτσι. Οπότε το κατεβάζεις χαμηλά για να ακούσεις. Έτσι.
Δεν κατεφόρει.
Όχι, αυτά είναι δεσιμπέλες. Να το. Είδες που βγαίνει.
Από τη διαφορά.
Ναι.
Κάντε απόλυτη σχέση για να ακούσετε.
Σήκωσέ το λίγο προς τα πάνω. Ωραία. Very nice. Thank you very much. The second International, excuse me, of Metamorphosis. Apologies
for the Greek. I will translate what I was saying. I went to visit the school and we were constructing the radio antenna. So I explained to them that you detect via the LNB the 10 gigahertz signal from the sky, from the sun, right? And this is more to the thermal part of the spectrum. So it's very hard to detect it when there are clouds. We had a bit of cloud coverage that day, but it was enough, there was enough gap to detect it. You heard the detection, it was a sharp sound. And I think they performed the detection perfectly. I'm very, very happy for them. Congratulations to the school. Thank you, Hira. It was great to see the enthusiasm of the team, indeed. So, right, I think the next school should be live. Let me check. No, one more and then live. So, the third school is the first model junior high school of Athens, Greece. And we have another Stellarium presentation, but now we have the Hydra constellation. Okay, so Sofia Papadopoulou and Angeliki Prelorenju will show us their video. Let me share it for you, just a minute. So. Right.
We are here to present the Hydra constellation. First, we're going to talk about some basic information about constellations. If you were to draw lines in the sky between the stars and use lots of imagination, the picture will look like an animal, an object, or a person. These shapes are called constellations. The constellations you can see at night, depending on your location on Earth and the time of the year. Over time, cultures around the world have had different names about constellations depending on what people thought they saw. Today, there are 88 officially recognized constellations. More about the Hydra constellation. Hydra is the largest constellation in the sky, covering 100 degrees from east to west. It lies in the southern celestial hemisphere, stretching across 1,303 square degrees of the southern sky. Hydra's head is located south of the constellation Cancer, and its tail lies between the constellations Centaurus and Libra. The constellation was first catalogued by the Greek astronomer Ptolemy in the 2nd century. It has 13 stars with known planets. The brightest star in the Hydra constellation is Alphard, with an apparent magnitude of 1.98. There are two meteor showers associated with the constellation, the Alpha Hydrids and the Sigma Hydrid. The Hydra constellation is connected to a myth about a monster, the Lernaean Hydra. Hydra was a monstrous water serpent, and it had a dog-like body and numerous snake heads, with one head being immortal. Its breath was poisonous and its blood deadly. This creature terrorized Lerna, regenerating 2 heads for each one being cut. It was born to Typhon and Echinda, and a sibling to other famous monsters like Cerberus and Ladon. Hercules had to kill this monster as his second labor. He was able to do so because his nephew, Iolaus, cauterized the stumps, allowing Hercules to dissipate the immortal head. He replaced the Hydra in the sky as a constellation to commemorate the event. The Hydra represents persistent problems where solutions often create new problems. Its defeat signifies overcoming seemingly impossible obstacles through perseverance and ingenuity. There is another myth associated with the Hydra constellation, and it is the myth of the crow and the figs. According to this myth, Apollo sent a crow to bring him water in a cup, but the crow got distracted by a fig tree. The figs weren't ripe yet, so the crow waited several days. As a result, it returned late, and it lied by blaming a water snake for the delay. Apollo afterwards realized the deception and punished all three by placing them in the sky as the constellations Corvus, Crater, and Hydra.
Now we're going to talk about mythology and equivalents in other cultures. The Japanese mythology says that the Hydra is a monstrous eight-headed, eight-tailed serpent that demanded human sacrifices and was slain by the god Susun. The Norse mythology says that the world serpent is a colossal sea serpent that encircles the earth. It represents a cosmic threat that Thor battled. The Mesopotamian mythology says that the chaos goddess Tiamat has a dragon-like offspring, including Mushushu, a dragon serpent slain by Marduk. The Vedic or the Indian mythology says that it's a dragon representing drought and darkness, defeated by the god of thunder, Indra. The Chinese mythology says that it's a nine-headed poisonous serpent representing chaos, defeated by Yu the Great.
Before we finish the video, we would like to say which sources we used so as to create this video. First of all, we used the Stellarium, afterwards the website of NASA, an online constellation guide, Wikipedia, and finally, Britannica.
Thank you so much for watching our video.
Very nice, excellent. Amazing. I learned a lot of things. That's great. Thank you very much. It was very, very inspiring. Great job. Congratulations. Right. So let's see who's next. Right. I think I should have the Model Junior High School of Heraklion with me. Are they online? Yes. So, hello. We can't hear you.
Can you hear us now?
Yes, we can hear you now.
All right,
And
so
you. Please introduce yourselves and we're ready for your presentation. Go ahead.
hello everyone. We are students from Greece. Our school is the Model Junior High School of Heraklion, and it's located in Crete. The title of our work is Building an Antenna to Visualize the Sun's Radio Frequency. The contents of our talk are study and construction of the antenna, search and visualization of the frequency, and conclusions.
At first, we discuss about the electromagnetic waves that our sun emits. The star of our solar system is a black body radiator and emits radiation across many different frequencies, not just a visible light. For example, emits in radio waves, microwaves, infrared, visible light, ultraviolets, X-rays, and gamma rays. Therefore, we want to detect radio frequencies that emit the sun. The parts of the construction are an attenuator, one LNB low noise block down converter, a battery of 12 volts, a BIST component, SDR USB, and a laptop or a PC. Of course, we use several different cables, such as a coaxial cable and others.
We use a satellite dish where weak radio waves are collected and amplified by the LNB, as well as they are converted into lower frequencies. An attenuator reduces the intensity of the signal without distorting it. The BIST power the LNB with a 12 volts battery. The BIST also protects the SDR, software-defined radio. The SDR is needed to properly route the signal to the computer. We download the SDR program onto the computer. We search for various frequencies to detect the 10.7 GHz emitted by the sun. We subtract the LNB value of 9.75 GHz and found that at a frequency of 950 MHz, we should see a peak.
We build a radio antenna that can detect radio frequencies emitted by the sun. The construction consists of specific materials, and the signal we receive is displayed by an appropriate computer software. Thank you for your attention.
Sorry, I'm muted. I thought I was talking. Thank you so much. Congratulations. I'm very excited that you did the antenna and you connected it with a computer and got so far. Congratulations to you and to your teacher for the very hard work. Thank you to have you with us. Please stay and enjoy the rest of the meeting. Right, so let me see where we are next. So we have a pre-recorded video from the Gymnasium of Philothei. The title is Our Solar System, and the presenter is Panagiotis Michalakeas. So let me find it. Sorry, wrong. Let me find it. Yes. Oh, that's not okay. Well, I have a little technical problem. Right. Why? Okay, that is not correct. Rotate, right. No, I'm sorry, the video is rotated for some reason, and that should not. It's good. Okay, thank God. Okay, good. I checked everything yesterday, but well, let's see.
Hello, my name is Panagiotis, and I will present you my project for geography, the solar system. My plan was to create a three-dimensional craft. My project includes all the planets, the sun, and the comet. First, I took a cardboard box, I painted inside blue, and then I let it to dry. Then I took the acrylic balls and I paint them as the colors of the planets, so they can match. After the balls and the cardboard dried, I took some thread and 9 screws. I tie in the screws the thread. Then I connect the screws to the planets, and then I glue on top the thread. After all this, I put the LED lights on the bottom.
Right, excellent. Okay, I'm back. I hope you were inspired to make some science art yourselves, because it is not just STEM, it's STEAM. Okay, so we also encourage people to do art related to science. Let's move on. Right, we are at the 7th Gymnasium of Haidari. They sent us a video about the Great Bear, Ursa Major, in ancient civilizations using Stellarium. So the presenters are Michaela Lazaridis, Myrto Manolakou, Katerina Margaroni, Eleni Plataniti, and Chrissa Souvleli. Right, let me find the video and I will share it shortly. Very nice. So, zoom, share.
We're the astronomy team of the 7th Gymnasium of Haidari, and we will present you our project on the topic The Great Bear, Ursa Major, in ancient civilizations using Stellarium. Astronomy is a science that studies celestial bodies like the sun, the moon, and the universe in general, trying to understand how it was created and works. Since ancient times, astronomy has played a very important role in the development of human civilizations. Ancient cultures observed the sky to measure time and create calendars, as well as for orientation and navigation, while many of them associated celestial bodies with their religion. The tool that can be used in astronomy is Stellarium. It is a software that allows people to use a home computer as a virtual planetarium that connects the position of celestial bodies and draws a representation of how the sky will appear to an observer, depending on location and time. It can also draw constellations and simulate astronomical phenomena. For this paper, the Sky Culture tab was used from Stellarium to explore humankind's cultural history, where you could switch to the viewpoint of ancient or various contemporary cultures. Constellations are defined as patterns in the sky set from fixed celestial objects,
Study focused on the Great Bear constellation and its interpretation by the ancient Greeks, Egyptians, Babylonians, and Chinese, as well as the Navajo. The study concluded with a comparison between the characteristics of these civilizations and those of contemporary societies. It should be noted that the ancient Greeks, Egyptians, and Babylonians were located in relatively close regions, specifically near the intersection of Europe, Africa, and Asia. In contrast, the Navajo were located in North America, where the ancient Chinese civilization developed in East Asia. All of these cultures were situated in the northern hemisphere. The Great Bear constellation consists of 7 main stars. The first 4 form the bucket, and the last 3 the horn or tail of the spoon. The study gave us the following comparison tablet. Let's see it in detail. The ancient Greeks did not give specific names to each star of the Great Bear, but used different names for the entire set, such as Great Bear, Eleki, also mentioned by Homer, Vago, because it resembled the card, and 7 stars or 7 oxen. It was one of the best-known constellations in the northern hemisphere, and was used for navigation and orientation, because it never set below the horizon. According to legend, the Great Bear is associated with Callisto, a nymph who was transformed into a bear by the goddess Hera. Zeus, in order to save her, placed her in the sky as a constellation. For ancient Egyptians, the Great Bear did not represent the bear and was called the fire fork or Musketeer. It was one of the most important constellations in the religion. The Great Bear appeared eternal because it never set. It made the symbol of the immortal, which were associated with eternal life in the afterlife. Some of its stars have special significance. Mizar was used for the orientation and alignment of the pyramids. Alkite was associated with deities and sacred symbolism. The Babylonians called the Great Bear constellation the Plough or the Chariot, a name similar to the honor given by the ancient Greeks. They associated with deities and myths. Due to its fixed position in the north, they also used it for orientation, calculation of times, and prediction of seasons. In addition, Babylonian astrologers monitored its movements to make predictions for the kingdom and played an important role in understanding the origin of the world. The Navajo saw a slender man where the Great Bear is and called him the Revolving Man. Constellations had sacred significance for them and were associated with myths and the creation of the world. They believed the stars were placed in the sky by divine forces and served as guides for decisions, agriculture, and ceremonies. Observing the sky helped maintain harmony between man, nature, and the universe. The ancient Chinese called the constellation Beidou, the Northern Dipper. The Great Bear was very important as it was considered the center of the sky. It was a symbol of power, and the emperor was considered a heavenly representative. Its position in the sky helped determine the seasons, agriculture, and ceremonies. Finally, it had religious significance and was used as a guide to cosmic order. Today, the official name of Ursa Major is the Great Bear, the same as the one used by ancient Greeks. Rather than being linked to religion or mythology, it is used to study the universe, conduct astronomical research, and support learning. The comparison also showed that the position of the Great Bear in the sky has changed significantly over time. First, the stars are not stationary, so the Great Bear didn't have the same shape in ancient times as it does today. Second, the precession of the Earth's axis slowly shifts the constellations relative to the horizon. In conclusion, studying the Great Bear shows how the same stars were interpreted differently, from myths and gods to scientific purposes, connecting humans with the universe. Its culture gave the constellation its own name based on beliefs, needs, and lifestyle. Despite differences in location and time, civilizations shared common use for the Great Bear, including religion, measuring times and seasons, and navigation. Thank you for your attention.
Very nice. Excellent. Amazing. Well done. Well done. Fantastic. Well done. That inspired me to go out and look at the night sky. I don't know about you. So let's move on. Also, the 7th Gymnasium of Haidari with the radio antenna construction this time by Thanos Vasilakis, Petros Spinos, Vasilis Dimou, Maria Skoupa, Thanasis Psikos, Panagiotta Psikou, Danai Miami. Just a second to find their very nice presentation. Antenna construction, very nice. And share it with you so you can all enjoy it. Yes. Amazing. Amazing. Okay, amazing. I hope you watched it okay, and you enjoyed that. I think that was excellent. It was art, form of art. Congratulations to the to the students and to the director. That was amazing. Excellent, excellent. Right. So, next, we go to the first gymnasium of Rafina with a black hole merger simulation from Panayota Marina Bamiadzi and Panayotis Yiannopoulos. Let me please find this and share it with you. So we're number 8. Very nice. So, and share.
Good afternoon. We're students of the Middle School of Rafina, Greece, and we'll discuss about the merge of two black holes. Our main goal was to observe better the results with the use of simulation using Python. Our goals were the understanding of gravitational waves, the interaction between the black holes, and the shape of their orbit before the final collision. Black holes are upper human things that attract every form of energy as they affect the spacetime. When these black holes attract each other, they create gravitational waves. When these attract, we observe the kind of orbit, the reduction of the distance, their movement before the collision, and the creation of gravitational waves to help us learn and understand about the universe. We used a ready open source Python code, the completed developing code platform Visual Studio Code, and Python libraries. We started by uploading and running the Python code and made some changes as to get the diagram of distance and time, the orbit of black holes, and the final video of their collision. Finally, we extracted them to analyze them. So now let's analyze the data and our observations. In this slide, we see the diagram of the distance between black holes. Specifically, the blue line shows us the change of the distance of the black holes, which tends to decrease until they merge, while the black line shows us the trend of the distance. We also notice that the black line is a steeper slope from 200 milliseconds to 400 milliseconds, where the greatest reduction in distance occurred. Here we see the diagram of the mechanical energy of the black hole system. We notice that from 800 milliseconds onwards, the mechanical energy increases rapidly, while at the same time, from what we saw in the previous diagram, the distance is significantly smaller. In the simulation, we see that the black hole follows a spiral orbit, which justifies the increase and decrease in distance. You also see that from a certain point onwards, the black holes move very fast. That is the moment when the mechanical energy increases a lot. And this results in the creation of gravitational waves. So, from the simulation, we learn first, how the black holes interact with each other. Furthermore, how gravitational waves are created. And last, what is the characteristic spiral before the merge of the black holes. This is the bibliography and the sources we use for the study, and thank you for your attention.
Very nice. Congratulations. Excellent. Right. Let me appear again. Very nice to see that the students are also taking on Python coding projects. To mention and thank also my PhD student Lukas Vlachos, Lukas Doukas, that made this available to us for this project. And yes, I'm glad to see that the students are taking on. Very nice. Yes, happy to see future scientists, the future scientists. Absolutely, I agree with you, Hira. Let us move on. Very nice, very nice. We have another antenna construction. I don't think we have enough antennas here shown, so I will show you a lot today, okay? A lot. And it is interesting to see how each school approaches this assignment. So now we're going to the second gymnasium of Kastoria, and to the students, Ariadne Alexiou, Konstantinos Asnais, Leonidas Asnais, Maria Ελευθεριάδου, Maria Ιωακιμίδου, Ελευθέριος Καραλής, Πρόδρομος Παμπουκίδης, and Alexandros Papadopoulos with a radio antenna construction. So, let us share and go.
Βάζουμε τώρα μια ραδιοεπηρέα. Λοιπόν, αυτή τι κάνει η ραδιοεπηρέα, ανοιχνεύει τον ήλιο. Πρέπει να συναρμολογήσουμε κάποια ηλεκτρονικά στατήματα. Πρέπει να ξέρουμε κάποιες απλές γνώσεις για το ηλεκτρομαγνητικό φάσμα. Τι κάνει αυτή η διάταξη? Επιτρέπει την ανίχνευση ραδιορυθμάτων από τον ήλιο. Δηλαδή, εκπέμπει ο ήλιος κάποια ραδιορυθμάτα και εμείς θα στρέφουμε την κεραία προς τον ήλιο και θα ανοιχνεύουμε τον ήλιο. Η συχνότητα στην οποία εκπέμπει ο ήλιος είναι περίπου στα 10 GHz. Το ηλεκτρομαγνητικό φάσμα είναι αυτό που βλέπουμε εδώ στη φωτογραφία. Αυτά είναι καλώδια, δύο τέτοια καλώδια, τα οποία είναι τύπου R, λέγονται, για να συνδέσουμε το δορυφορικό μας πιάτο. Τερδιόμετρο είναι αυτή εδώ στη σκηνή. Βλέπετε, αν τη συνδέσουμε στο ηλεκτρονικό δείκτη, μας δείχνει τι σήμα και πόσο μεγάλο κύμα θα έχουμε. Αυτό είναι το αναλογικό τερδιόμετρο. Και άλλη ελληνική παιδιά είναι αυτή εδώ στη σκηνή, βλέπετε. Και μια μπαταρία μας δίνει ενέργεια, είναι λίγο μεγάλη αυτή. Δεν είναι σαν τις νέες μπαταρίες. Και όπως όλες οι μπαταρίες έχουν ένα θετικό πόλο και ένα αρνητικό. Και επίσης το δορυφορικό πιάτο που το είδατε έξω. Εντάξει, αυτά είναι τα υλικά. Και επίσης χρειαζόμαστε και πρέζα, το πίγμα, το δοκιμάδικο, ταινία.
Θέλω να σου πω, το σπάμε.
Αριστερό το πράγμα. Έτσι.
Αλλά,
ωραία.
Πάτω.
Ωραία.
Πρέπει να το δοκιμάζεις τώρα. Ναι. Άμα σου λέει εσύ να το βάλεις πριν.
Μια πλευρά του καλωδίου θέουμε το LSD.
Εδώ.
Ναι, εκεί κάτω. Πάνω το εκεί μέσα το... Το γυρνάμε. Μια πλευρά Άρα, θέλει κάποιος να βάλει...
Ναι, εγώ. Και ο Λευτέρης στο άλλο.
Έλα, Λευτή.
Άξιο, να δουλεύει το κόμμα. Είμαστε. Δεν χωράει το... Δεν θέλω το γυρνάω.
Τι θες?
Αυτό
εδώ γυρνάς. Το μεταλλικό το γυρνάς, να πιάσεις τα πάσα. Ωραία. Τώρα το βλέπετε εδώ πέρα, πήρε ρεύμα.
Ναι.
Ωραία. Έτσι, μπράβο.
Γραφείο.
Το ίδιο.
Φινάλε.
Κάπου εκεί πάνω πρέπει να είναι.
Τώρα.
Δεν το είναι
Γύρισε.
απίστευτο.
Excellent. Bravo, as we say in Greece. Excellent. Well done. Let me very quickly describe in English what they were saying. So their professor initially explained what they need to do for the antenna construction and showed all the materials. Then the students themselves took on the task and they said they are very excited to actually use their hands, and these are the kind of projects that we want. So that was very inspiring. They constructed the radio antenna and they went outside to detect the sun, and congratulations to the whole team. It was inspiring to see teamwork. Right, so, oh yes, next we have the third model upper high school of Ilion with their project, the Radio Sun, and Zoe Duyeni, who will say hello to us. Hello, Zoe, do you want to speak and address the audience?
Hello, we are from the third model high school of Ilion. My name is Zoe and I represent the team that worked to create this video. I am a senior student in the third grade of high school. It is a great honor for us to participate in this International Astronomy Conference. Our project focuses on the study and observation of the sun through radio waves. Through this work, we explored how radio waves allow us to detect solar activity and understand better the dynamic nature of our star. In the video you're about to watch, you will see how we approached this investigation, the methods we used, the data we examined, and what we learned from observing the sun beyond visible light. We hope you enjoy our work as much as we enjoyed creating it. Thank you very much.
Thank you very much. We are really looking forward at watching your video. Let me share it.
Παρατήρηση σε ραδιοκύματα. Υλοποιήθηκε στο πλαίσιο του προγράμματος RADIIO από μαθητές της ΓΑΜΑ Λυκείου και αφορά τη μελέτη του ήλιου μέσα από ραδιοπαρατηρήσεις.
Στόχος της εργασίας μας ήταν η μελέτη του ήλιου σε διαφορετικές ραδιοσυχνότητες. Αναλύσαμε τη θερμοκρασία λαμπρότητας, συγκρίναμε εικόνες σε διαφορετικά μήκη κύματος και εξετάσαμε τη σχέση μεταξύ συχνότητας, ύψους και θερμοκρασίας.
Ο ήλιος είναι αστέρας φασματικού τύπου G2V. Αυτό σημαίνει ότι έχει κυτρινοπό χρώμα και θερμοκρασία επιφάνειας περίπου 5.800 Kelvin. Ανήκει στην κύρια ακολουθία μία διακριτή λωρίδα αστέρων.
Στο διάγραμμα Hertzsprung-Russell αστρικού χρώματος και λαμπρότητας φαίνεται η θέση του ήλιου στην κύρια ακολουθία. Εκεί βρίσκονται αστέρες όπως ο ήλιος που βρίσκονται σε υδροστατική ισορροπία και η ενέργεια παράγεται από τη σύμπηξη υδρογόνου σε ήλιο.
Ο ήλιος αποτελείται από διαφορετικά στρώματα. Η φωτόσφαιρα είναι το ορατό τμήμα. Πάνω από αυτή βρίσκονται η χρωμόσφαιρα, η μεταβατική περιοχή και το στέμμα, το οποίο είναι το θερμότερο στρώμα.
Ας δούμε τώρα τι είναι τα ραδιοκύματα.
Τα ραδιοκύματα είναι μορφή ηλεκτρομαγνητικής ακτινοβολίας. Παράγονται κυρίως από επιταχυνόμενα ηλεκτρόνια και μας επιτρέπουν να παρατηρούμε ψυχρές ή ενεργές περιοχές του ήλιου.
Τα ραδιοκύματα παρατηρούμε θερμική και μη θερμική εκπομπή. Επίσης, ανιχνεύουμε εκρήξεις τύπου 2 και 3
που σχετίζονται με ηλιακές εκλάμψεις και έντονη δραστηριότητα.
Όταν μελετάμε στα ραδιοκύματα,
ο ήλιος φαίνεται διαφορετικό σε κάθε συχνότητα. Οι χαμηλές συχνότητες αποκαλύπτουν τα ανώτερα στρώματα, ενώ οι υψηλές δείχνουν τα βαθύτερα. Έτσι, μπορούμε να μελετήσουμε περιοχές αόρατες στο οπτικό φως.
το διάγραμμα δείχνει τη σχέση μεταξύ θερμοκρασίας και συχνότητας. Οι κουκίδες αντιστοιχούν σε πραγματικά δεδομένα, ενώ η καμπύλη δείχνει τη θεωρητική προσαρμογή. Χρησιμοποιήσαμε εικόνες από διάφορα ραδιοτηλεσκόπια. Ο κλειστός κύκλος δείχνει τον ορατό ήλιο, ενώ ο διακεκομένος το ραδιοδίσκο, ο οποίος συχνά εμφανίζεται μεγαλύτερος.
Κάθε συχνότητα αντιστοιχεί σε διαφορετικό ύψος στον ήλιο. Σε χαμηλές συχνότητες βλέπουμε το στέμμα, ενώ σε υψηλές τη χρωμόσφαιρα με διαφορετικές θερμοκρασίες.
Στις υψηλές συχνότητες παρατηρούμε τη χρωμόσφαιρα. Οι λευκές περιοχές δείχνουν υψηλότερες θερμοκρασίες.
Στις συχνότητες από 1 έως 5 GHz παρατηρούμε τη μεταβατική περιοχή. Η θερμοκρασία φτάνει περίπου τους 100.000 Kelvin και ο ηλιακός δίσκος εμφανίζεται μεγαλύτερος.
Στις χαμηλότερες συχνότητες παρατηρούμε το κατώτερο και μεσαίο στέμμα. Η θερμοκρασία φτάνει έως και 1.000.000 Kelvin και αρχίζουν να φαίνονται δομές πλάσματος.
Στις πολύ χαμηλές συχνότητες παρατηρούμε το ανώτερο στέμμα. Η θερμοκρασία φτάνει τα 2 με 3 εκατομμύρια Kelvin
και το μέγεθος του ηλίου φαίνεται πολύ μεγαλύτερο.
Συμπερασματικά, ο ήλιος είναι ισχυρή ραδιοπηγή. Το στέμμα είναι πολύ θερμότερο από τη φωτόσφαιρα και κάθε συχνότητα αποκαλύπτει διαφορετικό τμήμα του.
Η εργασία μας βασίστηκε σε επιστημονικές πηγές όπως το LOFAR, το NRAO και την NASA Solar Physics. Σας ευχαριστούμε για την προσοχή σας.
Very nice. Congratulations. Excellent. So let me quickly describe what the students did. Okay, so they studied. You can't see me. So wait a minute. Now you can see me. Excellent. Right. Congratulations to the students. Congratulations, Zoe, and to the teachers. Thank you very much for this excellent presentation. I will very quickly describe what it was in English for our international audience. So they observed the radio sun, and in particular with radio wavelengths, of course, and different telescopes. They said that the sun is a star of G2V type. Okay, so it's like a yellowish color with a temperature of around 6,000 Kelvin degrees. And they showed the sun in the main diagram, the HR diagram, and the structure of the sun. The many phases of the sun, okay, so it emits across the electromagnetic spectrum, as we also saw in my presentation before. And why we study the sun at radio waves? Because, of course, it looks different depending on the frequencies. In low frequencies, you have higher atmosphere, and high frequencies you can see deeper in the sun, okay? And of course, there are regions that we see in radio waves that we don't observe with a naked eye. They showed you how it looks in the observations that you take from radio telescopes and the spectrum of it, and the different images that you take with different radio telescopes. Okay, and actually the comparison with the sun that you see with our eyes and the more extended radio emission that is revealed with low frequencies. Okay, so to summarize, they learned that the sun is a very strong radio source. The outer layer of the sun, the outer atmosphere is very, very, very hot, okay, hotter than the photosphere, and every frequency reveals different physical parameters in the sun. Okay, thank you very much. Congratulations again. Let's see what is next. Next, we have a video from the Gymnasium of Philothei about planets by Erika Kokini, Sotiris Papakonstantinou, and Rafaela Maroulaki. So bear with me so I can share it. Right. And we go.
Planets. Κίνη Ήρκα, Παπακοσταντίνου Σωτήρης, Μαρουλάκη Ραφαηλία.
We wanted to do this project as we had the puzzle ready and we simply wrote a little information about its planet. We printed and cut out photos and glued them onto the cardboard as well as the puzzle.
Then we wrote some informations and the names of the planets.
Mercury. It is the closest to the Sun and the smallest in the solar system. Venus. The brightest object in the sky and the second in distance from the Sun. It is about the same size as the Earth. Earth is the third closest planet to the Sun, the only one inhabited by humans and the only one whose surface is dominated by the liquid element by 71%. Mars. It is the fourth planet from the Sun and the second from Earth. It is called the red planet because of the red color on its surface. Jupiter. It is the largest planet in size and mass in our solar system. Saturn. It is the second largest planet after Jupiter and the only one with 9 rings.
Uranus. It is not visible to the naked eye and is the first planet to be observed by telescope. Neptune. The fourth largest in diameter with a mass 17 times greater than the mass of the Earth. Pluto is a dwarf planet. It appears from the Earth as the 15th magnitude star.
Okay, I think that was it. Very nice. I am back. Excellent. Thank you very much, Gymnasium of Philothei, for educating us about the planets and for making this puzzle. I like that puzzle very much. Beautiful. Right, let's move on. We have another radio antenna. You will not get bored of them today. It's all about radio antennas. Radio antennas everywhere, to every school. Excellent. This time from Leodio School of Nea Smyrni, radio antenna construction. Yes, from Leodio's Nea Smyrni. Very nice. From Panagiotis, I should make this bigger. I'm sorry. Right, how do I make this bigger? There you go. Excellent. So now I can read. Παναγιώτης Μπακλωρής, Φλούντζης Γεράσιμος, Γεωργία Παπαθεοδόρου, Κερασιά Μητυλινέου, Παναγιώτης Λεύκας, Κωνσταντίνος Περάκης, Άννα Σαββάδη, Ιουλία Σπασία Παπασάβα, Ανδριάννα Σιδέρη, and Κατερίνη Σκάρλα. And bear with me while I share their beautiful presentation.
Ως μέρος του προγράμματος RADIO, μια παγκόσμια πρωτοβουλία για τη ραδιοαστρονομία που απευθύνεται σε μαθητές και δασκάλους, επιλέξαμε μια από τις προτινόμενες εργασίες.
Το θέμα της εργασίας μας είναι η κατασκευή μιας απλής ραδιοαντένας με σκοπό την ανίχνευση των ραδιοκυμάτων που εκπέμπει ο ήλιος.
Ωραία. Πάρτε αυτό και πολύ θα το βοηθήσω αυτό εδώ. Μπράβο.
Το αεροπορικό βγάζει συλλέγει τα ραδιοκύματα που εκπέμπει ο ήλιος και τα συγκεντρώνει όλα σε ένα σημείο. Λειτουργεί ως ένας μαγνητικός τόπος για το φως.
Καλό διαμεταφέρου.
το σήμα του LNB στο πεδιόμετρο χωρίς απώλειες ή παρεμβολές.
Το πεδιόμετρο δείχνει την ένταση του σήματος με μία βελόνα, ώστε να ξέρουμε πότε ανιχνεύουμε τον ήλιο.
Η μπαταρία παρέχει την απαραίτητη ενέργεια για να λειτουργήσει το LNB και το πεδιόμετρο.
Το μεγαλύτερο πικ. Ναι, το κάτσε να το πω πιο ψηλά, χάνεται. Ναι, χάνεται. Εκεί είναι. Παίζει ρόλο, συγγνώμη γιατί δεν πάνω. Και ο ήλιος έχει βγει πολύ καλύτερα. Παίζει ρόλο ξεκάθαρα η γωνία, όπως καταλαβαίνετε, που είναι ο ήλιος αυτή τη στιγμή, γιατί έχει αρχίσει και δει. Αυτή η κλίση συγκεκριμένη τώρα έχουμε πετύχει το πικ. Το πάω λίγο πιο ψηλά να μου πείτε. Όχι, χάνει, το ακούω και εγώ. Και εδώ δυναμώνει. Μια χαρά είναι εδώ. Πιο κάτω να το πάω. Χαμηλό. Εδώ πρέπει. Εδώ.
Όπως είδαμε, η κατασκευή πραγματοποιήθηκε με απλά υλικά και οι μετρήσεις έδειξαν πως ο ήλιος εκπέμπει ισχυρό ρευματοκίνημα.
Η εργασία έδειξε ότι ακόμη και απλές σχολικές κατασκευές μπορούν να χρησιμοποιηθούν στη μελέτη φυσικών φαινομένων.
Amazing. I hope you enjoyed that. Excellent. I'm back. Excellent. Very nice. And I hope you make your own antennas. Okay. I would like to see how you change them, how you adopt. I'm sorry. My son just walked in. I'm a bit distracted. Come, say hi. You have to come close, 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 close. Very good. Excellent. Good. So let's move to the next presentation. I need view. Right, the next presentation is live by the first gymnasium of Rafina, observation of the apparent motion of the Pleiades in the sky using Stellarium, by Anastasios Anastasiou, Angelos Petassis, Ioannis Gomoulis. Are you here with us today? No. They're not here with us today. Is the first gymnasium of Rafina with us? No. Okay, so we will wait for, well, if they appear, we can show it later, okay? And we will move on. Or maybe I won't move on. Just give me a second. If I have the presentation, I will play it, but I don't have a video, I only have a PowerPoint, so we will move on to the next school. So the next school is, okay, that is amazing. It's a board game called Space Abyss, and it's the third gymnasium of Polychny with Ekaterina Theodoru, Areti Kechaya, and Savas Deligiorgis. I'm very excited to see this, so let's share it.
Hello to everybody.
Ah, wait, who is there? Ah,
I'm
you're here. Ah, you're here. Excellent. Hello, sorry, I didn't see you. How are you?
Fine. How are you?
I'm very good. Will you present your presentation for us, or do you want me to play the video for you?
No, I'll present the presentation for you.
Okay, yes, do it. Go ahead. Thank you.
We are pleased to represent the 3rd Junior High School of Polychny Thessaloniki in Greece. Our team consists of 3 members, Kechaya Areti, Deligiorgis Savas, and me, Katerina Theodoru. As part of the program Radio Galaxy Zoo Evolutionary Map of the Universe, we created a board game whose name is The Abyss of Space, and we are thrilled to demonstrate it to you all. It's a game which combines knowledge and entertainment. Don't miss the chance to give it a try. It was a pleasure being with you, and I truly thank you for your attention.
Sorry, I couldn't find the... All right, excellent. Very nice. I have a video from you. I will play it now. Yes? Yes. Excellent. Apologies for the stop. I need to get the video up. Ah, very nice. Excellent. So, let's play it.
Γεια σας, είμαι η Κατερίνα, είμαι η Αρετή, είμαι ο Σάββας και είμαστε ένα γκρουπ μαθητών του Τρίτου Γυμνασίου Πολύχνης στη Θεσσαλονίκη στην Ελλάδα και συμμετέχουμε στο πρόγραμμα Radio Galaxy Zoo Πλαστικού Αστεροσκοπία ΕΣΝΑ.
Στα πλαίσια αυτού του προγράμματος δημιουργήσαμε ένα τετραπέζιο παιχνίδι στο οποίο δώσαμε το όνομα «Η άξονα του διαστήματος», το οποίο αποτελείται από το ταμπλό που έχει ενσωματωμένο το πύραυλο, τα πιόνια, το ζάρι, τις κάρτες ερωτήσεων των πλανητών και τις κάρτες ερωτήσεων που είναι βασισμένες σε σεμινάρια που παρακολουθήσαμε. Επίσης, δεν θα μπορούσαν να λείπουν οι οδηγίες, που υπάρχουν και σε έντυπη αλλά και σε ψηφική μορφή, με το QR code που υπάρχει πάνω στο blog και με το link που σας αφήσουμε στην περιγραφή.
Πάνω στο blog υπάρχουν σχεδιασμένες οι διαδρομές που πρέπει να ακολουθήσει κάθε παίκτης για να φτάσει στον τελικό προορισμό που είναι ο πύραυλος. Και υπάρχουν 4 διαφορετικά χρώματα μέσα στους κύκλους. Το μπλε συμβολίζει τις ερωτήσεις του σεμινάριου που παρακολουθήσαμε. Οι κόκκινες συμβολίζουν τις ερωτήσεις από τους πλανήτες. Οι ροζ συμβολίζουν πως είσαι σε ένα ασφαλές μέρος και δεν συμβαίνει τίποτα, παίζει ο επόμενος παίκτης. Και άμα βρεθείς δυστυχώς σε ένα μαύρο κουτάκι, σημαίνει ότι βρέθηκες σε μια μαύρη τρύπα και πρέπει να γυρίσεις πίσω στην αφετηρία ανεξαρτήτως το που βρίσκεσαι.
Το παιχνίδι παίζεται με 2 έως 4 παίκτες και η ηλικία ατόμων είναι από 7 ετών πια. Και η αποδείξη είναι εξής. Ο πρώτος παίκτης ρίχνει το ζάρι. Τοποθετεί το πιάτο στην αντίστοιχη θέση και όπως βλέπουμε το πιάνο του παίκτη προσγειώθηκε σε μπλε κύκλο, οπότε ο αντίπαλος τραβάει την κάρτα ερωτήσεων του σεμιναρίου. Η ερώτηση έχει και τις 2 πιθανέστερες απαντήσεις και έχει κυκλωμένη τη σωστή απάντηση. Σε ποιες ζωδιαφυγές γίνεται εύκολη αναγνώριση από αλγόριθμους? Α. Στις απλές ζωδιαφυγές. Β. Στις πολύπλοκες ζωδιαφυγές.
Στις απλές.
Αν ο παίκτης απαντήσει σωστά, μένει εκεί που είναι και παίζει κανονικά στον επόμενο γύρο. Αν όμως ο παίκτης απαντήσει λάθος, χάνει τη σειρά του στον επόμενο γύρο. Σειρά του επόμενου. Όπως βλέπουμε, το πιόνι του παίκτη προσγειώθηκε σε κόκκινο κύκλο, οπότε ο αντίπαλος του τραβάει την κάρτα ερωτήσεων των πλανητών. Πριν του κάνει την ερώτηση,
πρέπει να πει στον παίκτη σε ποιο πλανήτη πρέπει να πάει. Ουρανό. Στον ουρανό. Τοποθετεί το πιόνι στον πλανήτη και μετά πρέπει να απαντήσει την ερώτηση. Έχει δακτύλους ο ουρανός? Ναι, αλλά είναι αχνότερη από τον χρόνο ή όχι? Είναι αχνότερη από τον χρόνο. Αν ο παίκτης απαντήσει σωστά στην ερώτηση, γυρίζει στη θέση που ήταν. Αν απαντήσει λάθος, μένει στον πλανήτη και στον επόμενο γύρο πρέπει να τον ξαναρωτήσουμε κάποια ερώτηση για κάποιον πλανήτη. Σειρά το επόμενο. Όπως βλέπουμε, το πιόνι του παίκτη προσγειώθηκε σε ροζ κύκλο, οπότε είναι σε safe zone ή αλλιώς ζώνη ασφαλείας και δεν απαντάει σε κάποια ερώτηση, είναι χάρη τη χειρά του. Είναι ασφαλής. Και τώρα δυστυχώς για την παίκτριά μας, το πιόνι της έπεσε σε μαύρο κύκλο, δηλαδή σε μαύρο κύκλο και πρέπει να πάρει ξανά από την αρχή. Αυτές είναι οι οδηγίες του παιχνιδιού και σκοπός του παιχνιδιού είναι να απαντήσουν οι παίκτες σωστά σε όσες περισσότερες ερωτήσεις μπορούν για να φτάσουν στον πύραυλο. Νικητής είναι ο παίκτης ο οποίος θα φτάσει πρώτος στον πύραυλο και θα εκτοξευθεί στο διάστημα. Μετά από αυτό το τραπέζι παιχνίδι που δημιουργήσαμε, μάθαμε να συνεργαζόμαστε και πήραμε βασικές γνώσεις αστρονομίας. Επίσης, γίναμε πολύ δημιουργικοί φτιάχνοντάς το. Αν σας άρεσε, κάντε like και subscribe!
Excellent. Amazing. Amazing. Excellent. 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 I want to play this game now. I want to play the game. So I will visit you and we play together.
Okay.
Yes. Well done. Congratulations. You should sell it on store.
We're thinking about it.
Yes. Yeah, that's great. How did you get the idea of making a board game? That's fantastic.
That's a good question. We love board games, so we wanted to create a board game so we can play it.
Okay, that's amazing. You created the best board game that I've seen.
Thank you.
Thank you very much. Congratulations to you and to everyone and to your teachers. And we're very happy that you shared this with us. Thank you very much. Good. Nice. So let's move on to the next school. Right. The next school is, you won't believe it, it's a construction of a radio antenna with simple materials. Okay, so this is the 4th Junior High School of Xanthi. I have to say, I'm very grateful that teachers and students chose this assignment. It's an honor to me that they chose it, and I'm glad to see that radio antennas are entering schools as an educational material. I'm very grateful for that. We are all very grateful for that. So, presenters Giorgos Mavridis, Dimitris Vidouras, Dimitris Diamandopoulos, and Ilias Kabakas. Let's find their presentation. Yes, Xanthis. And share it with you.
Next to Junior High School of Xanthi, we have constructed a helical radio antenna designed to detect radio waves emitted by the sun at the frequency of 1,420 megahertz. The helical type of antenna was chosen for directionality. The antenna was built using affordable, readily available materials. The antenna was constructed using simple single-core electrical wire and an aluminum plate as a ground plane. The properties of the helical antenna, like the diameter and the spacing of the helices, were determined by respective online tools. The signal was boosted by a low-noise amplifier and fed to the RTL software-defined radio version 4. The SDR is connected to a computer via USB port, and the radio signals are visualized using the SPR SARP software. Testing the radio wave reception with our setup, we observed an increase in the received signal strength when the antenna was pointed at the sun.
Very nice. Excellent. Very good idea. Great execution. Thank you very much. I'm back. As you see, the design is different. They don't all have to be. This is a very different design, bringing a very good result. They detect a continuum emission. So when they reach the sun, the whole spectrum is risen. Very good. Congratulations to the students and to the teachers. I would like to go and visit all your schools and you show me what you made. I think we should do that. I think I should do a tour across Greece and Pakistan and China. Good. Then the next presentation is about our planetary system, creation, structure, function, and life from Gymnasium of Philothei and Yuli Peristeri. So let me bring this up. Just a second and share it with you.
My name is Yuli Peristeri and I come from Greece, Athens. I will present you the solar system, our planetary system, creation, structure, life. What is a planetary system? Our planetary system is called the solar system and consists of the sun and all the celestial bodies that move around it. These include planets, satellites, moons, asteroids, and comets. The sun is located at the center of the solar system and is the main source of light and heat. How and why do the bodies move? Why is a system? We call it system because of the objects, planets, moons, don't move randomly in space. They work together in a specific way, held by the gravity of a central star. Gravitational balance. All bodies stay in orbit because the gravity of the star balances their motion. Every star can have its own planetary system. Our solar system is just one example. Planets of the solar system. There are 8 planets in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The first 4 are called terrestrial planets, and because they have a solid surface, while the others are gas giants. Earth is the only planet where we know that life exists. How was the solar system created? I present the nebular system theory. About 4.6 billion years ago, there was a large cloud of gas and dust called a nebula. Due to gravity, the nebula began to rotate and contract. The sun formed in the center, and the planets were created around it from small pieces of matter and gradually came together. What shape does the solar system have? How and why do the bodies move? The planets move around the sun in elliptical orbits, meaning orbits that resemble slightly flattened circles. The solar system does not have a simple geometric shape, but it shows organized and harmonious motion. Similarities. The idea of self-similarity. This motion can be connected to the idea of self-similarity. Self-similarity means that similar shapes appear in matter at different scales. A characteristic example is the spiral of Cecil. In a similar way, the motion of the planets can be managed as spiral-like similarities with the structure of the atom. An interesting similarity can also be observed in the microcosmos that is the atom. At the center of the atom is the nucleus, while electrons move around it, resembling the structure of solar system. Although this atom and the solar system operate under different physical laws, the similarity shows that nature repeats similar patterns at different scales. My solar system. The sun and the planets were designed to look realistic. The planets are arranged around the sun in the same order as in the real solar system, highlighting the elliptical orbits of the planets. The colors are realistic and based on photographs. The sides of the planets and the sun are not exactly to scale, so that everything could fit properly in the model. Is there life outside Earth in the solar system? Can the elliptical orbits and the shapes create life? Life exists only on Earth. However, there are places in the Earth, the solar system, where scientists believe that microbial life could exist. Mars. There is water ice and evidence of ice and water on its surface. Europa. Moon of Jupiter, covered with ice, with a liquid ocean underneath. Enceladus, moon of Saturn. It likely has an underground ocean which is ejected into space through geysers. Titan, moon of Saturn. It has lake of methane and ether, were very different form of life and considered possible. Although we have not yet discovered life outside Earth, the search continues with robots, satellites, and observation of exoplanets. The solar system is a mini version of the universe. From the motion of the planets to the structure of the atom, we observe similar patterns and shapes at the same scales. The space scientific study of planets, space, and smaller celestial bodies help us better understand the world around us and our planet in the universe, and perhaps even intervene in it. Thank you.
Excellent, excellent, amazing. Let's stop sharing. Congratulations, very nice presentation. I like the physics behind it very much. Excellent. And I like to see how different students approach the same topic in a different way. I love this. That's amazing. So let's move on to the next presentation. Let me find. Right, so we have 2 more videos and then questions if you have to, and then we will go to Faisal's very nice demonstration of Python. So now we have a video from the second high school of Vrilissia, okay? And the title is Continuous Q-band Signal Acquisition Using Satellite Receiver Hardware and Cloud Analytics. Very fancy, and it is, so wait for it. Presenters Παναγιώτης Αλέξανδρος Μπράβος, Χρήστος Μιχαλόπουλος, and Ioannis Stamboulidis. Let me find the presentation, and we are ready to go. Right, and share it with you. Is this the one? I guess. Yes, good.
Welcome to our presentation of continuous Ku-band signal acquisition. This project was a collaborative effort between students and a teacher at the second high school of Vrilissia. We set out to build a radio monitoring station using affordable everyday satellite equipment and a modern cloud computing.
The Ku band, which spans frequencies from 12 to 18 GHz, is essential for satellite TV, weather monitoring, and radar. Even the sun emits in this band. Professional equipment for this band is usually very expensive. Our aim was to use cheap and available hardware to make data collection accessible for our tight budget. We learned a lot of things in the process, as you will see in the following.
Our first setup was very simple. We used an 80 centimeter parabolic antenna and a low noise block connected to a handheld signal meter. By using a 12-voltage battery, we were able to move the equipment and observe how signal intensity peaked when pointing at the sun or catching reflections from nearby buildings. This is not, but it will be better to be able to record the signals, as we cannot watch the signal meter all day.
We hacked the signal meter a little, and we connected its output to an Arduino microcontroller. However, we quickly found out that the Arduino's built-in converter was too coarse, providing only 82 distinct digital values for our 0.4 volt signal range. It is like trying to take a high definition photo with a Minecraft camera. In order to see small details, we have to find a way to represent the signal with more precision.
To improve our precision, we added an external 16-bit analog to digital channel, the ADS1115. This allowed us to zoom in our signal. Now, instead of 82 steps, we can represent our signal with 2 to the 16th power steps, which is about 65,000 steps. This high resolution is critical because our signal has a lot of fluctuations. We also used an SD card module in order to record data in a text file. This allows us to use a PC to process the data.
In this photo, you can see our setup. In the lower right, you can see the signal meter. The two red wires carry the signal from the signal meter to the breadboard and the analog to digital converter, which is shown in the upper right. The data is then fed up to the Arduino, which is shown at the lower left. The SD card in the upper left is used by the Arduino to store the data.
Now with 24-hour dataset, we noticed a consistent pattern. The signal rises at sunset, peaks at midday, and cools off after sunset. We believe this is thermal drifting, where solar heating affects the electronics in the LNB, causing the recorded voltage to shift. We also observed peaks that are due to interference with cell phones, as well as sharp isolated peaks that may be due to aircraft or satellites.
Next, we added a Raspberry Pi to act as our internet gateway. We have connected it to the Arduino using a USB cable. It reads data from the Arduino and uses a simple Python script to upload it to the Adafruit.io cloud platform. So our station operates autonomously on the school terrace and can be monitored remotely. We retained the SD card module so as not to lose data during network out.
So now we have live data from the school roof. Our Adafruit.io dashboard is a real-time view of the signal. It features live gates, a raw data stream, and historical graphs that shows the signal trends from the last hour up to the previous 7 days. The data can be downloaded to our PC and then processed there.
At this point, it is worth to see some representative graphs. The signal depends on many factors such as the sun's position, temperature, precipitation, humidity, cloud coverage, and passing cloud edges. More notably, rain creates a very high terminating peaks in our data because water on the dish and in the air scatters and emits radio waves.
In conclusion, we successfully built a low-cost monitoring system capable of resolving both long-term and short-term variations. In the process, we learned a lot of things. First, precision is important, as the variations are subtle and in many scales. The use of the external ADC was very important. Second, the sky speaks. This means that rain, clouds, humidity, and temperature all influence our data. And third, we have learned how valuable is cloud integration. In the process, we have learned a lot about coding as well as the physics involved.
In the future, we plan to use 2 antennas in order to distinguish signal from noise. We also plan to add a weather station to investigate data correlation with meteorological data. Finally, as the next step in our investigation, we plan to use software-defined radio to perform spectral analysis of the signal.
Thank you for your attention.
Fantastic. Excellent. Well done to the students and the teachers. Congratulations. I'm very glad to see that a small idea has evolved and expanded, and you want to continue with it and take it to the next step and do interferometry. Yes. and also monitor the weather. I mean, what can I say? Congratulations. Excellent. Very nice. I think we have one more school before we go to Faisal. So this is the third gymnasium of Amarousion. And we have another board game, the Space Conqueror board game. Okay, that sounds amazing. I'm already hooked by Nefeli Balafa, Eleftherios Kalandranis, Vasiliki Terzi, and Antonios Drakopoulos. Let me find their presentation. And share it with you. Wait. Good.
Hello, we are the Astronomy Club of the Third Junior High School of Marousi. I'm the director of the school, Stephania Panes, and I would like to present to you the 4 students of the club, which all of them are students of the last class of our school, Lefteris, Nefeli, Celia, and Adonis. We decided to start the club based on the webinars of the Radio Science team, which we attended. The project we implemented is a board game on the theme of astronomy. We try to deal with a topic that does not require special knowledge of physics or mathematics, but rather encyclopedic knowledge. And now the students of the club will present the subject they worked on in relation to the game.
Hello, I'm Nefeli Balafa. I was in charge of the rules of our game. The game that we created is named Space Conqueror. The game includes 2 dice, one with various question categories and another with the numbers 0, 1, -1, a board of 200 cards of 4 categories and 5 playing pieces. The youngest player goes first. They roll the dice with the numbers, and if they get 0, they stay in the same position and they move based on what the dice shows. There are 4 categories of cards: mythology, science, history, movies. After the player rolls the dice, if they did not get 0, they must answer a question. To determine the category of the question, they roll the category card. Then they choose a card without seeing the questions, and another player reads the question from the card they chose by the active player. Each card has 4 possible answers, A, B, C, D. The player chooses one of them, and the player asking the question tells them whether it is correct. The goal of the game is for the players, after leaving Earth, to conquer as many planets as possible. When a player is the first to reach a planet, no other player can conquer the planet. Along the route, there are obstacles like black holes, and if the player lands on a black hole or a wormhole, they must answer 2 questions correctly in order to move 1 step forward.
Hello, I'm Anton Yakovlos. I was in charge of creating the questions of the game. There are 200 questions divided in 4 different categories. Each category consists of 50 questions. The first category is space history. The second one is space mythology. The third one is space movies, and the fourth and last one is space science. The reason why we chose to use 4 different categories is because we thought that if we use only one category, it would be boring for the people playing. So we wanted to create something much more fun for the players, and that not only focuses only on one category. So that's why we thought about that.
Hi, I'm Celia Terzi, and I designed the logo for our board game. I designed a character that does not have a gender, but I wanted to show the power-hungry people who want to keep on conquering things and they don't look back on what they already have. Also, the circle that I have made around the logo is supposed to represent the compass. Then I designed the back of our cards. And lastly, I painted the dice that the first 3D printed.
Hello, I'm Francesco Amarans. I have made this 3D printed on my 3D printer. Also, I have 3D printed the box that we will shoot the dice. I have made the board of the game, which includes the Earth, which is the starter point. It has 2 real planets, Mars and Mercury. Also, it has 3 imaginary planets of my imagination.
Thank you very much. We hope that someday you can play our board game and other people in the world.
Thank you.
Thank you. Bye-bye.
Bye.
Bye.
See you guys.
Excellent, excellent. I think we should make a board game club and meet and play all these beautiful board games. Fantastic, inspirational, and I really like the idea of having 4 different categories. Yes, make it exciting and 200 questions. Amazing. Excellent. Excellent. Right. Yes, yes. After the workshop, we play. We play these games. We meet and play. Right. So this was the end of the first session. Are there any quick questions? There is one question on YouTube, but I don't know about a radar for America. I'm sorry, I saw your question before. I don't know what you're talking about, but thank you. Good. So we will move to Faisal without further ado, who is going to show us a Python demonstration. Faisal, are you there? Yes. Excellent.
Can you see my screen?
We can see your screen, yes.
Okay.
We
So can you see the Google search bar?
Yes.
Okay. So how to start the Google Colab. Let's start from the basic. So once you search the Google Colab, you will get this URL, colab.research.google.com. You can simply click it. And you just need to be logged in with your Gmail account to start the workbooks. So I'm starting from scratch so that you can have an idea about how to start the process instead of figuring out spending time on it. And then you will have this interface where you can either open the existing notebooks which you have created or you have uploaded. You can upload ones, but let's start a new notebook. So let me explain what I'm going to cover in this workshop. I will first introduce you to the environment, which I'm doing at the moment. And after introducing to you with the environment, I will introduce some basic concepts. There are 3 workbooks I have prepared for you. One will be introduced, we will complete the 1 workbook in this workshop. Then, depending on the time, I will introduce the concepts in the second and third notebooks, so that you can continue your learning experience after the workshop as well. And they have all the theory you need for radio astronomy. The problems you are going to solve, you have the related theory as well there, and the code as well. You can run it, you can play with it and stuff like that. So first we have this environment where you have code places, you have code sections, code cells, you can say. So you can simply write print, basic example, print, let's say, which we all do, hello world. And if we do it, it will run it. Okay, let me say I have opened too many sessions, so I just close some of them. Which one are not necessary? This one is not necessary. Forget now. Okay, still too many sessions. Okay, I will introduce here. I will add code here. Print. Hello world. So it has given you the output. Now, this is just a text-based output. You can have like this. This is the text-based output. The simple print command it can print text, it can print numbers. So what you can also do is you can have calculations there. So in the basic maths operation, let's start by adding 2 numbers. So we can have this in the print statement as well. So if I do 2 plus 3, and the rest of this is hello world. \n is computing is the new line. So if we have \n, it will have new line. And then if we have \t, it has tab, some spaces. So let's see their effect as well, and then see how the numbers can be added. So you can see hello world, we have \n in the same printed statement. And then we have \t tab. Python is fun. Hopefully it's fun. And then this is without any backslash or stuff, simple text. And then some math calculations. 2 plus 3, 5. Now let's see some of the other operations which we can do, like with Python. Okay, so now another concept which is a very important concept is variables. In maths, we have used variables, or we write a is equals to b, or a is equals to 5, b is equals to 6, or we can have a plus b whole square formula. We use variables in a lot of algebra problems and other problems, calculus and stuff like that. So simple. In programming, we also need some variables to store the information. That information can be text, can be a number. Numbers can be of different types, like this is an integer, and you can have 9.5. This is a decimal, which we call float in Python. So there are different types of numbers as well. We will just check them as well. And then we have, we can assign values, we can print them with some text, like we have some fixed text, and then comma, we have added a variable. There are different ways to do that as well, but we will stick to the basic for now. And then we can print numbers similarly. We can one thing which you will see, if you are familiar with other programming languages like C or other, you will see that you have to define the data types in them, like if they are string or text or integer numbers or floating point numbers, float numbers. But in Python, it detects automatically and performs the operations. So if we run that, this will show the results, and you can see it has placed my name is, and then picked Wafa, and my name is Wafa. My age 9. I am dash years old, 9 years old. So it's not, of course, it's not me. Wafa was one of the kids in the cohort, I think cohort 2 or cohort 1. So she wanted me to use her name and age. So I thought, let's continue with it. And her pet name is Ada. So my pet name is variable pet name, comma, and then the rest of the sentence, Ada is a nice pet. So we have this. So if I had added something else, Ada is a pet, Ada eats, I don't know, sweets. I don't know what's pet eat. Okay, so whatever we want to write or extend, or we can do that. Now similarly, we now go a bit deeper into different kinds of data in the calculate. What we are mainly concerned are the numbers usually in the Python calculation, but just for the sake of learning, we can introduce some other aspect as well. So we have also, like in some logics, we can have Boolean logic as well. Boolean algebra. Boolean is like true, false. You can have logic. Sometimes you take decisions. Okay, if this is the case, we will do this. Or if we have switch, like is it on, is it off? You have this type of logic. You need Boolean. We have 0-1 operations as well in binary operations. We use Boolean. We can use true, false in Boolean operations as well. So here we have different types demonstrated. This is a string text, Luna, name, basically age. This is an integer. And then height, this is a floating point number or decimal, a Boolean, which is true, false, binary logic. And this, now let's say like we print them and check their types. This is also a floating number. So let's check their types first. So to check the type, we have a function type. It automatically detects the type of the data you have entered. So this will help you in knowing what is being entered, and you can apply different checks. But that's strict. You can, depending on the requirements. Sometimes you need the types, type checks. So we run it, and we see that Luna is there. Luna's type is string. Age is 12. 12's type is integer. Is student true? It's a decision true, and then it's false. Now I ask you a question to you. If I clear selected output, if I do this, what will be the type? Anyone would like to tell me? Any student who would like to tell me what will be the type of a school class now? If I remove the decimal point. Okay, I can tell you. Wait, somebody's writing. Okay. Nobody's answer, so I'll answer that. It will be integer. The type has changed. It has automatically detected that the type has changed, and it will, reduce it and display it to you. And you can see that there is a class written before it. Basically, it's the data structure which has defined the language itself. It's in the form of classes and abstract types. So it's a different concept, but you only need to be considered with the what is written in the types. So integer. Now in mathematics, in the scientific calculations, we of course use floating point numbers for accuracy. A good thing is in Python 3, it automatically converts operations like division into decimals. In the older version of Pythons, we had to add dot explicitly so that it will return floating numbers. Otherwise, it would have truncated it to integers. But now, in the latest Pythons, in fact, for quite some time, it has been doing it automatically. So yeah, so I was doing some mathematical operations, basic maths operations. We have addition. So addition has the same sign as in the maths, subtraction as well. Multiplication has asterisk sign. It's a bit different. It could have been x, but it would again, using x as a variable, it would have been problem. So the choice is made to use asterisks. And division again, as I said, this division mean this will be numerator and this will be denominator. So you can have complex examples as well. You can combine the operations. You can have basically it usually follows BODMAS and PEMDAS. It always follows BODMAS and PEMDAS. So we have studied in the school as well. You might have studied in your curriculum already. I think most of the students are from 5th grade and above. So there's a good chance everybody is familiar with that. So in scientific calculations, that we deal with sometimes large numbers, sometimes small numbers, sometimes we have different operations. Another important operation is this 10 multiply 10 steric 9. This means 10 to the power 9, exponent 9. So that's another way, another operation which you can play with. So let's say we want to test the addition. We have this as fifth now. We first write it in the billion in the usual form. If you want to add 150 billion, then we will have to add 9 zeros. and 200 billion, we again have to have 9 zeros after 200. Then simply add it. So, and then, there's another way of printing. You can have simple printing, comma, and any variable, or you can add variables within the text without needing a comma. There's another way. You can use this expression format, which you can use is F from the before the text. And once you do that, then you can simply pass the variable between the text within the curly brackets. So that's just another way of representing what we want to do. So again, there's a subtraction operation. Let's see first addition and subtraction. So we have addition and subtraction done. Some of the stuff I'm telling it from the basics, assuming that some of the people won't know anything about Python. So I'm going a bit slow and going from the basics. So yeah, now comes some slightly, and then we have division operation there as well. Let's say we have example like total fuel in liters and have mass. We have sent us 4 rovers on some place and we want to divide the fuel. So what can we do? We simply, let's say, total fuel in liters divided by number of rovers. So we have got 125 liters there. After dividing, it has already automatically added the decimal number, even though it's an exact division without any remainder or without any decimal value, any value after the decimal point, but still it has added a decimal 0, showing that division operation automatically converts any number into floating operations. Now, a concept which hopefully you are all familiar is the concept of relationship between speed, wavelength, and frequency. So if we talk about the speed of light, like we are doing radio astronomy, we are dealing with 2 things, frequency and waves. We have longer wavelengths in radio astronomy and lower frequency as compared to, say, gamma rays, infrared, visible light. So if we want to have higher the frequency, lower the wavelength, lower the frequency, higher the wavelength. And how that relation is managed is via velocity or speed basically. So you have lambda multiplied by f is the relationship. Lambda is the wavelength. It can be in meters, centimeters, and so on, kilometers. And frequency, it's basically hertz or per second. So the idea is that wavelength is basically, if you talk about a wave, you have peak, you have valley. So the distance between 2 peaks is called a wavelength. And what's the frequency? Frequency is simply how many complete cycles can pass within 1 second from some particular point. So here we can see from between 0 to 1, we have 2 cycles. So the frequency is 2 hertz. Similarly, for the next second, we have 2 cycles. Now, another concept here is amplitude. 1 to 0. That means amplitude is from the central, from it's the height of the wave. So like a building has a height, wave has a height. So we have this 1 as the amplitude. Now, we see we use this concept in a calculation. To basically we can plot it as well. First, we understand how we can study the relationship between wavelengths and frequencies. So in radio astronomy, a very common frequency is about 1.4 gigahertz or 1420.4 megahertz. We can have it, or about 1.4 gigahertz. It's the a lot of major surveys from by NRADIIO or other radio astronomy community, even on ASCAP, will be on 1.4 gigahertz, 21 centimeter, basically the wavelength. This is because of the hydrogen gas. This is a famous hydrogen line. It basically represents the abundance of matter as well in some place. So that's a very physics astronomy based connection there. So if you want to, let's say, convert frequency into wavelength or wavelength into frequency, so how can we do this mathematically? So we have this formula C is equals to lambda f. If we know speed of light, although it's a bit approximation, but just for this simple case, we can do that. And if we want to know lambda, if we know frequency, we can calculate lambda simply by taking f there, c divided by frequency. So if we have lambda, we can simply take lambda there, c divided by lambda will be frequency. Here we want to know wavelength. Wavelength is equal to c divided by frequency. So we have speed of light, frequency which we have, and then we want to know we have in megahertz, so we know that we should know what we are calculating in, and then we will get the answer in meters. If we have use some other units, megahertz instead of we can use gigahertz, then we would have gotten the results in the similar lengths. So let's see now. Run it. The wavelength of the hydrogen line is 0.2112 meters, or basically it is 21 centimeters. Centi means divided, means a hundredth. So if you want to convert meters into centimeters, we can convert meter multiply by 100. So 0.21 will go to 21. That will be centimeters. This is a very famous wavelength in astronomy. Radio astronomy and you can both in radio continuum astronomy or spectral line surveys. In both cases, it is very famous. Now, other thing, if we want to plot some frequencies and wavelengths, we want to plot some wave or simulate some wave. What are the essential parts which we use? We use simple equation for wave. Usually we have amplitude multiplied by sine. Here we are using a package NumPy. This is a mathematical library. It has a lot of mathematical functions like sine, cosine, exponentials, exp, and a lot of other stuff as well. Arrays, data structures, which are useful in Python. Mathematical operations. Then this library is matplotlib. This is a plotting library. A library frequently used for plotting. And what we are using here is as PLT, as NP. This is called aliasing. We use aliasing or nickname because we don't want to write the full name every time we use a related function. For example, here we have want to initiate 500 data points linear space, and let's say for the sake of before going to full example, let's break it into smaller ones. Although it automatically gives a lot of hints, let's just try to let's say try to write everything yourself so that you can have a good practice of writing. I have just shifted to a German keyboard, and my software is still US, so sometimes I will do typing mistakes. np.linspace, starting from 0, let's say and I just said 10 samples so that we can visualize them. Print X, you have this. So it has gone from 0 to 1, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 0, starting from 0 to 10, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 samples. You have divided numbers between 0 to 1 into 10, and then you got 10 numbers. Similarly, you can let's say go to 9. Now you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are more understandable. So using this concept, we can have, let's say, time is divided between, in 500 points and starting from 0 and going up to 1. So we are getting between 1 second, we are, creating a wave. Now, if you want to have 5 hertz, so we need 5 cycles. And first, we need to define what is meant by 1 cycle. 1 cycle is basically a circle, because if you look at the wave, I'll show you how the wave looks like. It is kind of circular in nature, cyclical or circular, because if we combine them, it will, have a circular type of thing. That's the so if we go, where is it? Yeah. So we have 2 pi to have a complete circle, and then we want 5 hertz. So we have time between 0 to 1. So we want 5 cycles in that time. So we will 5 hertz. Amplitude, at the moment we are using unit amplitude, that is 1. So we won't need to write it. But I will show you how we can, change it and see what it does. And then we simply plot t on x-axis. This is the x-axis value. PLT dot plot is plotting for plotting. And wave is the data point we want to plot. So it's on the y-axis. And we say we want color blue. And we assign a title: simulated radio wave, time, seconds, amplitude, and grid will help us in reading the data properly. I will show you what does it do. And plt.show basically displays your plot. So now we see. So we have gone from 0 to 1. We have 5 cycles. This is 1 cycle. This point to this point is 1 cycle, 2 cycles, 3 cycles, 4 and 5. And we can see the amplitude has gone to 1 because we haven't assigned anything. So it is going to 1. So let's say make it interesting and make it 2. And see. Amplitude increased to 2. Now make it a bit more interesting and change the frequency to, let's say, 3. What will do? It has reduced the number of cycles within the same time frame. Now we can make another change. Now we are seeing that it means that we want 3 complete circles in this 0 to 1 time frame. We can say we want half circles. So half circle will be simply pi. We can make it pi. So we have 3 half circles or half circles. Okay. And if we can further reduce it. So we have this. So there are different ways you can, there are different parameters you can use to define your wave and plot your wave. I will just store it to the original so that we can. Although I have given the notebooks to Eleni, she will forward to you. So these are the simple waves concept. How much time do I have, Eleni?
So how much time? Let me check. Sorry, I'm on a different screen. Where are you? So you have 250. You have 15 minutes. Yes.
Nice. So we can cover some more concepts as well. Okay. So, and now there are different division types as well. So we have studied the standard division. So there is another, okay. So there is another type, which is the integer division, where you are only interested in knowing the integer output. Let's say if I want to divide 15 by 7, I don't want the decimal values, so I will use double slash and it will give me this one. So let's try it out. Okay, let's go there. And let's see the difference between this and let's have some other number here, 40. And we want to use Q is equals to okay. So you can see the difference. The standard deviation has given us the accurate result. The quotient integer division has only given us the quotient. But so in our usual calculations, astronomical calculations, we will use the standard division so that we can have accurate answers. Okay, so that's the main point. Okay, now another concept is logical operations. We can have a loop iterative operations. So let me just pull them just in case I will share it. So in the workbook, okay. So okay, so I'll just so that I can cover some of the concepts we have, and you can try astronomical. Okay. So in the workbooks, you will see some of the science explained as well. So like the astronomical unit and then the calculations related to the astronomical units. I will suggest you can try to use it the same concepts. The new concept here is the list concept. List is basically collection of the data in Python. A good thing is that you can have a list with different types. You don't need to define the type again like variables. We don't need to define if it's a string list or a list of floating point numbers. So here we have list of planet names and then their distances from sun in astronomical unit. You can see one is for the Earth. Now, one thing about list is that it starts from 0 and goes to n-1 index. So if we have 8 planets, so we have 8 planets in our solar system. Unless you are from an older generation, where we used to learn that there are 9 planets, but we dropped Pluto a few years ago. I don't know, it's been a long time, I think. And now Pluto is a dwarf planet. So in the planets list, we don't include it. So we have 8 planets. If we define a list, the list will go from 0 to 1. So in this case, if I have index 0, then I will have a first value of Mercury. If I have index 2, then it will be basically third value, which is Earth. And since I want to match names with distances, so I will have matching names with 0, Mercury being 0.39 astronomical units away from Sun. Earth being the third planet, its distance is about 149.5 million kilometers from Sun. we call it 1 astronomical unit. It's an average value. It's not an it's not a fixed value. It's an average value. Earth passes elliptical, and the distance varies from the sun. And similar, the last one is Neptune. It is way far away from our position. It's 30 astronomical units away from sun, and so about 29.1 from us. So it's very far away. And similarly, if you want to access the last element, there are two options. One is if we know the size of the list, that is 8 elements, then we can simply write 7 because n minus 1 value, or we can write -1. So it will give the same result to us. I suggest run it yourself, change the code yourself, similar with the wave code I've just showed you. Okay. Okay, I have to close some. Close. Some of them needs to be closed. Other sessions, okay. See, once we want to complete it, we can terminate other sessions. Just reload it. So you have to manage the memory you are using as well. Since I have been using a lot of examples, it was consuming it. Yeah. So it's not working. It's not working. So yeah. So we have again the names of the planets and the corresponding distance. And then what we have learned about the indexes. 0th index, we have Mercury. Index number 2, which is the value number 3. We have Earth. Again, distance of the index number 2 and value number 3 is 1, basically Earth's astronomical unit distance. And the last name of the planet, we have Neptune. Another similar concept you will encounter is arrays, which is similar to lists, but more optimized for mathematical operations, which is using NumPy. You can explore it. I just mentioned some of the things in the notebook so that you can try it out. Another interesting concept I have explained is the for loop. There are other type of loops as well, while, do while stuff, but just for introducing students to the concept of iteration, I have added loops. Loops are needed when you don't want to repeat the same operation. Let's say I want to print 5 number. One way is to write print 1, print 2, print 3. Another way is simply run a loop. And the loop in Python starts with the keyword for. I in range. Range starts from if we don't want to write the starting point and write the simply one value, it will assume that that value is the ending value and the starting value is 0. But if you want to start from 1 and want to go to 5 and we have n is equal to 5, then we write n plus 1. So again, like indexes of list, the last value is usually n minus 1. So if we have given n, it would have printed till 4. So you want to print the last value, we have n plus 1 and it will 5. Similarly, if you want to, this can be useful in some, let's say, mathematical operations. If you want to have, so if you want to have, but print the total sum or something like that, then it can you can either add 1 plus 2 plus 3 plus 4, but what about if you have n is equals to 100? It will be a ridiculous operation. So you can simply run this logic and print it. It will sum all the numbers in the loop simply by iterating from 1 to n plus 1 and adding the number. This is called the iterative variable. So it will add the current number into the bucket, into the storage value we have. So you can simply run these operations. The reason I'm explaining this example, I will explain to you in how they can combine in a very good mathematical in a useful calculation operations. So and now is the logical operation. So we have seen if we want to have, let's say, decision making based on types of something or some conditions, we can use conditionals. If else is a very useful condition, and if you have multiple conditions, we can use if else. Another thing you can see is the use of double equal to signs. This is for the comparison operator. operation. Single is equal to means assigning a value, A is equals to 5. But double is comparison. Similarly, here you can see, so now understand this slightly a bit complicated. We have planets types. We have already defined names and distances, now define types as well. The first 4 planets are called terrestrial planets. Mercury, Venus, Earth, Mars are called terrestrial planets. Then the second one, Saturn and Jupiter, are called gas giants. Then Uranus and Neptune, they are called ice giants, basically. So let's say, first, before going into committing ourselves into any operation, we will check if all these 3 lists are of same length. For that, we will use length operator, because if they are not in the same size, we won't be able to associate name with distances and their types. So we compare the length of the names list with the length of the distance list and the length of the planet types list. And if it is not comparison, if it returns false, this comparison operator basically returns true or false Boolean. So if it is true, then it will return true, it matches. If it doesn't match, then it returns false. So if all 3 don't match, then it will give an error. And if it is not the case, if it is not the failure, then it will proceed. To proceed, we'll see another operation zip. What it is doing, it is combining these 3 lists into a single collection, and then mapping name with distance and planets. That's why we needed all of them in this of the same length. So we have name, distance, and types. And we can iterate through them as well, like we are iterating through the values. So we have for name, distance, and planet type in. We can assign any name to these variables, but we are using the names which are look more logical. And then use the zip function so that we can map these 3 different lists into one, and once we iterate them one by one, these 3 will map with the corresponding indexes. For the first, we will have Mercury's distance, and planet type. So we can see that this is how it is being printed. Planet Mercury, distance from the sun 0.39 astronomical unit, type terrestrial. And then based on that, we are taking a decision. If it's a terrestrial planet, then it will write the definition. This is a rocky inner planet. Okay. So how it is going to work with the complete list. We run it, it's working. It is taking decision like for Venus, again, it's a terrestrial, it's a rocky inner planet because it's a terrestrial planet, type terrestrial. But Jupiter and Saturn, they are gas giants. So this is a large outer gas giant. For Uranus and Neptune, this is a large outer ice giant because they have these different types. So these you can do. And similarly, there are the slightly more advanced calculations, not slightly advanced, related to radio astronomy. We have done, in this notebook, which you can explore. And then there's an example which you can try it out as well. It's called CSV file, comma separated values. Comma separated values are standard way of dealing with data along with FITS files and DAT files and other format, but CSV is also a very common format you will encounter. So I have added the example which you can test it out. For that, first is the example of creating CSV files. So we have all these 3 lists declared above, and we can use planet data and creating this CSV file. So if you run it, and if you go into the data pane, you can see a CSV file there. You can download it for your further analysis as well. Let's say download it and see how it looks like. I want to open with, we can open with Excel, but Excel won't tell you the exact structure. A notepad will tell you how this looks like. You can see comma. You have column names, comma, value names, comma. That's why we call comma separated values, CSV. So you have that. And then what it is doing, it is combining the lists. It is appending the data from each item. It is iterating again. First, it has created an empty data list, which will be basically a list of it will be a list of lists as well, combination of them. And then in each data row, we are adding for I in range. We can use planet names, planet distance, anything. Basically, we just need to match the length of the planets list. So can be and since name, distance, and types all have the same length, we could have used any one. And then append on the same index we have on each index. On zero, let's say on 0, we have planet Mercury. Mercury's distance, because we are passing an index first starting from 0. Again, we haven't provided a starting point 1 like the last time, so it will start from 0, which is what we need. And it will go to n-1. Length will be 8, but it will go to n-1 because we have not added +1. And we need that in the list because list follows the similar convention as range. It starts from 0, goes to n-1 range. That's why we don't need to specify the starting point, and when we don't need to add the +1. So it will assign all the items with the corresponding planet name, distance, and types, and then save it in a. We can assign header and then file name, and then the real operation will happen. We will open a file. CSV file name, if I give the file name, we want to do the write operation. W is the write operation. New line, we don't want anything to be present in the new line. We want to keep it empty. That's why an empty character is passed. As again, we provide the aliasing. It will give so that we can have a short name to write. And then CSV writers, first you start a CSV.writer CSV file, pass the CSV file, CSV file there, and then the writer will write the right row. First row, we just want a single row. That first single row is the header row, and then write rows. Then in the rows, we can simply pass the whole data we created by combining 3 lists. And then you have successfully created a file which looks like this, and I've showed you how it looks like. I'll just show you again. These are our headers. These are our planet's data, and you can see it has mapped them correctly one by one. And now, if you want to read the CSV file, so we have a very useful package. I have added links as well. Pandas. Pandas is a very standard data sciences package. It is a very useful tool for data analysis, not just in Python, but in finance industry, finance, or any other a lot of industries. It is the use. Okay. So we have already CSV underscore file name is already in its memory. If it's not in the memory, because since it's the same notebook, we don't need to assign it separately. You can see that if I hover over it, it is showing me planets.csv already, because we already have created it using the code above. Now we import pandas as PD again. In your laptops, when you will set the environment, you may need to install pandas. Here, a lot of the packages are already installed. That's why the notebook is a very good way to learn Python coding. So you have import the pandas package and read the file name using the file name read underscore CSV. There are other read operations as well, depending on the type. It can even connect with the database, but we are using the CSV file, the CSV, and then header. We want to print just the header files. So we have df.columns, which says the header, but if we want to print the whole data frame, df is data frame. It is like an Excel type of structure, and it gives a very good idea about things. So we have this. So again, this is since these were like these 3 notebooks I created were for like sessions spanning from 1 to 2 hours. What you can do is like go check those notebooks. They are step-by-step notebooks, and run the code and see and try to make changes in the code. and see what it does. So hopefully you at least you got enough introduction of the Google Colab environment and the language of Python itself to get a jump start, because it's a very short time. In short time we can't cover a lot of deep topics, but I try to cover essence for jump start. Hopefully that will be helpful.
That's great. Thank you very much, Faisal. I think it's a very good introduction from like completely basic things and taking it a step up. And I hope you inspire more of the students to try this and start coding. That would be great. We will share your Jupyter notebooks so people can try them. Thank you very much. So,
thank you.
Let's move on to the next part of the presentations from schools from Greece. We will start with, just let me see my notes, from the Athens College, the Hellenic American Educational Foundation. The topic is Suncatcher, and the presenter is Nectarios Giannakis. I think Nectarios is here. Would you like to say hi?
Yes, hello. It's a
Hello,
pleasure to be here.
Nectarie.
Thank you very much to the whole radio team and for making this event possible.
Thank you very much for participating, and let's watch your video.
Thank you. Thank you.
Yes. Fantastic. Oh, okay, good. Fantastic. Thank you very much.
You're welcome.
You detected some things there. Excellent. Keep
Thank you.
keep working hard, and yeah, that's amazing. That's great. So let's move on to the next one. Right, another video. Okay, this is about galaxies. Yes, we love galaxies. So, from the experimental upper high school of Chania, Galaxies of the Universe, from Ioannis Panoudakis, Ioannis Benakis, George Nikolouzakis, Elina Liodaki, Konstantina Ridjaki. Let me find the video and share it with you. Yes, it's the one. And let's share it.
Galaxies of the Universe. Presentation summary. Introduction. What is the universe? The universe is the sum of everything that exists, all space, time, matter, energy, and the physical laws that govern them. It includes everything from tiny subatomic particles to vast galaxies and the space between them. According to modern scientific observations from sources such as NASA and ESA, the universe consists of common matter, about 5%, dark matter, about 27%, dark energy, about 68%. How can we observe it? We observe the universe by using technology to see beyond the limitation of our eyes. The main ways are as follows. 1. Telescopes. They are collecting light or other forms of radiation to create images. Ground-based telescopes, space telescopes. 2. The electromagnetic spectrum. The universe emits energy that we cannot see with naked eye. Radio telescopes, X-rays and gamma rays. 3. Spectroscopy. 4. Gravitational waves. 5. Space missions. Is there a visible and invisible universe? Visible is the sphere around us, from which light has had time to reach Earth in the 13.8 billion years that the universe has existed. Invisible is the part of the universe that is so far away that light has not reached yet, due to the expansions of space when we never see this part. 2. The spectrum that the eye cannot see. Many things are invisible to the human eye, but visible to our instruments. For example, the James Webb Telescope sees the infrared revealing stars hidden behind dense clouds of dust that ordinary telescopes are unable to detect. How can we study and understand the universe? The study and understanding of the universe is achieved through the combination of scientific observations, mathematical models, and cutting-edge technology. The main pillars of this process are 1. Observation of the electromagnetic spectrum, optical telescopes, radio telescopes, X-ray and gamma ray. 2. Spectroscopy. 3. Multi-messenger astronomy. 4. Theoretical cosmology and simulations. 5. Space missions. Methodology. Analysis. The photo on the left shows two galaxies that are tails. The tail on the right is faint, diffuse, irregular and fluffy, while the tail on the left is quite clear and sharp and also curved, irregular. These galaxies are curved. There is a clearly defined bright core. The image shows a radio galaxy with a complex and non-linear morphology. In radio observations, the emission shows a characteristic sigmoid pattern with the areas curving in opposite directions above and below the central core. The central core is clearly visible as a strong and compact emission source aligned with the observed galaxy. The extended structures show thick, diffuse, and irregular permanent emission regions best represented as plumes. The superpositions of the radio isoluminosity curves over the field of view reveals the close relationship between the core and the areas. Discussion of the results. The morphological characteristics of the radio areas indicate the presence of an active galactic nucleus which powered by a supermassive black hole. The symmetric bending of the regions above and below the nucleus differentiates the system from cases where the morphology is determined exclusively by external environmental pressures. In conclusion, the dominant physical process is the precession of the supermassive black hole in the central nucleus, with the environment influencing the detailed shape and evolution of the regions. This combined effect satisfactorily explains the complex non-linear morphology of the system. The observed spathe-shaped morphology is interpreted as a strong indication of the precession of the central supermassive black object. The diffuse nature of the plumes reinforces the scenario of a denser environment possible at clusters of galaxies where the jets lose their coherence, expand, and mix with the interstellar gas. Overall, the combination of a bright central core, spathe-shaped curvature, and diffuse areas argues in favor of classifying the object as a gist structure, where the dominant physical process is the precession of the central engine, with the environment playing a secondary but decisive role in the morphological evolution of the system. Conclusion. We study the galaxies enclosed by supermassive black holes because studying space is interesting.
Excellent, fantastic. Right, we're raising the bar, We're raising the bar, as we say. And I'm glad to see that the students have chosen our citizen science project because these were examples from Radio Galaxy Zoo EMU. The first object are the dancing ghosts, two galaxies that interact with each other, and the second is a bent radio source. A very good explanation and very high level. Thank you very much. Right, let's move on. Let me see my notes. We have the topic is the radio sun, again from the experimental upper high school of Chania, presented by Mariangela Kambouraki, Ioannis Berbadidis, Konstantinos Kakabelakis, Maria Anastasaki, Paraskevi Kotsifaki. Apologies for making mistakes. I am getting old and I don't see very well. So, right, let me share the presentation. Okay, this one. Radio Sun, very good. Let's not make mistakes. Mm-hmm.
Experimental channel lithium of honey, working on the radio program, the radio sun. Does the sun produce radio waves? The answer is yes, but it is the strongest and the most stable source of radio waves known to man. Due to the proximity of our star, you can use radio waves to tell us the temperature of the sun. Our mission is to show you what temperature these images are by using the distribution of radio wave brightness temperatures as a function of its temperature. Introduction. What is the sun? The sun is the central star of our solar system. It is a huge, almost perfect ball of plasma, held in a spherical shape by its own gravity. The energy it produces is vital to life on Earth, providing the light and heat we need. What the sun does nuclear fusion? The sun main function is to produce energy through nuclear fusion at its core. In the core, the temperature reaches about 50 times 10 to the 16th Kelvin and the pressure is extremely high. These conditions allow the function with hydrogen atoms into helium atoms. The proton-proton chain. The dominant progress is the proton-proton chain where four protons hydrogen nuclei fuse to form a helium nucleus, releasing energy according to Einstein's famous equation E equals m times c squared. Energy transfer. The energy produced is transferred to the outer layers of the sun through two main mechanisms, radiation in the radiative zone and convection in the convective zone. Corona. The sun's outer atmosphere, which extends millions of kilometers into space, surprisingly linked the temperature were sourced to over 1 times 10 to the 16th Kelvin.
What are radio waves? Radio waves are invisible electromagnetic waves with very low frequencies, 3 Hz to 300 GHz, part of the broader electromagnetic spectrum, widely used for wireless communications, radio, television, mobile telephony, Wi-Fi, as well as in medical applications and astronomy. They propagate at the speed of light and transfer energy without breaking chemical bonds in matter. Their main features: 1. Frequency and wavelength. They have the longest wavelength from 1 mm to 100 km and the lowest frequency from 3 kHz to 300 GHz in the electromagnetic spectrum. 2. Propagation speed. In a vacuum, they travel at the speed of light. 3. Electromagnetic nature. They consist of electric and magnetic fields that oscillate neutrally, perpendicular to each other and perpendicular to the direction of propagation. 4. Refraction and reflection. They have the ability to be reflected in the ionosphere and refracted, which allows communication beyond the horizon. 5. Non-ionizing radiation. They do not have enough energy to ionize atoms, unlike X-rays, making them safe for use in communications. The Sun and radio waves. The Sun produces radio waves. The Sun, as a huge body of plasma in constant motion, rotation, convection, magnetic disturbances, emits electromagnetic radiation across the entire spectrum, including radio waves. 1. Thermal emission. Even at lower temperatures, such as the photosphere, charged particles emit radiation due to their thermal motion. Magnetic structures. The most powerful radio waves come from magnetic structures, such as sunspots and flares. Electrons, accelerated by strong magnetic fields, emit synchrotron radiation, which also includes radio frequencies. Using radio waves to measure the sun's temperature. We can use radio waves to measure the temperature of the sun, although not in the same way we measure the temperature of the Earth.
We can use radio waves to measure the temperature of the sun, although not in the same way that we measure the temperature of the Earth. We can measure it with black-body radiation, radio astronomy, and the advantage is that radio waves penetrate the sun's outer atmosphere much better than visible light, allowing astronomers to see the temperature of the photosphere more clearly. In conclusion, the sun is a huge nuclear machine that produces energy through fusion, while the production of radio waves is a side effect of dynamics of plasma, which can use to map and measure the temperature of its layers. According to the photo and the analysis we made in each case, the sun has different giga and megahertz, which means that in the frequency range of 20 and 18 megahertz, the sun is quieter. According to the figure, we can calibrate imaging of the quiet sun. We can obtain the brightness temperature in several frequency bands with high spatial resolution. Our figures show that lower temperature spectrums are specific.
What are they made of? Each station consists of 2 parts, one from the low band, between 10 and 80 MHz, and one from the high band, between 110 and 240 MHz. Both parts consist of many dipoles that are combined electronically. The signals are sent to the central computing facility in where they are correlated in real time and converted into images, spectra, and time series for pulsar studies. Software has many flexible observing modes that can be used to simultaneously point in different directions in the sky. Other modes allow continuous monitoring of the entire visible radio sky. International baseline, for the first time, provide subtoxic second analyzed in this frequency range.
Great. That's fantastic. Congratulations to the students and the teachers. Very nice to see how high level these presentations are. So the next school will present live. So let's welcome the Athens College with their project SC25 Pick Up the Peak. Are you here?
Yes, we're here.
Fantastic. Will you share your presentation? Great, we can say it. The floor is yours.
Hello everyone, we are here from Psychico College to present about the antenna and experiment. My name is Elena Kostadinidou and with me is Tassos Kadas, Maximus Wilkinson, and Panagiotta Christospar.
Hello everyone. I will introduce you to Solar Cycle 25. Solar Cycle 25 is part of the Sun's roughly 11-year activity cycle. During its peak, the Sun becomes more active than usual. There is an increase in sunspots, solar flares, and coronal mass ejections. This heightened activity can create stunning auroras, lighting up skies farther from the poles than usual. At the same time, it can affect satellites, GPS systems, and radio communications. Consequently, the peak of solar cycle 25 reminds us that we live in a connected solar system, where events 150 million kilometers away can shape our world. As we can see at the graph below, we are currently witnessing the last few moments of the peak before it starts to decline.
Our antenna is designed to pick up microwave radio signals between 10 and 13 gigahertz. These signals are naturally emitted by the sun, so instead of visible light, we are detecting radio waves, which allow us to study solar activity in a different part of the electromagnetic spectrum. The main component of this is the 60-centimeter satellite dish, which acts as a reflector. It collects and concentrates incoming radio waves towards a single focal point. There is located the low noise block down converter, or LNB, which amplifies very weak microwave signals and converts them to a lower frequency that can travel through a coaxial cable without significant loss. The signal then passes through an analog satellite finder, which works as a signal strength meter. This allows us to measure variations in the radio signal intensity. And to power the whole system, we used a 12-volt battery.
Before we could continue our experiment, we first needed to construct our antenna. This involved assembling all the equipment and preparing the cable to connect the battery to the analog satellite finder. For the experimental procedure that took place at 2 p.m. on Thursday, 26th of February, we placed our antenna at a suitable spot, oriented in such a way that it faces the sun, which was at 200 to 210 degrees from the north, and 35 to 40 degrees above the horizon. Following that, we took measurements on either side of the sun's position. The exact angle is presented in the table and graph. The variations of our results show a clear raise in dB as the antenna aligns towards the sun's position, representing an increase in activity.
In conclusion, building and testing the Sable radio antenna showed that meaningful astronomical observations can be made using basic yet low-cost equipment. By turning the antenna to the appropriate frequencies and monitoring the signal strength, we were able to detect variations in the sun's radio emissions, confirming that the sun is not only a source of visible light, but also a strong emitter of radio waves. The variation in the received signal versus the orientation of the activity can be directly detected through radio output, giving practical evidence of space weather phenomena. Overall, this project proves that solar radio observations can be accessible to students. At the same time, it reinforces important concepts such as electromagnetism, wave propagation, and astronomy, making the antenna both an effective scientific instrument and a powerful educational tool. Thank you very much for your attention. Have a very pleasant day.
Amazing. Congratulations. Very good presentation. I hope you enjoyed these experiments, and we are very grateful that you shared them with us. Thank you very much. Very nice. So let's move on. The next presentation is a video by the Experimental Upper High School of Chania, and it is an exploration of the universe using a stellarium by Konstantinos Katsandredakis. I'm sorry about that. So let me share the presentation.
Exploration of the universe using Stellarium from the first experimental high school of Chania. Introduction. In the context of the radio program, we were assigned the task of observing the night sky using the web app Stellarium. The information for this presentation was almost exclusively sourced from that specific app. Method used. We launched the app, Stellarium, and began exploring the night sky. More specifically, we focused on celestial bodies of interest, like the planets of the solar system, large galaxies, important and nearby stars, and nebulae. Analysis. Through the method described previously, we were mainly able to learn about the foreign bodies: the Andromeda Galaxy, M31 on the measure scale, Saturn, Mars, Jupiter, Pleiades, M45 on the measure scale, Betelgeuse, and Orion's Nebula. Key information points: where and when to look at the night sky to locate the listed celestial bodies, how far away they are from Earth in light years, major cosmic events involving them both in the past and future. Looking at some bodies in more detail. In order to help you grasp a part of the information that we were exposed to, let us look at some bodies in more detail. The Andromeda Galaxy. The Andromeda Galaxy is a large spiral galaxy just like our own, and the nearest major galaxy to our own at 2.5 million light-years away. Being slightly larger than our own galaxy, it is the dominating entity in its galactic group. In roughly 4 to 6 billion years from now, the Andromeda Galaxy and our own will merge into a new massive galaxy, setting the foundation for new stars to begin forming and possibly igniting a quasar as the two supermassive black holes at their respective centers merge. Betelgeuse. Betelgeuse is the star located at the left shoulder of the Orion constellation, sitting at roughly 642 light-years away from the Earth. It is one of the nearest red supergiants to the Earth. During 2022, it made global headlines when its brightness suddenly dimmed, leading many to believe that it would go supernova. Whilst it did not blow up then, we can tell with certainty that it will go supernova within the next 100,000 years. Another interesting thing about Betelgeuse is that it's so huge that gravity can't properly hold it together. It spits about 190 million kilograms of mass into space every second. Orion's Nebula. Located around the belt of the Orion constellation and sitting roughly 1,300 light-years away from Earth, Orion's Nebula is one of the largest star nurseries that we can observe, host to about 2,800 stars and counting. It is one of the most beautiful deep sky objects that one can observe with the naked eye. In conclusion, through the assignment of the radio program, we were able to learn a lot of interesting facts about the celestial bodies that we had heard of before but never actually done any research on. The information we obtained was very interesting and valuable to us since we're heavily interested in the natural sciences. In order to finish off the presentation in a way befitting of those magnificent objects, we will be taking a look at some photos/illustrations of them. Thank you dearly for your attention.
Amazing. Thank you very much. Excellent, excellent presentations, topics, depth into the presentations. Thank you very much for sharing this with us, and I hope you continue studying the natural sciences. Very nice. We will move on to the next school, the Pyrrhus American College of Greece, with the construction of a simple radio antenna for solar detection, and involving the students Χριστόφορο Στράτου, Χριστίνα Κάπου, Παρασκευή Ηλία Παπαδοπούλου, Μικαέλα Μάλια, Νικόλαος Κουτσός, Μελίνα Τσαρούχα, Εμιλία Παπαδάκη, Αμαλία Άννα Δενδρινού και Αντωνία Τσιγαρίδα. Let me share.
We're very excited to connect with fellow students from different countries. Even though we're meeting virtually, we hope this presentation brings us closer and helps us learn from one another. We are students from the gymnasium of the American College of Greece, and we worked on the construction of a simple radio antenna for solar detection.
In this project, we study the sun, not in visible light, but in radio waves. The sun emits radiation across the entire electromagnetic spectrum, including microwaves. Detecting these emissions is part of radio astronomy. Our goal is to build a simple and low-cost antenna system that can detect solar radio waves at approximately 10 GHz using commercial satellite equipment. The figure on the top is a picture of the sun captured with a telescope with the help of Dr. Vandoulakis when she visited them. Solar radio emissions are produced by both thermal and non-thermal processes. The photosphere and the corona emit microwave radiation due to their high temperatures. In addition, charged particles moving in solar magnetic fields generate radio signals. During solar flares, the intensity of radio emissions significantly increases. The frequency we target, around 10 GHz, belongs to the microwave region, which can be detected with satellite reception technology. The system was built using affordable and widely available components. We used two coaxial satellite cables, an analog satellite finder to measure signal strength, a low-noise LED, a 12-volt battery for power, and a standard satellite dish about 80 centimeters in diameter. Basic tools such as pliers, a cutter, and insulating tape were also required. The total cost remained under 70 euros. First, the LNB was mounted on the arm of the satellite dish. Then, one cable connected the LNB to the satellite finder to the port labeled QLNB. The second cable was modified by stripping its insulation to expose the inner conductors. The central wire was connected to the positive terminal of the battery, while the beaded shielding was connected to the negative terminal. The other end was attached to the finder, completing the power circuit. All connections were insulated for safety. After assembly, the satellite finder was powered on by rotating the control knob. The device displayed an initial baseline signal level. This reference level is important because any increase above it may indicate detection of microwave radiation. The dish was placed outdoors with a clear view of the sky. By slowly rotating it towards the sun, we monitored the signal strength on the finder when the dish aligned with the sun. The signal level impressed the confident that the system was detecting solar radio emission. We observed strong insight signals under clear sky conditions. Cloud and humidity sometimes reduce signal strength. The highest readings were usually recorded around midday when the sun was highest in the sky. Small fluctuations were also noticed, likely caused by interference or satellite or terrestrial microwave sources. One of the main advantages of this setup is its low cost. It is simple to contrast and use commercially available components. Despite its simplicity, It provides real-time visual confirmation of solar radio detection, making ideal verification demonstrations.
The highest signal intensity was recorded when the antenna was directly aligned with the sun. This confirms that the system successfully detects solar radio emission in the microwave region. We also found out that the small angular deviation from the sun's direction resulted in a noticeable decrease in signal strength, something that highlights the directional characteristics of the parabolic dish and the importance of precise targeting. As expected, when the antenna was pointed away from the sun, the received signal dropped to background levels. Furthermore, we confirmed that stronger signals are recorded during periods of intense sunshine, while under cloudy conditions, signal attenuation is observed due to absorption and scattering by clouds and the atmosphere. Last but not least, we showed that the solar radio waves can be detected using simple satellite equipment. The dish, L&D, and finder together function as a basic microwave radio telescope. In conclusion, this experiment confirms solar emission at around 10 gigahertz and demonstrates that radio astronomy can be accessible even at school level with minimal budget.
For this assignment, we visited our school's library. Our references can be found here. Last but not least, we will say a big thank you with the sound recorded by our antenna. And the melody that our school's orchestra wrote on top of that sound.
That's great. That is fantastic. Great, thank you very much. I am back. Right. I'm very glad to say that this project inspires so many students, and I'm glad to see they also visit their school libraries. That's great. Excellent. Because it's not only the things that you can find online. Libraries are also very important, and books are important. Let's not forget about that. So, right, next we have the Ford Gymnasium of Toumba, Thessaloniki. Okay, they have sent a video, but if they want to say hi, if anyone is here, please unmute and introduce yourselves.
Hello, can you hear me?
Yes, I can hear you.
I'm from Thessaloniki, Greece. My school is the 4th Junior High School of Toumba, and I'm here to present our project for Caspia A, which is a supernova remnant. That means we're looking on the leftovers debits from a gigantic stellar explosion. I'm really happy to be here with you, and I hope you enjoy the video we've made for you. If you have any questions, I'm really happy to answer them.
That is fantastic. Thank you very much. I will share your video now, and yes, let's find it. Yes, that is here. Excellent.
We're students of the 4th High School of Toumba, and this is our project about a cosmic detective story. Meet our subject, Cassiopeia A, for short, Cass-A. It's just breathtakingly beautiful. It's this incredible cloud of gas and dust, basically the ghost of a star that exploded. But here's the thing. This one picture, it doesn't even begin to tell the whole story. It's actually just one tiny piece of a much, much bigger puzzle. And that really gets us to the heart of our investigation today. So, if this is just one object, what's the deal with all the different pictures? And why do they look so wildly different from each other? Well,
It's because astronomers are using different kinds of eyes, telescopes that see light that's totally invisible to you and me. It's new you. It reveals a brand new clue. To solve this thing, we've got to understand our subject first. So, if you want to look up into the northern sky, you'd find our target hiding inside the famous W shape of the constellation Cassiopeia. The constellation itself is pretty easy to spell. Cassiopeia. It's incredibly faint in the light our eyes can see, which is actually why it was a mystery for such a long time. So, what is this thing? It's what's called a supernova remnant. That means we're looking at the leftover debris from a gigantic stellar explosion. The death of a star like 20 times more massive than our own sun. It's the kind of explosion that actually forges heavy elements, the very stuff that planets or even we are made of. This celestial crime scene is really far away. The light we're seeing from this explosion has been traveling for 11,000 years just to get to our telescopes. We're quite literally looking into the past. Our investigation is going to start with the most violent evidence we can find. The highest energy light that's just blasting out of this remnant. When we look in gamma rays, the most energetic light there is. Cassiopeia doesn't really have a lot of detail. It just looks like this powerful glowing blob. What this view tells us is that the whole remnant is acting like a giant particle accelerator. It's one of the most powerful factories in our entire galaxy for making cosmic rays. Then we switch view to X-ray and the picture changes completely. You see this unbelievably intricate web of filaments and knots. This is no simple blob. It's a complex, super dynamic structure of gas that's been heated to millions of degrees by the explosion shockwave. Really cool is how scientists can read this X-ray light. They study the spectrum of the light and they can see the chemical fingerprints of all the different elements, telling us exactly what that original star was made of. It's like cosmic forensics. We can take those fingerprints and build a literal chemical map of the explosion. You can actually see where different elements, like silicon in red and neon in blue, got blasted out into space, and the kind of light that our own eyes can actually see. The difference is just stunning. On the left, that's what we see in normal visible light. It's faint, almost ghostly. Compared to that, the vibrant blazing inferno we see in X-rays on the right. It just goes to show you how much of the story is happening in wavelengths our eyes just can't pick up. That's not to say the visible light view isn't important. When we zoom in with a powerful telescope like Hubble, we see these absolutely beautiful, delicate filaments and material that were thrown out by the star. They're glowing because they're being heated up by the supernova shockwave. And just like with the X-rays, these colors are chemical clues that we can actually translate. The green glow you're seeing that's coming from filaments that are super rich in oxygen, the red and purple wisps, those are full of sulfur, and the blue areas are mostly made of hydrogen and nitrogen. Every color helps us map out the anatomy of this explosion. Next, we hunt for clues that are a little cooler and hidden from our eyes. To do that, we need to tune into infrared light, and this is the view from the James Webb Space Telescope, which sees in infrared. You can basically think of it as cosmic heat vision. It lets us peer right through all the dust that's in the way and see the cooler gas that X-ray and optical telescopes just miss. And this reveals even more about the chemical makeup, showing us heavy elements like argon and neon. We've got one last major clue, and it's not from the highest energy light. It's from the longest, lowest energy wave of all radio waves. In radio waves, Cassiopeia is anything but faint. It is intensely, overwhelmingly bright. This view shows us this powerful cell structure, and that's where the explosion shockwave is just revving up electrons to nearly the speed of light, causing them to literally scream out in radio wave. And the wild part? After our own sun, Cassiopeia is the brightest thing in our entire sky at many radio frequencies. It's actually so bright and so stable that astronomers use it to calibrate their telescopes. So we've gathered clues from all across the electromagnetic spectrum, from the highest energy gamma rays all the way down to radio waves. Let's put all the pieces of the cosmic puzzle together. We can see our first image with totally new eyes. We know those vibrant blues
blues and greens are just pretty colors anymore. They are the chemical signatures of superheated silicon and neon seen on X-rays. And those fairy reds, that's the cooler glow of cosmic dust revealed in infrared light by the James Webb Space Telescope. We are seeing the entire story of this explosion told across the full spectrum of light all at once. As our research shows, no single view tells the whole tale. To solve the mysteries of the universe, you need every single clue. It's only by combining all these different perspectives with scientists called multi-wavelength astronomy that we can ever hope to truly understand objects like Cathay. We've decoded one star's death just by looking beyond what our eyes can perceive. What other incredible, profound cosmic secrets are out? They're hiding in plain sight, just waiting for us to look with the right kind of eyes.
Fantastic. Excellent. Wow, very nice. I also like the graphics very much in the presentation. Thank you so much.
We're so happy to be here, and I really want to thank our teacher, Samada, because she made the video and it's so good. I could never imagine all these difficult things to be in this so easy and understanding video. Thank you very much.
Thank you very much. I loved about the forensics, space forensics. That's excellent. Thank you for being with us, and please stay and enjoy the rest of the meeting. So let's move on to the next presentation. It's a video from the Gymnasium of Anavisos, Conversing with the Sun by Kalia Hadjirusea Agapi Georgiou. Sorry, Giorgio. Maria Garifallia Karali. Let me find the presentation. Okay. Very nice. And share it with you.
Για κάνει στροφή, κάνει στροφή. Το βλέπετε?
Ναι, όντως.
Το βλέπετε?
Τι βλέπουμε?
Λοιπόν, μισό. Πάνω, κράτα εσύ εδώ. Κράτα εδώ να τους εξηγήσω. Λοιπόν, έχεις αυτό, το γυρνάς. Βλέπεις, εδώ μικραίνει η συχνότητα.
Ναι.
Εδώ, τον άποδο θα πρέπει να γίνεται. Γιατί από εδώ είναι δεν είναι.
Space Map. Πέρα να δουλέψουμε με τον κόσμο του πάμε στο κοινό.
Παρακολουθήστε πώς θα δουλέψει κατευθείαν.
Φυσική παιδιά. Τι πάρει. Δεν είναι καν να πάτε μέσα. It's working. Hello, I'm Agabi, and taking part in the astronomy program at school or building a antenna was such an amazing experience for me. Even though I didn't know what exactly to expect at the beginning, I quickly realized how interesting and exciting it would be. Learning how radio antennas work and actually building one ourselves made everything feel real and hands-on. It was amazing to see how science can connect us to space and help us understand more about the universe. I also had so fun working with others and sharing ideas and solving problems. Overall, it was not only educational, but it was also funny and memorable. And I'm really happy that I had the chance to be part of it.
Hello, from me as well. As far as I'm concerned, I had a very positive experience working on the radio antenna project. I was highly satisfied with the overall process as it allowed me to develop valuable knowledge and practical skills. In my view, the project was well organized and fulfilled its educational purpose. Kind regards and thank you for your time and consideration.
Okay, I'm gonna cry here. That's very nice. Thank you guys very much. Much appreciated. I'm very touched by your kind words. We all are, and congratulations to you for taking on the project and finishing it. Huge congratulations. Well done. Very nice. Excellent. So let's go to one more video by the FTS Gymnasium with lithium classes. A board game. Yes, another board game. Excellent. Galaxy Escape. So here we have a very long night of playing board games related to space here by Βασιλική Σωτηρίου, Λάμπρος Ελευθερίου, Σπύρος Σωτηρίου, Άγγελος Ζαφύρης, Κωνσταντίνος Μακρυπίδης, Όλγα Γκολεζάκη, and Κωνσταντίνα Μακρυπίδη. Let me find the video and share it for you. Very nice.
Hello, we are the team from Fitias Gymnasium with Lyceum classes, a small school in Western Greece, passionate about astronomy. Greetings to all participating schools, and thank you to the event organizers for giving us the opportunity to take part in today's meeting.
For our final project, we had the idea of creating a digital game that gives players a fun way to review everything they learned through the radio program. We wanted the game to be for everyone, not only those who took part in the program, but also anyone who wants to test their knowledge of radio astronomy and astronomy.
After a lot of discussion, we settled on this storyline. Our galaxy is in danger. A supermassive black hole has become extremely active and is tearing everything apart. The galaxy is divided into sectors. In our spaceship, we start at the center and travel throughout different sectors, trying to reach the outer edge of the galaxy and escape. Our fuel, meaning the energy we have for the journey, isn't enough, but we can earn more energy by answering quiz questions correctly each time we move to a new sector. If we don't answer the quiz questions correctly, we gradually lose energy and end up back at the center with almost none left, and we get destroyed. Also, if we had more time, we'd love to add an arcade-style minigame as a break from the quizzes, as well as a multiplayer mode. It was also important for us to collaborate with schools from China and Pakistan that are part of the radio program, so they could translate the game into their own languages.
Let's try it out for a minute and see how it works. On the right side of the user interface, you can see our energy gauge starting at 80 petajoules, along with the zoom control bar, mute, language selection, restart, and the full screen button. It doesn't really matter which sector of the map we move to. Let's start right here. When we move, a quiz pops up for us to answer. For example, here we have to place the names of the planets in our solar system in the correct spots. We just earned 60 petajoules and we move on to the next sector. If I'm not completely sure about the right answer, I can choose more than one option. Of course, I won't get the maximum energy. We keep moving outward.
Most of the questions can be answered by anyone with basic astronomy knowledge, but there are also a few, like this one, that are specifically about the radio program. Here, of course, we choose China, Greece, and Pakistan. There are also a few questions that don't require any knowledge at all. For example, here we just swap the pieces to form the correct picture. At some point during one of our moves, an extra challenge appears. An asteroid field is in our path, and we choose to fly through it so we can play the arcade minigame. I've played this game so many times while we were developing it that the only way I can miss a question is by switching it to Chinese. So I'll just guess. Oh, not completely wrong. Maybe I know a little Chinese after all. And that's how we gradually reach the outer edge of the galaxy. Once we collect 400 petajoules of energy, a button appears that lets us finish the game and win. Kostas worked on the game's music. Vasiliki created the map. Lambros set up the rules. Olga and Christos did the play testing and helped find bugs and glitches. Angelos worked on the user interface. Konstantina prepared the quiz content. And finally Spiros brought everything to life with the programming. Oh, and there was also Mr. Yanis, who played the role of the complainer, although he called himself the coordinator. We're especially grateful to the students from Shanghai, Northern America International School for their decisive contribution to our project. Their support helped us improve our work, and it was truly an honor for us to collaborate with them. That was our game. If you'd like to try it, you can visit our school's website and use this link. Thank you to the organizers for their hospitality, and thank you all for watching. We wish you a great rest of the event.
That's amazing. I know what I'm doing tonight. And so if you have other plans, cancel them and play the board game, okay? And you can learn other languages too. Excellent. And this is all about the international collaboration. And we are so glad we gave you the way to do that. It is very important for us. Thank you so much. Right, I made a little mistake in the program, so I forgot to show you one video from Gymnasium of Philothei, and thank you for letting me know online. Right, so I will share it now, and then we will have the 11th Gymnasium of Thessaloniki, which are here to present live. So let me find the video from Philothei, which will be presented by Marinu Danai, and it is about the solar system. Okay.
Solar system consists of the Sun and 8 planets which are in elliptical orbits around it. Each planet has different compositions and depending on the distance from the Sun has also different average temperatures. The planets and the temperatures are Mercury 167 Celsius, Venus 464 Celsius, Earth 15 Celsius, Mars -65 Celsius, Jupiter -110 Celsius, Saturn -140 Celsius, Uranus -195 Celsius, and Neptune -200 Celsius. The planets also have satellites, like the Earth has the Moon. The planets vary from Mercury and Venus, which have no moons, to Saturn with 274 confirmed moons. Between Mars and Jupiter, there is a vast number of celestial bodies called the asteroid or the asteroid belt. There are the remains of the early solar system in the form of rocks of irregular shape from small size to about 1,000 kilometers across.
Very nice. Thank you very much, Danai, for the great presentation. And now I will invite the 11th Gymnasium of Thessaloniki to present their work on the simulation of black hole mergers. Γεια σας, hello. You are live. You are live. We can see you. How are you? I was speaking in English. Okay. Can you hear us?
Yes, yes, yes.
Ah, good. Excellent. I am speaking to you. Great. So please introduce yourself. And do you want me to share your slides or will you do it yourself?
Good afternoon. We are from the 11th Gymnasium of Thessaloniki, Greece, and today we present a project about the simulation of black hole merger and gravitational waves.
Very nice. So please unmute because we cannot hear you. We cannot hear you speaking. You have the mute on. Okay, I will help you. Stop sharing, unmute, and then share again.
Oh, all right. Can you hear it?
Yes, thank you very much.
We had some problems. Okay, wait.
Can you hear us?
Oh, all right.
Yes, we can hear you. Please go ahead.
Can you see what our screen?
We can see your screen and I can see myself in the screen. So please share your presentation. Thank you very much.
Right. Okay.
Good afternoon. We are from the 11th Gymnasium of Thessaloniki, Greece, and today we present a project about the simulation of the black hole merger and gravitational waves. This is our team. We studied black hole collisions, gravitational waves, and radio astronomy. We also created a Python simulation showing the black holes merging. In 1915, Einstein's general theory of relativity described gravity as the curvature of spacetime. He predicted gravitational waves. This prediction was confirmed in 2015 when LIGO detected a black hole merger. In September the 15th, 2015, the two LIGO detectors in the United States made the first ever direct detection of gravitational waves. They map shows light measurements of gravitational waves from the readings from the right and on the left, detected compared with the Gravitational waves are rate of space-time got by mass and moving objects. They travel at the speed of light and give information about cosmic events.
Massive universe distorts space-time by Einstein's general theory of relativity. Stars and galaxies create dips or gravity wells, forcing light and objects to follow curved paths rather than straight lines. This curvature is what we perceive as gravity.
A black hole forms when a massive star collapses. Its gravity is so strong that nothing can escape, not even light.
Black holes orbit each other with energy and move closer. Finally, they collide and release enormous energy as gravitational waves. Like the gravitational waves use laser measurements of tiny changes in space. We simulated the merger of two black holes using Python and Google Color.
The program calculates the final mass and produces an animation, the gravitational chirp sound. Here we can
In this slide, we present part of the animation showing the spiral motion and the final merger of two black holes.
You can hear the sound from the collision of two black holes known as chirp. LIGO can convert space-time distortion signals into an audible sound called the chirp, so we can now hear.
Radio astronomy studies celestial objects using radio waves and large radio telescope. Black holes typically have minimal electromagnetic radiation emission and are difficult to detect directly with radio telescopes. Radio astronomy provides additional information about black holes. Black holes absorb matter, but some material is reflected at high speed. These emissions are called radio jets. The Interferometry telescope captured the first black hole in the galaxy's wave which showed the bright disk on the dark side. Gravitational waves detected by LIGO confirmed Einstein's theory. Radio astronomy complements observations of black holes mergers. The merger of two black holes does not emit radio waves. However, radio astronomy helps us better understand the environment in which the phenomenon occurs. A black hole merger simulation helps us better understand and visualize the phenomenon.
Thank you for your attention.
Thank you very much. That was amazing. Congratulations. Well done. Thank you very much for this excellent presentation. Did you enjoy doing the project? Yes?
Yes.
Yes. Excellent, excellent. Very, very good. Thank you very much. Please stay and enjoy the rest of the presentations. That's great. Right, so let's move on to the next. We have a couple of videos to play, 4 videos in particular, before we go to Hadjivi School, which are live with us today. So, we have the 3rd experimental gymnasium of Ierapetra and their video construction of a radio antenna using simple materials and a very long list of names. I'm sorry, I won't say all the names in the interest of time because we are running a bit late. Apologies for that. I will go straight to the presentation, if that's okay with you. Oops. Okay. This one. Good. Very nice. Let's go. Excellent. Thank you. Thank you very much. And to the Third Gymnasium of Thessaloniki. That was great. We're glad you enjoyed playing with the antenna. Sorry, Ierapetra, third Experimental Gymnasium of Ierapetra. Now we have another presentation from the Gymnasium of Philothei, the solar system, by Regina Georgakopoulou. Okay, so let me share that.
Our solar system. Hi, my name is Regina Georgakopoulou, and this is my exercise about our solar system. Mercury is the only slightly larger than Earth's moon, is the fastest planet zipping around the sun every 88 Earth days. Venus is the second planet from the sun and the sixth largest planet. Is the hottest planet in our solar system. The Venus trip around the sun takes only 225 Earth days. Earth, our home planet, is the third planet from the sun and the fifth largest planet. Is the only place we know of inhabited by living things. Mars, the fourth planet from the sun, and is a dusty, cold desert world with a very thin atmosphere. Jupiter is the fifth planet from the sun and the largest in the solar system. By far, more than twice as massive as other planets combined. Jupiter's trip around the sun takes 12 Earth years. Saturn is the sixth planet from the sun and the second largest in the solar system. It's surrounded by beautiful rings. Saturn's trip takes 29 and half Earth years. Uranus is the seventh planet from the sun and the third largest planet in our solar system. It appears to spin sideways. Uranus' trip takes 84 Earth years. Neptune is the eighth and the most distant planet from the sun, is the fourth largest and the first planet discovered with mass. Neptune's trip takes 165 Earth years. Pluto is once our solar system's ninth planet, but was being reclassified as a dwarf planet. It was locked in Jupiter belt. Pluto's trip takes 248 Earth years. The end. This is the model of our solar system. This is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto.
Fantastic. May I just say that having Pluto up there, it's very emotional for me. So thank you for adding Pluto in the solar system. When we were kids, Pluto was a planet. Poor Pluto. Anyway, so we have two more videos from the Public Onassis High School of Acharnes. Okay. So the first one is the 21st centimeter line of neutral hydrogen and the structure of the Milky Way by the Inekis Korpidas. So let me share the presentation so we can enjoy it. Here we go.
Good afternoon. We are the Radio Astronomy Group of Public Onassis High School of Acharnes. In this project, we investigated the structure of the Milky Way using the 21 centimeter emission line of neutral hydrogen. The main goal of our study was to explore how neutral hydrogen is distributed across the galaxy. We compared radio data with optical, infrared, and gamma ray observations to understand how different physical components of the Milky Way relate to each other. Why neutral hydrogen? That's because it is the most abundant element in the Milky Way. It emits radiation at a wavelength of 21 centimeters in the radio spectrum. Unlike optical light, radio waves are not significantly absorbed by interstellar dust, allowing us to observe the full structure of the galactic disk. To achieve our goal, we used the Aladdin Sky Atlas to load and compare different full sky surveys. We overlaid images from radio, optical, infrared, and gamma ray observations and performed a qualitative comparison of their spatial distributions. To begin with, the HI4PI map shows a strong bright band along the galactic plane. This indicates that most of the neutral hydrogen is concentrated in the galactic disk, outlining the large-scale structure of our galaxy. The infrared map traces warm interstellar dust and regions of active star formation. We observed a strong similarity between the infrared and HI maps, suggesting that gas and dust are often located in the same regions. In the optical map, we mainly observe stars. However, the galactic plane appears fragmented and partially obscured because interstellar dust absorbs visible light, limiting optical observations. Gamma rays are produced by high-energy processes, such as cosmic ray interactions with interstellar gas. The emission follows the galactic plane, but we also observe bright point sources, many of which are extragalactic. When overlaying the infrared and HI maps, we observe strong spatial correlation. This indicates that dust and neutral hydrogen coexist in dense regions associated with star formation. The comparison between optical and HI maps demonstrates the limitation of visible light. Many hydrogen-rich regions are invisible in optical wavelengths due to dust absorption, highlighting the importance of radio astronomy. The gamma rays overlay shows that high-energy emission generally follows the distribution of neutral hydrogen, supporting the idea that cosmic rays interact with interstellar gas. Our results demonstrate that the Milky Way appears fundamentally different depending on the observed wavelength. Each part of the electromagnetic spectrum reveals a distinct physical component and process. It is understandable that neutral hydrogen plays a central role in galactic evolution. It serves as a raw material for star formation, defines the structure of the disk, and participates in the energetic processes. Concluding, we found out that a multi-wavelength approach is essential for understanding the Milky Way. The 21-centimeter line reveals the hidden structure of the galaxy and is fundamental to both star formation and high-energy phenomena. Thank you for your attention.
Excellent, fantastic. Let's share also the other presentation from the same school, which is about the radio sun and the solar atmosphere.
Good afternoon. We are the Radio Astronomy Group of Public Onassis High School of Averness. We will present our research on the radio sun. We studied how the sun emits radio waves and how these emissions help us understand the structure and temperature of the solar atmosphere. The sun emits radiation across the entire electromagnetic spectrum. Radio waves allow us to observe atmospheric layers that are not visible in optical light. By studying radio emissions, we can better understand solar structure and apply this knowledge to other stars. The solar atmosphere consists of three main layers: the photosphere, chromosphere, and corona. The photosphere is the visible surface at about 5.8 thousand Kelvin. Above, it is the chromosphere, a transition layer. The corona is the outermost layer, and it's extremely hot, reaching hundreds of thousands of Kelvin degrees. We used real radio images of the sun at frequencies ranging from gigahertz to megahertz. We also analyzed the brightness temperature versus frequency diagram. By comparing images and the model curve, we estimated the temperature of different atmospheric layers. At high frequencies, radio emission comes from the lower solar atmosphere, mainly the upper photosphere and lower chromosphere. The sun appears smaller and more detailed. The measured temperature is approximately 10,000 Kelvin. At intermediate frequencies, emission originates from higher layers, mainly the upper chromosphere and the lower corona. The apparent diameter increases and the image sharpness decreases. Temperatures reach up to about 750,000 Kelvin. At low frequencies, radio waves come from the middle and upper corona. The sun appears much larger and the image becomes blurry due to strong scattering effects. The observed temperature is around 300,000 Kelvin. We concluded that the appearance of the sun depends strongly on frequency. Higher frequencies correspond to lower atmospheric layers, while lower frequencies correspond to higher and hotter layers. Radio astronomy is a powerful tool for studying the sun. We conclude the corona is extremely hot and radio wave scattering affects low frequency observations. Each radio frequency allows us to observe a different height in the solar atmosphere. Thank you very much for your attention.
Very nice. Thank you. Thank you so much. That's amazing. Right. So, is the Hadjive school here? Yes?
Yes, we're here.
You're here. Excellent. Very nice. So, would you like to go next? Can you hear me?
I cannot share my screen.
Oh, why? I have enabled it.
I found it.
Yes, thank you. So, yes, we are ready for you. Welcome.
Okay, we can begin.
Collisions between galaxies and anti-galaxies with anti-gravity.
What is antimatter?
It has everything opposite or symmetric. By whom it was discovered, Dirac 1928 prediction theory.
Anderson 32 Discovery Lab.
When it was discovered, 1932 anti-electron, 1955 anti-proton, 1959 anti-neutron, 1965 anti-nucleus.
Where is all antimatter in the universe? We should have same quantities. Baryon asymmetry.
Galaxies are the largest systems. Are there anti-galaxies? Probably half of them.
What's in anti-galaxy and anti-gravity?
It will explain universe's expansion.
Something that nothing known can explain.
The expansion would be exactly the observed. Men argument against. Wouldn't we see annihilation?
Simulation description. We made the simulation with an AI agent, base 44. We bring two galaxies into collision track. Since they attract each other, they tend to collide and most of the times merge.
We then replaced one of them as a repulsive anti-galaxy. We have used several parameters to accomplish annihilation. We want to see how rare it is. First parameter is the speed they have to each other. We increase the velocities, forcing them to come closer and closer.
We found out that it about 1,600 kilometers per second with jet annihilations.
Simulation measurements. The graph of velocities observed shows that more than 1,600 is very rare, 1%.
Ας το πει επόμενος, ο Ιάσονος.
For both galaxies to have this velocity and escaping its own cluster of galaxies, we need 10,000 galaxies, only for the velocities to have annihilation.
Second parameter is the direction they have to each other. We have added a slight vertical velocity, 30 km per second, and we increased the radial velocity to maximum, 3,000 km per second, and still we didn't have annihilation.
Simulation results. This counts to a focus of less than 1 degree out of 365. But for a sphere, we have a second 1 per 365 angle.
Now we need to put them all together. For both galaxies to have this close direction towards each other, we need 10 billion galaxies for annihilation only for the directions.
Now we need to put them all together. So just for the velocities needed and the close direction to each other, we need 100 trillion galaxies.
Simulation results. But the highest estimation is 2 trillion galaxies. So this is why in case of repulsion, we don't see any antimatter annihilation from galaxy collisions.
Πύρος.
We tried also many other parameters that make it more difficult. So this study shows that it is mathematically impossible to achieve annihilation in our universe.
Αυτό ήταν, τελειώσαμε. Ευχαριστούμε. That was it. Thank you very much.
Amazing. I was drawn by the simulation. It's amazing. Excellent work. Congratulations to all of you. Also for presenting in English. It's hard. Very well done.
Thank you.
Very well done. Congratulations. You are becoming scientists every day, a bit more and more. So I hope you continue studying science and you are the scientists of the future that will solve all these problems and puzzles and discover new things. Okay? Congratulations. Well done.
Thank you.
So let's move on to Arsakio Gymnasium of Patra. Do we have Arsakio here?
Yes, we're here.
You're here.
Can I share my screen for the presentation?
Yes, you can share your screen. Absolutely. Please also introduce your team and we are ready for you.
So, hello. We are Asakio School of Atlas, and we're here to present you our project about the Northern Lights, a multidisciplinary exploration of auroral science, observation, and cultural significance. The students participating are Miltiadis Palalas, Akelikia Doniasideri, Melitini Tavernaraki, and Sofia Haritsi, and our teachers are Nikolaos Yannakopoulos and Anastasios Psinas. A window into space physics. The northern lights are shimmering curtains of green, red, and violet light that have fascinated humanity for millennia. Beyond their beauty, auroras reveal the dynamic relationship between the sun and the Earth's magnetosphere. Modern science shows auroras are visible signatures of energetic solar particles interacting with Earth's magnetic field and atmosphere, making them essential to understanding space weather and protecting modern infrastructure. How auroras form? Firstly, there is the solar wind emission. The sun continuously emits charged particles that travel toward Earth carrying embedded magnetic fields. Then there is the magnetic reconnection. Solar wind merges with Earth's magnetic field, transferring energy and accelerating particles toward polar regions. Thirdly, there is the atmospheric collision. Energetic electrons collide with oxygen and nitrogen atoms in the ionosphere, exciting them to emit light. Lastly, light emission atoms return to ground state, producing green oxygen at 557.7 nanometers, red high-altitude oxygen, and blue-purple nitrogen auroras.
Hello, we cannot hear you anymore.
Hello guys, could somebody take the lead?
Can you hear me now?
Melitini?
Can you hear me?
Okay.
Yes, I can hear you. Please go ahead.
Auroral morphology. Long stable bands stretching across the horizon, curtains, vertically structured sheets with dynamic folds, pulsating phases, intermittent diffuse glows that flicker rhythmically, spiral and coronas, dynamic rapidly changing structures overhead. These shapes reflect underlying magnetospheric processes and particle dynamics in Earth's upper atmosphere. From ancient tides to satellites, oral traditions, indigenous sky knowledge and observations, ground instruments, all sky cameras, spectrometers, magnetometers, satellite missions, Themis swarm goes and dedicated probes, citizen science, public observations, and distributed sensors. Ground-based tools, all sky cameras, spectrometers, magnetometers, and radar systems provide high-resolution local data. Space missions, NASA's Themis, ESA Swarm, and NOAA's GOES satellites offer global coverage linking auroral activity with solar conditions. Advancing auroral science, machine learning forecasting, neural networks predict auroral activity from solar wind measurements, outperforming traditional statistical methods in short-term forecasting. High-resolution imaging, new satellite
imagers capture fine-scale auroral structures and unprecedented spatial and temporal resolutions. Coupling models, improved simulations reveal how energy flows through Earth's magnetic environment, illuminating substorm triggers and particle acceleration. Space weather prediction research focuses on predicting geomagnetic storm severity and understanding auroral links to broader space weather dynamics.
Auroras in human culture, indigenous interpretations. Sami tradition viewed auroras as spirits requiring respect. Inuit stories describe them as ancestor souls playing games in the sky. Ancient to medieval, Aristotle speculated about burning vapors, while medieval Europeans associated auroras with war or divine intervention. By the 18th century, systematic documentation laid the foundation for modern geophysics. Cultural breed. Auroras contact humans' experience with space physics, shaping cultural identity across millennia while inspiring scientific inquiry and technological innovation. Technological impacts. Aurora signal geomagnetic disturbance that can disturb modern infrastructure. Power grid. Geomagnetically induced currents can overload transformer as seen during the 1989 Quebec blackout. Satellites. Increased atmospheric drag during storms alters orbits and degrades electronics. Communication and navigation. Auroral activity disrupt GPS accuracy, HF radio communication, and aviation routes over polar regions. Challenges in auroral research. More triggers. What precisely induces auroral substorms? Long-term forecasting. How can space weather predictions be improved? Plasma process. What fine-scale dynamics shape auroral structures? Solar cycle effect. How will increasing solar activity impact technology? Addressing these questions requires coordinating international research efforts combining observation modeling and interdisciplinary collaboration.
More than a spectacle, the North Lights bridge human experience and space psychics thoughts, centers of culture, interpretation, and scientific investigation. Arrows have revealed the dynamic sun-Earth relationship. As technology becomes increasingly vital to space weather effects, understanding auroras is essential for safeguarding modern infrastructure contained interdisciplinary research will deepen our knowledge of this remarkable phenomenon and protect the systems society depends on. Thank you very much for your attention.
Great, great, great. Amazing. Thank you very much. Great, guys. Thank you so much. Very nice to hear also about the aurora. And has anyone seen the aurora before? live?
I never seen the aurora before, but I wish I could see it. At least one in my life.
Yes, yes. Let's hope there is a geomagnetic storm soon that can bring it a bit closer to Greece, a bit southern, so we can observe it. Otherwise, you can travel to the northern countries or to the very southern countries and observe it. Thank you again so much. We appreciate all the effort. You know, English is not your first language, and you know, you're very young students. So congratulations to you, and congratulations to the teacher and for all the efforts. Thank you so much. Right. Let me move on to another presentation by Gymnasium of Philothei, the Solar System by Panayota Spiropoulou. And then after that, we have two more presentations. One will be by the Model Upper Secondary School of Agia Anargiri. And then I will present the presentation about Stellarium from the first Gymnasium of Rafina, because we had, apologies for that, we had a technical problem with the presentation. So let me share the presentation from Gymnasium of Philothei.
The Solar System, Panayota Spiropoulou, A3 Junior High School of Philothei in year 2024-2025. Universe. The universe includes galaxies, solar systems, planets, stars, and much more. In short, this universe consists of everything. Dark matter is probably included, but not necessarily dark energy. It is also estimated that the shape of the universe is most likely hyperspherical. Moreover, as beautiful as it may appear in images, it can be equally dangerous for a human being due to the lack of oxygen, along with many other hazards. Galaxy. Our solar system, which we inhabit, belongs to the Milky Way galaxy. A galaxy may have more than one solar system. The name of the galaxy comes from the ancient times when, according to the myth, Hera accidentally spilled Sotnamir from the top of Olympus into the sky and created the galaxy. In modern times, we have kept the old name, and we know that if we observe the galaxy, we will see that the stars have taken on a strange shape as if milk had been spilled. The definition of the planet. A planet, according to the International Astronomical Union, is defined as any celestial body that orbits around the stars and meets the following criteria. It has enough mass to spherical and it has its own gravity. It does not have enough mass to cause nuclear fission. It has cleared its neighboring region of planetary debris. It is not a satellite of another planet. A celestial body that meets the first two criteria, but not the one regarding dominance in its orbit, and it is not a satellite, it is called a dwarf planet. The planet. Until today, there are 9 planets in orbit around the Sun, with one considered as a dwarf: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Sun. The Sun is the star of our solar system and the brightest celestial body in its sky. Its mass constitutes almost 99.9% of the solar system's mass. Some scientists also argue that in 4 to 5 billion years, the Sun will increase its mass and transform into a red giant, which may expand as far as Earth's orbit, potentially engulfing the planet. However, another view suggests that Earth will most likely move further away and survive. After this massive expansion, the red giant will begin to shrink and eventually become a white dwarf after a long cooling period, during which it will lose a significant part of its mass. Finally, it will turn into a black dwarf. Mercury. Mercury is the closest planet to the Sun and the smallest planet in our solar system. It is also one of the 4 red planets of our solar system, and it is worth noting that all of them are inner planets. Some scientists, based on NASA, state that Mercury is an untouchable treasure. This view is based on studies indicating that Mercury contains an internal layer of diamonds approximately 15 kilometers thick. Venus. Venus is the second closest planet to the Sun after Mercury. It is also the brightest object in the night sky after the Moon. Venus is often described as Earth's sister because of its great similarity. As it is only slightly smaller, it is a lunar, rocky planet, and its atmosphere is very dense with high concentrations of carbon dioxide. Earth is the planet we inhabit, with 71% of its surface covered by water and the rest consisting of various landscapes such as mountains, deserts, and plains. Earth is the third closest planet to the Sun, with Mercury and Venus lying between them. According to evidence from radiometric dating and other sources, Earth formed approximately 4.54 billion years ago. Earth is also classified as an inner planet. Mars is the fourth planet from the Sun in our solar system and the second closest to Earth. There are also signs of meteorite impacts on Mars. Mars is often referred as the red planet because of its color. Scientists suggest that Mars once had water and possibly life. Furthermore, in the future, humans may be able to live on Mars. Jupiter is the largest planet in our solar system in terms of size and mass, and it is the fifth planet from the Sun. It belongs to the outer planets and is often described as a gas giant. This is because it is the largest planet in our solar system. It is worth mentioning, however, that Jupiter is a planet composed of gases rather than solid matter. Saturn is the sixth planet in terms of distance from the Sun and the second largest in the solar system after Jupiter. It also belongs to the so-called gas giants. Saturn has 146 satellites, 53 of which have been given names. It also has numerous rings and composed of gaseous matter. Its most well-known names are Mimas, Enceladus, Thetis, Dione, and Rhea. Uranus is the seventh planet from the Sun, the third largest and the fourth most massive in our solar system. Its name comes from the Greek mythology, where Uranus was considered a deity and the father of Cronus. It is also worth mentioning that Uranus has 28 satellites. An important fact is that this planet was discovered on March 13, 1781 by William Herschel. Neptune is the last planet in our solar system in order of distance from the Sun. It is composed of gases such as hydrogen, helium, and ethane. It was discovered by Ayrton Ledretier, John Couch Adams, Jonathan Gottfried Galle on September 23, 1846. There are also 16 satellites orbiting Neptune. Pluto is no longer considered a regular planet, but a dwarf planet. This is because, according to measurements made in 2006, its actual diameter is equal to 0.18 that of Earth. It has 5 satellites and was discovered by Clyde Tombaugh on February 18, 1930. Pluto is mainly composed of rocket ice with a mass approximately 1/6 that of the Moon's. The Moon is the Earth's only natural satellite. Its name comes from the ancient Greek goddess associated with its satellite. In modern Greek, the Moon is also called Theia. It is also the brightest celestial body in the sky after the Sun. The Moon affects Earth in resulting the phenomenon of tides. Additionally, it is a rocky celestial body. Acknowledgement. Many special thanks to Mrs. Inlove Serva from help with English translation and to Mrs. Dimitra Majuka for his valuable feedback and extension of guidance. Bibliography.
Amazing. Excellent. Well done. Congratulations for all the hard work and the effort. And I'm really glad to hear that you enjoy doing this. It was obvious that you enjoyed doing the presentation. May I add, since maybe many of you may not know this, but all the gas giants, so Jupiter, Saturn, Uranus, and Neptune, have rings, but from small telescopes, like amateur telescopes from the Earth, we can only see Saturn. Okay, but if you see pictures online from the James Webb Space Telescope, you will see that all these gas giants have rings. Very nice. So without further ado, we have the Model Upper Secondary School of IE Anargiri with a presentation listening to our sun, signals from our star in the frequency range 10 to 12 gigahertz. Is someone from the school with us today?
Hello.
Hello. Hello. Yes. How are you? Everyone is good?
Yes, yes.
Excellent. Would you like to share your presentation or do I share?
We will share.
Okay, excellent.
Thank you.
Thank you.
Hello everyone, I'm Nick from Upper Secondary High School of IE Anargiri, and along the rest of my classmates, we will present you our experiment named Listening to Our Sun, Signals from Our Star in the Frequency Range of 10 to 12 gigahertz. The purpose of the experiment is to detect the relatively weak radio waves it emits in that frequency range, then convert them into a lower frequency electrical signal, and finally turn them into an acoustic signal with the help of various components. Those components include a satellite dish, an LNB, a satellite finder, a 12-volt battery, and finally coaxial cables.
Light is supposed to particle length a wave. The electromagnetic spectrum begins with the radio waves with the largest wavelength. After that, there are microwaves, infrared light, visible light, ultraviolet, X-rays, and finally gamma rays with the small wavelength.
Now, what if we had a scientific instrument that could observe sun solely in the red color of the visible spectrum in the wavelength of 617 nanometers? Then this is what we would see. Lighter colors in the image represent regions with higher light intensity, while darker ones represent regions with a lower intensity.
In this image, we can see our sun in the radio waves in frequency of 240 MHz. The solid circle indicates invisible light. But how are radio waves generated? When a charged electron interacts with a magnetic field, it accelerates and emits radiation.
Optical window and the radio wave region, which include the frequency around 10 gigahertz.
How we can measure waves coming to the red antenna parallel to the center axis are reflected to the focal point where the wave is located.
The operating principle of a radio antenna is the phenomenon of wave interference. When two radio waves
Sorry, I have to interrupt you.
align.
Sorry, I have to interrupt you because your signal is very bad and we can't hear. The last 3 slides went very fast without hearing you speaking. Sorry, the signal was very bad.
Open my data and try again?
Yes, please do, because we would really like to see the presentation, and I would ask you to go back 4 slides.
Okay.
Here. So your signal was very bad starting here when you started describing the effect around the magnetic field.
And how is the signal now? It's okay?
It's moderate, yeah.
Okay.
So
in this image, shall I start?
Yes, thank you.
Okay, thank you. In this image, but how are radio waves generated? When a charged electron interacts with a magnetic field, it accelerates and emits radiation.
Yes, but why at 10 gigahertz? Earth's atmosphere lets radiation pass only through the optical window and the radio wave region, which includes the frequency around 10 gigahertz.
How we can measure waves of 10 gigahertz by using radio antenna. Waves come to antenna parallel to the central axis are reflected to the focal point while LNB is in.
The operating principle of a radio antenna is the phenomenon of wave interference. When two radio waves arrive in phase, their peaks align and the signal becomes stronger. This phenomenon is called constructive interference.
Another crucial instrument is the LMB. Its main function is to down-convert the signals coming from the sun at about 10 GHz to lower frequencies around 1000 MHz. It is sensible only to frequencies at the range of 10 to 12 GHz, so it does not respond to lower frequencies like Wi-Fi or mobile phones.
The next instrument is the satellite finder, the field reader. It converts the radio frequencies / signals into voltage. It produces a sound buzzer. The stronger the signal, the louder the sound.
Now, in this video, we will present our experiment listening to our sound in a frequency around 10 GHz.
The materials we used, and this is the LMB.
Firstly, we point the disk towards the sun. The disk focuses the waves 10 to 12 GHz onto the LMB and receives the signal to 1000 MHz. This signal is sent through the coaxial cable to the field motor, which displays a reading and produces a tone. If the disk is turned away from the sun is loud. We really enjoyed it. Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you very much. That's great. Thank you very much. Did you enjoy doing that project?
We didn't listen to you. We didn't hear
You
you.
didn't hear me. I asked if you enjoyed doing the project. Did you enjoy building the antenna and all this process?
Yes, very much.
Yes.
It was fun.
Okay, good. Would you like to continue, maybe take it to a next level and connect the antenna to the laptop and see the signal on a screen? Because that would be the next step. So we
Yes, why not?
Okay, we could guide you with that. We are testing some process that won't require buying an SDR, which is you can order it from abroad. We don't find it in the Greek market, and it takes a long time. But we're developing a process that you can do a little hacking on the satellite finder and connect it to the laptop. And we will share it with you once it's ready. Okay. Okay, great. Thank you. Thank you. Thank you so much. Excellent. Right. Before we close and we do the closing remarks, I have a presentation by the First Gymnasium of Rafina, observation of the apparent motion of the Pleiades in the sky using Stellarium. Unfortunately, the presentation didn't play properly on our computers. We tested it in 2 different computers. So I will read through it, and my apologies to the students. So let me share. Right. Very good. So observation of the apparent motion of the Pleiades in the sky using Stellarium. Introduction. In the present project, we studied the Pleiades star cluster. The aim of the study was to understand the observed phenomenon. Theoretical background. What are the Pleiades? The Pleiades are a star cluster consisting of 7 stars that symbolize the 7 sisters. They are visible from Earth with the naked eye and are often referred to as Poulia. The Pleiades cluster was used in ancient times to determine the seasons, since its heliacal rising occurred in late May, announcing the arrival of summer, while its setting foretold the arrival of winter. Astronomically, the Pleiades are composed of young, bright blue stars and nebulae. They are located approximately 440 light years away from Earth and were formed relatively recently in astronomical terms. Apparent motion of the stars. The motion we observe in the sky is not due to the actual displacement of stars over short periods of time, but rather to, first, the rotation of the Earth around its axis, and second, the revolution of the Earth around the Sun. These motions cause the apparent displacement of constellations from night to night and from season to season. Tools and resources. The following were used for the completion of the project: the Stellarium platform, the Google search engine for theoretical information. Sources are listed in the end. Stellarium is a free night sky simulation software that allows the accurate representation of the positions of stars and planets for any date and time. So let's see the methodology, the observational steps. The procedure followed is described in detail below. First is the application installation. They downloaded and installed Stellarium application to our mobile phones. And here's a screenshot. On a daily basis and at a specific time, we recorded screenshots of the position of the Pleiades in the sky, keeping the following constant: observation, location, time, and field of view. Transfer and processing. The screenshots were transferred to a computer where they were organized by date. Image comparison. The images were compared with one another in order to observe changes in the position of the Pleiades relative to the horizon and surrounding constellations. Video creation. Finally, a video was created that depicts the gradual motion of the Pleiades in the sky. Very nice. And results and observations. Image comparison. From the comparison of successive screenshots, it was observed that the Pleiades rise earlier each successive day, gradually change position relative to the horizon, and shift in relation to other constellations. Graphic representation. For better understanding of the results, graphs were used. Graph 1, altitude of the Pleiades in degrees in relation to the days of observation. In the horizontal axis, you have the date, and in the vertical axis, you have the angular altitude in the sky in degrees. A gradual increase or decrease in the altitude is observed depending on the season. Graph 2 is the time of rising of the Pleiades per day. The horizontal axis is the sunrise hour, and the vertical axis is the date. I think it's the other way around. The horizontal axis is the date, and the vertical axis is the sunrise hour. Yes. So this shows that the Pleiades rise approximately 4 minutes earlier each day. Conclusions. In conclusion, the Pleiades are an open star cluster in the constellation of Taurus. With a naked eye, people can usually see 6 to 7 bright stars. And now I'm sure that everyone will do this. They are relatively close to Earth, about 440 light years away. They are easier to see in the autumn and winter. In ancient times, people used their rising and setting as a calendar to mark the seasons. The Pleiades also help astronomers study how stars are born and how they develop. They were very important in many cultures, including ancient Greece. In the past, sailors and farmers used them to decide when to travel, when to plant crops, and when to harvest. In addition, they were an easy and impressive object for ancient people to observe and learn from by watching the sky. So here they share their bibliography and sources. Thank you very much. And a huge thanks to the students of this school. Let me name them. Really appreciate your effort. Antonios Κατσαμπής, Δημήτριος Λαζαρόπουλος, Νικόλαος Ραφαέλ Μπαρόλας, Ιωάννης Παπασωτηρίου, George Κίμον Τέιλαχ, Άρης Πάνας, Παναγιώτης Φορούλης, Αναστασία Κατσαρά, Ενγού Γιάν Χουί. Σας ευχαριστούμε. Sorry. Thank you very much for this great effort and presentation. And I enjoyed a lot the joke about 6-7 in your presentation. Thank you very much. Great. Thank you to all. We will have some closing remarks by the radio team, whoever is online. I know it's very late for China. I don't know if Hongming is still here. But maybe here. You are, thank you. Okay, great. Sorry, I couldn't see you. Would you like to say some words for closing?
What a day. And thank you so much for giving me this very, I mean, this is incredible. This is incredible. And I really cannot imagine how creative you are before listening to your talks. And I'm sorry I was unable to attend all the talks, but for the talks I heard, I was really shocked. I must say this, I was really shocked. And thank you for your passion and not only involvement, I would say. These are all creation. And I hope in the future I can, in the long term, I can collaborate with you. Thank you so much.
Thank you. Thank you very much, Hongming. Hira, would you like to say some words?
Yeah, thank you very much. So I have been with you all the day and it was a very, very productive day. I must say that I really want to congratulate all the students for their amazing projects and all the teachers who went extra mile to support their students. We, as radio team, tried our level best to create learning opportunities for students in these three countries. And you are the one who seized this opportunity and made most out of it. So we are really proud of you. Without your efforts, our project will not be impactful. So you are the one who really created the impact. So I'm really happy for you, and I'm also very happy for the radio team because during the all day when I was listening to your presentations, I remember the moments when we were writing this proposal, especially Eleni, and we were like, okay, we will organize these online workshops, we will visit these schools, students will make their radio antennas, and in the end there will be an international workshop where students from these countries will be presenting their projects. And yes, today is the day. We have done it. Yes. All the online workshops, the school visits, the students making these radio antennas, and now they are presenting their projects. So yes, so we are happy because of you. You help us achieve all these things. So we are really proud of you, and we are looking forward to work with you again and again and extend this project and this initiative to the next level. Thank you.
Fantastic. Thank you very much. I think Faisal has left the Zoom, but we thank him also for the great Python demonstration. And we urge you to get the notebooks and try out Python. I also would like to thank everyone, the radio team, the teachers, the students, the parents that supported this. Grateful for that. And today we saw how radio astronomy can connect the students across countries, across cultures, and continents, okay, through international collaboration and teamwork. That was important and very amazing to see all the students working together. So by working together and sharing ideas and learning from each other, we saw that science is a powerful way to explore the universe and build bridges between people. So this is the message I want to leave you with. And we will call it a day. Thank you very much. We hope to continue this, and we will invite you when we have news about the continuation of our project, so you can join us. Thank you very much, everyone. Thank you.
Thank you.
We thank you. Congratulations to the team that organized it.
Thank you very much. Thank you very much. Your presentations were